couple of minutes. We can delay a little bit.
Okay.
Still, some participants are coming in.
So is there a chair or introducer for this session?
We have two chairs. And they will introduce you.
Okay,
Just
good.
A couple of
Thank
minutes.
you.
I think we have more people coming in.
Very good.
And can you play the screen file and the shared file, just back and forward? Let's see whether it is moving.
Okay. No. Okay, I need to do this.
Your file, I mean.
Yeah, I'm checking it now. I need to do this. This. No. You see the change screen?
Yes, and then go to the second page. There's one more page. Okay, it looks fantastic.
Okay.
Yes.
Brilliant. Thank you.
Valerie, and I think you can have the chair. Yes. Okay.
Okay, should we start? Okay, it's a pleasure to welcome, let's say, electronically welcome and introduce the first speaker, remarkable physicist Seamus Davis. Seamus, it's a pity that you couldn't join us here in person, but it's great to see you even online.
Very good.
Okay, so please, actually Seamus, our outstanding physicist of our time, doesn't need much introduction, and he will be talking about his most recent finding on the electron pairing mechanism of superoxide high temperature superconductivity. Seamus, please go ahead.
Okay, wonderful. Thank you very much for inviting me to give this presentation. It's a privilege to do so, and it's an exciting time for me. I'm dialing in this morning from Oxford. It's still dark here, but it's as beautiful as ever. And I'm going to be representing a team made up of my group at Oxford and also my group in Ireland. It was a joint effort between two parts of our group. So the subject of today's discussion is the mechanism of CuO2, copper oxide high temperature superconductivity. Oops. Excuse me, I need to change something. Okay, so, everyone in this audience perfectly well aware that superconductivity is profoundly useful and important state of matter. And it plays a giant role in science today, all kinds of advanced medical, bio, astrophysical, high energy physics, high field, high fusion, and quantum computing. So we need more superconductivity, and we need higher temperature superconductivity, and we need to have the material science necessary to design the room temperature superconductors of the future. That's really what we've been struggling with for a number of decades now. So I'll remind you that electrons can't really condense into a macroscopic quantum state unless they pair, and if they pair, you can write a two-particle wave function of this type. It's quite generic. It's got a real space component and it's got a spin component. And in this talk, we're just going to deal with spin singlets. So I showed the singlet component there on the top left. And you can expand this into creation and annihilation operators if you like that kind of stuff. It's shown on the top right. So even a single pair is written as a sum over the average, or the sum over two operators of opposite spin and opposite momentum. Now, if for some reason all those pairs can condense and form a macroscopic quantum state, then you have a superconductor. And I'm deliberately not saying here, Bardeen, Cooper, Schrieffer, I'm saying just if there's any mechanism Probably color superconductivity, you know, doesn't use Bardeen-Cooper-Schrieffer. It uses other mechanisms. Probably neutron star, you know, superconductivity doesn't use Bardeen-Cooper-Schrieffer. So the point I'm trying to make is that if you can condense a macroscopic quantum number of Fermi pairs, you get a macroscopic quantum state. It's got a macroscopic wave function with an amplitude, often called in superconductivity world the energy gap, but it's really the amplitude of the wave function, and a quantum phase. And something we'll have to keep in mind for this talk is that the modulus squared of the amplitude is the number of condensed particles in the condensate, the number density of pairs. Now, here's Bardeen-Cooper-Schrieffer. In this gloriously beautiful theory, you consider fermions of opposite momentum and opposite spin, and they interact in a two-particle fashion through an interaction potential of VKK prime. Of course, that's true in general for any gas of fermions, but we just focus on this scattering process. B, C, and S hypothesized that the many-body wave function is the one shown there on the right, capital of psi. It's a product state. It's not entangled, no matter what your high-energy colleagues tell you. It's not an entangled state. It's a product state. But it's a product state of singlet pairs. With that product state, you can write down the BCS theory. So you write the order parameter, delta K, as the sum over momentum space for the interaction potential, VKK prime, that's a Fourier transform of the interaction potential in real space, times the average value of this anomalous operator, C minus annihilation minus K spin down, annihilation plus K spin up. Now, you'll be stuck unless you had a wave function which you could calculate the value of that average, but we have the BCS wave function, so we can calculate that average of C, and it's this famous gap function. There's a self-consistent function. If here, for a given interaction potential V and for a given band structure E of K, a solution for delta of K can be found, then we say we have a BCS superconductor. Its energy gap, its order parameter is 1.76 times KBTC for S wave. That's has guided our thinking now for half a century, and it's a magnificent piece of theoretical physics. But it's not the general case. The general case is any mechanism which will condense an anomalous average C up, C down, averaged over the whole wave function, not equal to 0. And that mechanism does not have to be BCS. All right. Now let's turn to CO2. You all know, starting in the 80s, some of you even remember, a few of us remember, when the cuprates were discovered, TC started shooting up. In fact, 35 years later, these are still the highest critical temperature ambient superconductors. They still represent the best starting point for room temperature superconductive electronic technology that we have available now. Now, admittedly, the hydrogen sulfides and lanthanides appear to superconduct at room temperature, but only at hundreds of millions of atmospheres. At ambient pressure, the cuprates are still our best superconductors. And we'd like to actually control them by understanding what pairs the electrons together in these compounds at such tight, strong binding energies and superconduct at such high temperatures, minus 100 degrees centigrade. Now let's think of the electronic structure. So the CO2 plane is a square lattice of copper, oxygen, copper. The coppers are in the 3D9 state. To put them in the 3D10 state requires a Coulomb energy, U, which is about 3 electron volts. The overlap integral of copper and oxygen makes what would be a hopping rate of around 400 millivolts. It's a very strong overlap integral. And now if you represent that as a band structure shown on the right, the 3D9 band is at the bottom, the D band. It's separated from the empty upper D band by the Hubbard or Coulomb energy U, and that's a very big energy. But when Mother Nature was inventing this material, she put the oxygen p orbitals in between. So the energy level of the 2p6 oxygen p orbitals is much higher, and the energy splitting between the 2p6 orbital and the 3d10 orbital is called the charge transfer energy. I call it epsilon. We had to change it from delta to epsilon for the experts because it's too confusing when you're measuring the order parameter of the superconductor and you call it delta, and you're measuring the charge transfer energy and you call it delta. The referees get confused. So we call the charge transfer energy epsilon. Now at half filling, Coulomb, this is a Mott insulator. It's an antiferromagnetic Mott insulator. But you can hole dope it. And hole doping, it's not like hole doping a semiconductor. What you're doing is removing an electron from an oxygen atom in the p band. And when you do that, transport begins, some kind of a quantum mechanical state, which in my opinion is not fully understood, is created. But it allows transport through the crystal as soon as it appears. Then we get this glorious phase diagram. So P is the number of hole densities per CO2 unit cell, temperature on the left-hand axis. You only have to put 1 or 2% of holes into this compound to destroy the antiferromagnetism. A mysterious phase, which I call electronic dark matter, but other people call the pseudo gap, appears. And then by the time you get to 15 or 20% hole density, you get high temperature superconductivity. It's beautiful, but we don't know why. What is the actual mechanism that's producing this robust high temperature superconductivity in dozens of different compounds? It's quite a universal phenomenon. All right, now let's turn our attention to superexchange. And here I'm not talking about a crystal, I'm just talking about 3 atoms, 2 copper atoms in the 3d9 state and 1 oxygen atom bridging them in the 2p6 state. You can write the Hamiltonian for those 4 electrons. And, you know, if you know what you're doing, you could diagonalize it, but, you know, it's relatively easy to solve in perturbation theory. So you write the energy of the d states, you write the energy of the p states, you write the PD hopping rate, and then you know, destroy a p and create a d or vice versa. And you write the Hubbard energy on the 2 copper sites, Hubbard energy U. So that simple Hamiltonian you can study. In fact, of course, it was studied in the 1950s. It's well understood for 3 atoms. But it represents very subtle physics. I'd like you to think about that. So consider the 4 electrons. The top 2 lines here are the 4 trivial conformations of those electrons. So 1 copper is spin down, the other copper spin up. The 2p6 orbital, each of the 2p6 orbitals is in the signet state. And there's 2 ways of doing that in my cartoon, no problem. Now, if you have hopping from oxygen to copper, that's how the transport starts, hopping of an electron from oxygen to copper. So the middle row shows what happens. If an electron hops onto the copper site, the energy level for the 3d9 state disappears. It no longer exists in the Hilbert space, and the 3d10 state appears at a high energy. And there's 4 simple ways for that hopping to occur. And then on the lowest row is the next most interesting process, which is 2 hops, 1 from copper to oxygen, 1 from oxygen to copper. It also has multiple conformations, and so on and so on. You can solve this problem, at least in perturbation theory, and if you just focus on the spin-spin interaction, neglect the transport, then that part of the Hilbert space is described by Heisenberg Hamiltonian, and this has been known since the late 1950s, by Heisenberg Hamiltonian, SI.Sj, where Si is the spin on 1 copper, Sj is the spin on the other copper. And the strength of that antiferromagnetic spin-spin interaction is given by J, superexchange J, which is written there for just 3 orbitals. In the case that the Coulomb energy, the Hubbard energy, is much bigger than the charge transfer energy, and there's many transition metal materials where that's not true. Transition metal oxides where that's not true. But for the cuprates, it is true. U is much bigger than epsilon. In that case, the superexchange energy is, in perturbation theory, is 4 times the PD hopping rate to the power of 4 divided by the charge transfer energy cubed. That tells the strength of superexchange between adjacent spin-a-half electrons on the copper sites. Now let's take that picture and generalize it to a lattice. Now we won't take just 3 atoms, we'll take, 10 to the 30 atoms. We'll take an enormous square lattice of CuO2. So under those circumstances, you'd have a Heisenberg Hamiltonian on the square lattice, and you can solve that in 2 sublattice mean field theory on the back of an envelope. And you all know the solution. It's an antiferromagnet. This antiferromagnet has to have the band structure of CuO2. So it has to have a lower Hubbard band, 3d9, upper Hubbard band, 3d10. It has to have the 2p6 band in between and the charge transfer separation epsilon. But otherwise, the spin-a-half electrons should form, in theory, a spin-a-half square lattice antiferromagnetic insulator, if superexchange theory is correct. And of course, that's exactly the state which occurs in the parent state of the cuprates. So what this tells us is that the superexchange picture is correct for the undoped compound. All right, now look at your CuO2 up here. There's 4 electrons, 2 on the copper sides and 2 on one oxygen side. If we take away just 1 electron, now we're in the whole doped situation. And this is a completely different, Hilbert space and really very different physics. As I just said, you get a completely new phase diagram containing unidentified phases, containing exotic density waves, containing high temperature superconductivity, all just because you took away 1 electron from the oxygen atoms. Now, high TC superconductivity. The band structure can't be changed much by, adding 5%, 10% of holes. It'll be approximately the same, but maybe a new hole-doped band, sometimes called the Zhang-Rice band, would appear at the top of the oxygen band. And we know it's a superconductor. So Phil Anderson, God rest his soul, in 1987 proposed that what happens is that you destroy the long-range antiferromagnetism, but you keep the superexchange interaction. The superexchange interaction now forms singlet pairs, and they condense to make a high-temperature superconductor. So my code for this hypothesis is up here on the right. He basically said charge transfer superexchange, epsilon, is what causes the condensate of electron pairs. There's no electron-photon interaction. There's no antiferromagnetic spin, weakly interacting antiferromagnetic spectrum of antiferromagnetic spin fluctuations. It's just superexchange which does this. That's a hypothesis, but a work of great genius, of course. Now, for those of you who remember those days, cast your mind back to the late 1980s. The world's leading condensed matter theorists were all working on, the mechanism of high TC. So look down here. So Ruckenstein, Peter Hirschfeld, superexchange mechanism. Gabby Cotliar and Liu, superexchange mechanism, okay? Charge transfer antiferromagnetism and superexchange pairing correlations, Doug Scalapino. So this was the central idea that was being pursued in the first few years of this field. And wonderful, that's fabulous. Now, fast forward 35 years and ask yourself, what's going on in the theory of this field? It's the same. People pursuing the doped 3-band Hubbard model in search of the superexchange mechanism, charge transfer superexchange mechanism of high temperature superconductivity. Of course, nowadays, the theoretical tools are immensely more powerful than they were 35 years ago. But the focus of the research remains the same, to understand whether charge transfer superexchange is the mechanism of high temperature superconductivity. And why is this focus still going on? It's because experimentally, this is an unresolved question. All right, now let's think about the 3-band Emery model. This is Vic Emery, God rest his soul. He passed away as a relatively young man. In '87, he said the correct model we should use for the cuprates is to keep the 2 oxygen orbitals in the band structure. So his Hamiltonian had both the energies of the states, of the 3d9 state of the coppers and the energies of the 2p6 state. So alpha and beta sum over both copper and oxygen orbitals. He kept the Hubbard energy on the copper side. It was known to be there. And he kept all possible hopping processes between different orbitals. That Hamiltonian was not solvable in 1987, and that Hamiltonian is not solvable in 2022 in an analytic form. But we have modern theory tools, and I'm not a theorist, but I just want to sketch for you dynamical mean field theory. So suppose you have a complicated correlated problem you want to solve, like the 3-band Hamiltonian for the cuprates, shown in the white box in the middle. So in DMFT, what you do is embed a small, let's say 3 atoms or 12 atoms, or a small number of atoms, a cluster of the atoms with their correct Hamiltonian, embed that in an effective medium, which is a metal, Green's function for delocalized fermions. Then you solve for the impurity states which are created by your accurate Hamiltonian cluster embedded in the medium. If you find that solution, you extract the self-energies. Using the self-energies, you update the Green's function of the medium. And then you check, does the Green's function of the medium, is it consistent with the Green's function of the CO2 model you're trying to solve? And, typically it's not on the first iteration. So you go around again, you update the Green's function of the medium with the new self-energy, and now you resolve the impurity problem. And you just go around and around and around until the Green's functions of the effective medium are indistinguishable from the Green's functions of the Hamiltonian you're trying to solve. And then you regard that as a clustered DMFT solution of a very complicated correlated Hamiltonian, like the 3-band Emery model. Okay, so here's the 3-band Emery model. Modern calculations often use 4 coppers and 8 oxygens, so 12 atoms as the cluster. Then they embed that cluster in a medium, solve using continuous time quantum Monte Carlo for the impurity states produced by that embedding, extract the self-energy, update the Green's function, check to see if it's consistent with the medium. If not, go around and around and around until it converges. If it converges, and the geniuses behind this theoretical mechanism have figured out how to typically make it converge, if it converges, now the medium and the Hamiltonian you started with, the one in the red box, have the same Green's functions, which are the eigenstates of the system. So if you know those Green's functions, you can calculate what's the value of the anomalous average for pair condensate. So here, I didn't say anything about electron, boson, coupling, or anything like that. I just said, solve for the Green's functions and then calculate the anomalous average. If that anomalous average, Ci up, Cj down, averaged over the whole many-body state, is not 0, then we say the theory says it's superconducting. This technique gives great power to the theorist. One thing you can check, so this is a solution from André-Marie Tremblay's group in Sherbrooke just last year, which was a big motivation for us. Here's our cartoon of the band structure on the left. Lower Hubbard, charge transfer, hole doped, upper Hubbard. Well, the modern DMFT solution of the 3-band model has a lower Hubbard band, a charge transfer band, a hole doped band, and an upper Hubbard band with a charge transfer gap in between them. They can see the charge transfer gap directly in the solution. Okay. Now, if it's just a question of do modern theories identify the mechanism of pairing within this Hamiltonian, there's wide acceptance that the pairing is coming from what I would call charge transfer superexchange. In the 3-band Hubbard model, you can see, world's leading theorists listed here, and now up-to-date theoretical calculations showing that this is the case in theory. The tricky part is that there has been no empirical test of the relationship between the charge transfer energy and the amplitude of the pair wave function. So none of these beautiful theories have been tested directly at atomic scale in experiment. Right. Now they give great power to the theorist. If you look at the bottom right-hand graph here, the horizontal, so now the theorist can model a material, let's say lanthanum cuprate, with the correct parameters. Then calculate how big is the pair wave function, I'm going to call the average of Ci up, Cj down, averaged over the many-body state. I'm going to call that the pair wave function from now on. So they can calculate the amplitude of the pair wave function. And now they can just, in theory, reach in and dial the value of the charge transfer energy. Okay? So for lanthanum cuprate, this was done by Weber, Howell, and Kotliar. They, adjusted the charge transfer energy, and what they found out is the pair wave function amplitude changed very rapidly as you change the charge transfer energy. You're not changing temperature, you're not changing the carrier density, you're just changing the charge transfer energy, but it has a huge impact on the superconductivity. And last year, Andre Marie's group did this calculation for BISCO, which is the material we can study, and they also found that the pair wave function, amplitude of the pair wave function evolves quickly as the charge transfer energy is increased. And of course, it evolves in the logical direction. As the charge transfer energy gets very, very large, the material has to turn into an insulator. And so the superconductivity has to disappear. And that's exactly what happens in the theories. All right. So here's some and now in order for us to make an experimental test, we needed to normalize the value of the amplitude of the pair wave function. So we normalized it by the value reported by the theorists for the standard materials parameters of the compound, the charge transfer energy, which actually exists in the real compound. So that allows us to look at their predictions and say, in BISCO, pair wave function amplitude, the charge transfer energy goes as minus 0.5 per electron volt. And for LSCO, it goes as minus 0.3 per electron volt. Now, unfortunately, you can't measure CI dagger CJ. It's a complex field. You have to measure, in our universe, you have to measure a real number. So what experimentalists can measure is the magnitude squared of the pair wave function amplitude, which is the number density of the pairs. So for BISCO, the Shabrook prediction is that the rate of change of condensed pair density with charge transfer energy should be 0.9 per electron volt if charge transfer superexchange is the mechanism of ITC. And here we just summarized, in fact, this has been predicted for a range of materials now. So horizontal axis is charge transfer energy, vertical axis is normalized pair density, normalized by the ambient pair density that you would get for the standard parameters of each material. And that yellow cone there is the cone of interest. The astrophysicists would say, the phenomena are, if charge transfer superexchange is the mechanism, then if you do the experiment, the results should lie inside that cone. All right. Now, how could you test this idea? Well, the first thing you need to do is to change the charge transfer energy. So that's a tricky one. But Gabby Kotliar and his team identified how to do that. You can do it by altering the distance of the apical oxygen atom from the copper atom. The apical atom is minus 2e charged. If you move it closer to the copper atom, it drives up the charge transfer energy, and farther away, it drives it down. DMFT has revealed this for a wide variety of different compounds. Roughly, you get about 1 electron volt of change of charge transfer energy for 1 angstrom of motion of the apical atom. And this concept has been around since the beginning of cuprate research. Move the apical atom, alter the charge transfer energy. So that's the objective. So here's a cartoon now, a little movie showing the concept of our project. So on the top line here, you see the copper oxygen plane. So oxygen is red and copper is blue when they're in the plane. And I show the apical atoms above the copper atoms. The line below is the actual hypothetical electronic structure in this situation. The 2p6 state is in red, and the 2 copper 3d9, 3d10 states are in blue. And below that, the amplitude of the pair wave function. Below that, the number density of electron pairs. So if we could change the apical distance, what would happen to the charge transfer energy epsilon, and what would happen to the electron pair density? Well, as a cartoon, this is what we would expect. As we move the apical away, the charge transfer energy goes down. So as we move the apical away, charge transfer goes down, but superfluid density goes up. as we move the apical towards, charge transfer energy goes up, but superfluid density goes down. That's the concept. All right, how would you do that experiment? Well, Mother Nature has been very, very kind to us. In BISCO, there is a supermodulation of the crystal in the 1-1 direction. Every 26 angstroms, 26, 27 angstroms, roughly, there's a modulation there's an undulation in the position of the bismuth atoms on the surface. That's what you see on the top left-hand side. And we know from X-ray scattering, exactly what's happening there. The gray dots on the top right-hand side tell us the location of the bismuth atoms in the top layer. But from X-ray scattering, we also know what's happening to the copper to apical oxygen distance inside the crystal. So when the bismuth atom is at maximum displacement along these squiggly lines here, then the copper oxygen atom in the plane is the apical to copper atom is minimal. And when the bismuth atom has minimum displacement at what we call phase pi here, then the apical distance is maximum. So everywhere in this picture, by using X-ray refinement, one could know in principle how big is the apical distance between the apical oxygen and the copper atom. And we have enough precision to know that for every atom in this field of view. Okay. Now it'll turn out the quantitative value of that number is not critical, but for the material scientists, the thing to realize is that the apical atom moves almost 0.4 angstroms. The type of pressure that you would need to do that in a controllable way is huge. So this is an amazing situation where the apical atom moves a very significant fraction of the unit cell in one of these modulations. Now, how would we visualize the energy gap between the top of the P band and the bottom of the D band? It's not that complicated. At the top of the P band, the tunneling density of states zooms up extremely quickly. And at the bottom of the empty D band, the tunneling density of states zooms up very quickly. And you can measure the energy difference between those two bands. We did it long ago when looking for the dopant atoms. And Yayu Wang has done a beautiful study of very lightly doped cuprates where he measures the same thing, the charge transfer energy. And in our study today, we're using the same technique. We just measure the energy difference between the top of the P band and the bottom of the D band. And the vertical scale in the top right-hand panel here is logarithmic. So the density of states is screaming up exponentially. Your ability to measure this epsilon is very, very good. Now, you could argue that maybe we don't measure the absolute value correctly, and possibly that's true, although the value we find is consistent with everything in the literature for multiple different techniques. But the following statement is definitely true. If there are changes in the value of the charge transfer energy, we can see those with high precision. That statement is true. Okay. And last but not least, we need to visualize the density of electron pairs. And for that, we use scanned Josephson tunneling microscopy, a superconducting sample and a superconducting tip. Under those circumstances, there's a Josephson current of electron pairs from tip to sample. The Josephson current density goes as the amplitude of the two wave function, the product of the amplitudes, and the amplitude is the square root of the number density. So in Ambergaukar-Baratov, the Josephson current through this junction multiplied by the normal resistance of that junction is proportional to the gap in the tip and the gap in the sample. And we assume that the gap in the tip, the number density in the tip is constant. So what that means is if I square the Josephson current, if I measure the Josephson current, critical current squared, and suppose I keep the normal resistance constant, then I get a measure at that location of the density of pairs in the sample. This is, the concept has been around for decades to visualize the condensed electron pairs rather than the single electron quasiparticles. However, you really can't do this as shown on the screen here. And the reason is that the junction resistance for STM is enormous. So that means the Josephson critical current is tiny. It's, few picoamps. And so that means the Josephson energy is equivalent to a temperature in the microkelvin range. You need a microkelvin STM. No one has succeeded to do this. Okay. Luckily for us, Bob Dines identified a solution when he pioneered this technique. And he showed that even if the phase is not rigid between the tip and the sample. Suppose the horizontal axis here is phase difference. Suppose the phase is wandering around in some stochastic way. As long as the average of the phase over the sign of the phase is not zero, then there is an electron pair current. And the electron pair current occurs at finite voltage, but the electron pair current has a maximum Im, and the maximum is in theory proportional to the Josephson critical current squared. And the electron pair conductance has a big peak at zero bias. It's not a Majorana, don't get excited. It's a peak in the pair conductance, and the magnitude of that peak is proportional to the maximum in the pair current, which is proportional to the Josephson critical current squared. So what Dyn showed is that you can measure the pair density in the sample by measuring either the maximum in the diffusive pair current or by measuring the value of the pair differential conductance at zero bias. And you have to know what the normal state junction resistance is. So either keep it constant or measure it, but then you could visualize the pairs. Okay, so to do that for Bisco, we had to make a high TC tip, which we did by exfoliating a little piece of Bisco onto the tungsten tip. After that process, we can tell that the tip is superconducting because the energy gap is 4 delta, not 2 delta in the single particle spectrum. And we can tell directly by visualizing that we still have atomic resolution. These are two completely different tips. And, you know, this technique has been repeated in other labs as well. So it's known to work. So with such a tip, and now just using voltage differences of microvolts, this isn't the tens of millivolts you use for quasiparticle tunneling, it's just tens of microvolts. As you bring the tip in close to the surface, you see the pair current branch appearing quite beautifully. We were thrilled to see this. Now, what we want to measure is the maximum in the pair current as a function of location. So in doing that, so here's a typical topographic image of Bisco with the superconducting tip. Now, in that field of view, if we measure the maximum of the pair current at a few tens of microvolts, it looks like this at 50 millikelvin. I forgot to say, you have to be at low temperatures. It looks like that. That's one of the first, that might even be the first image ever made of an electron pair condensate in a superconductor. You're not looking at the quasiparticles, you're looking at the pairs in that image. Now that has spawned a whole new industry that I'm not going to talk about here. We were extremely lucky that in that first experiment, we found that there is a pair density wave in the cuprates. And now, you know, the scan Josephson tunneling microscopy is a growing field of condensed matter physics. It's an exciting field of condensed matter physics. I'm not going to talk about that, just to assure you that this technique definitely works, and several different groups now know how to use it. Okay, now let's do our experiment. We want to quantify apical distance delta, charge transfer energy epsilon, and electron pair density in Bisco. Now, in this compound, you know, we can label this 1-1 modulation by its phase. We set the phase to be 0 at the line of maximum displacement, pi at the line of minimum displacement, and 2 pi at the next maximum, and so on. So we could label the phase everywhere in this field of view. And for each phase, we know what is the apical distance from X-ray refinement. So let's do that experiment. Top left-hand side is a topographic image with a tungsten tip. We can see the supermodulation throughout the image. We can label the phase of the we can measure the phase of the supermodulation everywhere in that field of view. And from the X-ray refinement, we can estimate the apical distance everywhere in that field of view. And the apical distance is changing by more than 0.3 angstroms in that image in the left. So that's with a conventional tip. Now with a superconducting tip, we figured out how to do the same thing. We can see the supermodulation, we can measure its phase, and we can label the apical distance, you know, for the supermodulation. So that allows us to measure the phase of the supermodulation, and if you believe the X-rays, to measure the apical distance in our experiments. Now let's get to the heart of the matter. What happens to the charge transfer energy as you go along this modulation in the crystal?
Seamus,
So,
sorry to
yeah.
interrupt, but it's the only way to let you know that you have 5 minutes left.
Perfect, good timing. I have only 5 minutes left to speak, so we're in good timing. So, you know, if you measure the differential conductance plus minus several volts along the red dashed line, and if I plot the differential conductance as a color scale here versus energy along that line, what you see is that the energy difference between the top of the lower band and the bottom of the upper band is modulating. And it's modulating once per supermodulation period. And it's modulating by a lot. So we were thrilled to see that. And similarly, if we have superconducting tip, we see the supermodulation of the crystal. We measure the maximum in the pair current along the red dashed line. If I plot the pair current magnitude versus energy in microvolts along that line, it's modulating. So these are facts. There's no theory involved here. I mean, you have to agree that the experiment is working, but there's no theory involved here. The energy gap between the two bands is modulating, and the Josephson current is modulating with the supermodulation. All right. So let's take that at face value. We know the phase everywhere in this field of view. We know the charge transfer energy everywhere in that field of view. So we can plot a 2D histogram of charge transfer energy versus phase and reduce that to a curve. Charge transfer energy versus phase in 17% BISCO looks like the bottom right-hand curve there, measured. You can see the charge transfer energy is changing by more than 0.3 volts. It's amazing. Similarly, you can measure the Josephson current or the Josephson conductance. We had to measure the normal state junction resistance squared and multiply, make a 2D histogram, and then show this is the number density of pairs versus the phase of the modulation measured. And the number density of pairs is changing by almost 20%. So this is the summary of the experiment. Find the phase from the topographic image, find the charge transfer energy in red from the gap in the spectrum, find the electron pair density in blue from the Josephson current, and label them all by the phase of the supermodulation. If you do that, then you can plot number density of pairs versus apical distance. It shoots up. The bigger the apical distance, the stronger the superconductor. Haha, people predicted that 35 years ago. Charge transfer energy, it shoots down. And in fact, it shoots down on the curve, which has been expected for more than 30 years. It does exactly what's expected. All right. Now we can quantify rate of change of electron condensed pair density with charge transfer energy by removing the common variable, which is phase. And here's the key result of the experiment. You can alter the condensate pair density by almost 25% in BISCO by altering the charge transfer energy by almost 35% in BISCO, by almost 30% in BISCO. This is a fact. Okay, independent of theory, this is a striking fact that you alter the strength of the superconductivity by dialing the charge transfer energy. Now, this fact, it turns out, is consistent with the theoretical predictions from the cluster DMFT calculations for hole-doped CuO2 using the Emery 3-band Hamiltonian, which is an amazing fact, I have to say. We were startled, and so were the theorists. Okay, so here's the conclusion. The hypothesis is that charge transfer superexchange, charge transfer epsilon, controls the amplitude of the pair wave function. In pursuit of that, we can measure the charge transfer wave function with atomic, the charge transfer gap with atomic resolution. We can measure the amplitude of the pair wave function with atomic resolution. And they both modulate by almost 30% in BISCO because Mother Nature is kind to us. That modulation produces this relationship between pair density and charge transfer energy. Now, this is a fact in and of itself, but if you're willing to stipulate to the 3-band Emery model and its DMFT solution, then the measured relationship between pair density and charge transfer energy is in excellent agreement with the theoretical predicted relationship for charge transfer superexchange being the mechanism of high temperature superconductivity. Okay, the other thing which emerges from this is that really, in my opinion, we should concentrate our attention now on powerful solutions of the three-band Hubbard model for the cuprates as a predictive theory for to find new superconductivity, to find new physical phenomena. It appears that this theory has traction on the reality of the experiments. And with that, and I'd like to acknowledge our super exchange team. Most of the work they had to do was during the pandemic. So I'm really grateful to them for their excellent work. And thank you all very much for listening.
Seamus, thanks so much for your exciting talk and wonderful presentation. Are there questions? Please. Who is the first? Yeah.
Thank you. Good evening. This is Amit Karen. I don't know if you can see me. Super talk on superconductivity, very nice. But I have a question. The bottom line is that the super exchange is what counts, and the super exchange can vary with T or charge transfer gap or U, because they are not so different, U and epsilon that you have in your slide.
Hi, Ahmed. Yeah, thanks for that question. So
wait, I didn't ask yet.
we don't study the super exchange J. We have no access to it. We just study the charge transfer gap.
I know, but I just want to say that in the literature...
And it's an empirical fact that the charge transfer gap controls the superconductivity. So discussions about J don't play any role in that empirical fact.
In any case, can I finish my question? In the literature, there are papers in the past that show connection between TC and J by Reeks and Raman and USR. And so my question is, can you pinpoint what is exactly new, or what was not in those papers that you are reporting?
Very good. TC is not a measure of the amplitude of the pair wave function in a correlated superconductor. That's known very well from the three-band Hubbard models. So TC is not a proxy for the condensate.
All right.
More questions? Okay. If there is no more questions from the audience, Seamus, can I ask just simple-minded question concerning the experiment? So, am I understand correctly that what you definitely see in the experiment, that you have something what you could call, let's say, self-induced or developed for one or another reason, electronic granularity, and then the transport which you see, and in a superconductor is sort of like hopping between these, let's say, inhomogeneities in a condensate density. Is that
right?
And that's why. And that's why
let me share screen and answer that question. So obviously for many decades, there's been the hypothesis that the condensate of electron pairs in the cuprates is heterogeneous. But when we visualize it directly, it's not. The heterogeneity you see here is due to zinc atoms, which were substituted on the copper side in order to test the technique. And in fact, away from the zinc atoms, the superconductor, the condensate itself, is highly homogeneous. So this came as a big surprise to us, and we're still trying to understand what it means. And even though the single electronic structure is heterogeneous, the condensate appears to be homogeneous. But this is now at the frontier of our capability to do scan-Josephson. So it remains, it's a mystery that remains to be solved.
Thank you. Well, if there are no more questions, let's thank Seamus once again for a wonderful presentation.
Thank you. Bye.
And we have this certificate. And well, probably it will be sent to you.
Very good. I look forward to that.
Okay, thank you very much once again.
All right. Bye, everyone.
Bye.
Bye.
Okay, so let's move to the second talk, which will be in the same mode, I believe, right? It's Bernd Büchner from Dresden, and
Good morning.
the title is Orbitals and Pneumaticity in 111 and 111 type ferrum-based superconductors. Bernd?
Okay. Good morning, everybody. Can you hear me? Sorry, can you hear me? Can you also see my slides? Does it work?
Yes.
Okay, so then good morning, everybody. First of all, I would like to thank the organizers for inviting me to this conference, and I regret very much that I'm not able to be in Turkey, not able to be in Bodrum. And thank you to the organizers that they allow me, or they gave me the possibility to change the presentation to this online version due to health reasons. So sorry for not being with you. So what I'm going to talk about is iron-based superconductors, and I'm going to talk about two different systems. Two different systems. These are, let's say, the 1111 type systems and the 111 type systems. They are very, very different compounds, and also the aspect which I would like to discuss with you in the next minutes turns out to be very, very different in these two systems. So this is the outline of this talk. I will show you phase diagram now on single crystals, which we obtained for first series of these 1111 type crystals, and discuss in particular the nematic fluctuations, and arguing that there is a very strong coupling between these nematic fluctuations and superconductivity, which points to the real role of orbitals in these systems. I will show you some recent experiments where we measured strain-dependent thermoelectric transport, so where we have direct access to changes of Fermi surface and scattering upon tiny changes of the lattice structure, so an intimate coupling between lattice and electronic degrees of freedom. And then if time allows, I will continue and will show you also recent results on lithium ion arsenide, which is a very peculiar, very nice system on the one hand, because it allows very detailed studies of surface science, so photoemission and STM studies. But on the other hand, it's really very much different from the other iron-based superconductors, also with respect to the phase diagram and the properties, and this I will discuss. And I will in particular discuss here evidence for nematicity, which is very much different from that what we found in other systems. So before starting, I would just like to mention the people involved in this work, a big team in our institute, starting from the synthesis of crystals. And Ria Kappenberger, she was really crucial, PhD student, crucial to find the first way to synthesize these large single crystals on these 1111 type systems. We do NMR, NQR. A large part of the talk will deal with nematic susceptibility to transport measurements, and here Federico Caglieres and Xiaocheng Hong were main players in the game. And then at the end, I will come to ARPAS, and most of you probably know Sergei Borisenko is the head of our ARPAS team. Okay. Iron-based superconductors, are they good metals or are they bad metals? And I think this question is not easy to answer. And it's very much different from the cuprates, where we think that all the systems behave rather similar. In the iron-based superconductors, there are big differences. If you just look at the resistivity, for example, you find systems which are really very nice nice metals, like lithium iron arsenide. So this is a measurement of resistivity. You have a large RRR, you have a tiny residual resistance. You can fit this resistivity behavior as T-square behavior. So this really looks a lot like a conventional nice metallic state, and then you have a superconducting state. There is, however, a clear exception from this rule. And this exception from this rule are these 1111 types of systems, in particular this lanthanum oxygen iron arsenide compound. And already in the first work, when this superconductivity was discovered more than 10 years ago, nearly 15 years ago, you see there is this upturns, and then you need to dope in order to get some metallic conductivity. And this remains the case till today. So I think this is the smallest resistivity I ever found in a single crystal on these 1111 type systems. So you still see this upturn here. Then there is a strong decrease. You have these structural and magnetic phase transitions, which I will discuss in more detail later on. And then there's a decrease. And this already tells you that this increase and this overall huge resistivity is not extrinsic. So you change, you even open a gap and nevertheless resistivity decreases. So you have an intrinsic reason for an extremely bad mobility of electrons. You're very, yeah, we have a really bad metal in these systems. And what you have to do is to have to dope, and then at the end of the day, you end up with something which looks like a T-square in a nice metal. So in some sense, if you look on this, again, very old data, if you look on this doping dependence, this really looks a little bit like a cuprate. So you start from a very bad metal, and then you end up with metal upon doping only. So it's already telling you that you are far away from a conventional metallic state. And there's another experiment telling you something like that. So for example, if you start from the optimally doped compound here and plug in a tiny amount of impurities, superconductivity crashes down. And this again goes along with a localization of charge. Again, you immediately come again to a localized state when you plug in some defects in these systems. So that's really completely different situations than we have it in this lithium iron arsenide, far away from a good metallic state, very close to a localized state. I admit that I do not know a reason for that. So if you ask the theoreticians, they will tell you, okay, electronic structures are very similar. There's no reason for that. So the crystal structure of these layers is very similar. If you have a look on this, if you have a look on the structure, of course, there is a difference. So we have these iron arsenide layers here embedded between lanthanum oxide layers. This makes the system probably much more two-dimensional. It's also really from chemistry, it's completely different. It's not an intermetallic compound. It also makes it much more difficult to synthesize the crystals. Still, it is a system showing the highest TC. So these really bad metals, these systems where you really have to dope a lot before you get some reasonable conductivity, these systems show TCs up to 60 Kelvin. Much higher than that what you find in all the others, in lithium iron arsenide or in 122 and all the other systems which we are used to study. So it's an interesting system because it is a real high TC compound here, but this high TC emerges out of these very bad metallic states. If we are close to a localized state where the d electrons are not mobile anymore, of course, it's worth having a closer look on the electronic configuration in these local energy scales. And then you see this iron atom embedded within this arsenic tetrahedra. And this means you have also orbital degrees of freedom which play a role. So you have a crystal field splitting. If you then plug in these 6 electrons, you end up with these degenerate XZ and YZ orbitals. Okay, and this of course plays a crucial role. So you have this degeneracy of the orbitals. Okay, in a metallic system, it's our bands which are degenerated, but this of course is a source of a strong coupling to the lattice. And this is also well known. We have this phase transition going ahead, which you already saw in the resistivity before. We have a structural phase transition from tetragonal to orthorhombic, which lifts this degeneracy. And it's already argued a lot that these orbital degrees of freedom play a crucial role when discussing this so-called nematic instability in these iron-based superconductors. And in these 1111 type systems, in contrast to other systems, these structure phase transition, or this nematic phase transition, if you would like to call it like that, or this orbital order, if you want to call it like that, is well separated from the magnetic one, which occurs 15 Kelvin lower temperatures. That's already seen in the very early work which we did on powder crystals. Okay, so that's the starting situation. So we have these orbital degrees of freedom, we have these nearly localized states, very bad metallic states, and of course we have magnetism in the game in these systems. And the phase diagram which we also know for these. So for, again, fluorine doped 1111 type systems looks like that. So there's a revised version. We have synthesized a new series of polycrystalline materials recently, studied that mainly with NMR and with many other techniques. So you have the magnetic transition, which is rapidly decreasing here. You have this nematic transition, which is also decreasing. They are well separated. Separation becomes larger. Signatures of this nematic transition disappear in thermodynamics, disappear also in local probes. And then you have a superconducting dome here, which emerges out of the system. It's quite interesting to see that we really have an underdoped region here where we have no magnetic order and TC increases upon doping. And then we have the optimally doping here. So that's, again, it's a different phase diagram than that what we are used to for the other iron-based superconductors. I should also mention that we rechecked old data. So we took an NQR probe. So we go to the literature, look for all publications where NQR were measured, where measurements are shown. We rescaled all these data on these NQR lines. I can explain in more detail if you want, but message is that these phase diagrams also on old samples now fall on a single line. So we are quite convinced that this phase diagram is really correct. So it's polycrystalline material, because the main problem with these 1111 types crystals, because we are not dealing with intermetallics, the main problem is to get nice single crystals where you can do reliable and sophisticated experimental studies. And at least for these parent compounds, we had a breakthrough, and that is a couple of years ago. That is Ria Kappenberger doing a PhD. She found a way to synthesize these really very nice and large single crystals, and that's a very unusual way. It's based on abnormal crystal growth. It's connected to polycrystalline material synthesis, and then you have to do very special thermal treatments, very special alignment of materials, and everything is described in detail in this Journal of Crystal Growth article. And then you finally end up with this very nice, faceted, nice, large single crystals of this lanthanum oxygen iron arsenide. And that's the starting point of this initial initiative of us to revisit this system. Still, the challenge is that doping with fluorine is extremely difficult, and we are still working on that. There are some first progresses, so replacing oxygen by fluorine in this process, but the control for that we still do not have. What is more easy to do is to replace iron by cobalt. So then we can use the same process. We can produce single crystals now. The cobalt concentration which we found in the crystals corresponds very well to the nominal cobalt concentration, which we use to synthesize the crystals. So that's shown on this line. So we have now a series of samples as a function of doping. We, of course, know that this is, let's say, not the best superconductivity or best superconductors to which we expect, because on the one hand, cobalt doping is electron doping. We know that, of course, because cobalt has one d electron more than iron. On the other hand, it's an impurity, and I've shown you already how sensitive these unusual bad metals react on impurities. So therefore, we expect that superconductivity will be very bad in these systems. And that's also what we find at the end. So of course, what we can do now is we can use more sophisticated experimental techniques to study the phase diagram. And some results are published in this paper, for example, measurements of the thermal expansion, where we use a dialatometry to study both these structural phase transition, so that means the cinematic phase transition, and the magnetic transition. You can even see in the lattice. So you're just measuring the size of the crystal. You can also measure the magnetic phase transition, and you can follow that as a function of doping, and you can derive a phase diagram which looks like this. And as expected, superconductivity is lousy in these systems, strongly suppressed when you compare it to the fluorine doping, but this is just the effect of the impurities, which we expect. On the other hand, the phase diagram looks very similar. We have a magnetic phase transition, we have these structural or pneumatic phase transition, and then we have a superconducting dome. Okay, that's the phase diagram which we find, and we find it from various techniques, also from NMR and published now in these recent papers. That's not the end of the story, I should emphasize. So we are still working on that. We are still working on improving the single crystals. So we have now a series of, the next step is a series of samarium 1111 type compounds, where we again started the cobalt doping. There's an entire series of samples that exist. We have now better superconducting properties here, because samarium also in the fluorine dope compounds leads to higher TC. And this is work in progress. And I will tell more on that in the next years, hopefully. And in addition, we also have first steps towards fluorine dope crystals. Okay, that's work in progress. Now let's have a look on this aspect which I would like to emphasize today, and that's this pneumatic susceptibility. So having these single crystals now we can follow this approach, which has been pioneered by Ian Fisher a decade ago on these 1 to 2 compounds, where he used piezo elements to apply a tiny strain of the sample and measure simultaneously the resistivity. And you can do that in different configurations as shown here. So you can probe different modes, and there you can really address in particular this nematic instability, or this nematic susceptibility as people call it. So if you then measure the resistivity as a function of these tiny strains, so look at the numbers, it's 10 to the minus 4 strain only, then you see the strong increase of the, or strong change of the resistivity as a function of this strain. If you plot the slope of these lines here as a function of temperature, you derive this divergence of the nematic susceptibility defined as change of resistivity divided by strain. Okay, fine. No surprise. So we are approaching this nematic instability. You can fit this with this typical Curie-Weiss law, and that's shown here that this is not so bad. So 1 over this nematic susceptibility follows a straight line, and this shows you just how good this fit is. So parent compound, no surprise, divergence at the phase transition. So such experiments you can now do on the entire series of crystals, and that's shown here. So you start from the underdoped compounds where you still see this phase transitions here. You go to optimal doped compounds and overdoped compounds. In all of these systems, in the entire phase diagram now, we see that the resistivity strongly depends on this on tiny strain. So the nematic susceptibility and nematic instability is relevant in the entire phase diagram of these systems. What you can do as next is you can have a look on these characteristic temperatures which you derive from these Curie-Weiss fits. Now you see here this divergence is close to this phase transition, to the structural phase transition. But what you also see is when you just follow these straight lines here, that these characteristic temperature, which you get from these fits, changes, becomes smaller, even changes sign, and then it becomes negative. So if you plot these Curie-Weiss temperatures from this fit, you clearly see this straight line upon doping, and you see that I do not see anything. You see that it crosses 0 close to optimal doping. And these are just these 2 examples: optimally doped compound where you're close to 0, overdoped compounds where it's negative. But so, and then of course it's straightforward to compare this to the superconductivity, to this behavior of the structural phase transition. In some sense, we lose our signatures of the real phase transition. There is no long-range phase transition when we measure specific heat, thermal expansion, or NMR. But if we take this characteristic temperature from this nematic susceptibility, we can follow this line down to 6%, and we see crossing 0 just at the 6%. In some sense, if you take this Curie-Weiss fit as a signature of, let's say, this characteristic energy, we have something like a quantum critical point connected to this nematic susceptibility, which occurs close to the 6%. So this, of course, relies somehow on fitting of the data, but you can also have a simple look on the data itself. So just maybe go back. So just looking at the numbers. So these numbers, this nematic susceptibility means the derivative of the resistivity versus the strain, which is much, much larger here than it is for the overdoped compound. So it's not only these characteristic temperatures which you get here, but also the absolute value of this nematic susceptibility, which changes in a very systematic fashion as a function of doping. And this is just a color plot of this nematic susceptibility for all these crystals which we have here. And it's apparent that you have 2 critical regions here. One is located close to about 4%, and one is located close to about 6%. So there are 2 concentrations where this nematic susceptibility diverges. And both are connected to peculiar points in the phase diagram. One is connected to the transition to the quantum critical point, if you want, or the transition where the composition where the magnetic order disappears. So in some sense here you see that these nematic degrees of freedom are coupled to magnetism. And that's of course clear if you go back to my initial paper, pictures on these orbitals. We know that orbital order and magnetism strongly comes together. There's a lot of theory arguing that indeed spin fluctuations are the driving force for this nematic instability in the iron-based superconductors. Here you see this coupling. But you see also that this is well separated from a second instability, and the second instability or the second enhancement of the nematic fluctuations comes along at a composition where we have superconductivity. So you could immediately, just looking at this color code, you would say, okay, just measuring the nematic susceptibility, you see the superconducting instability, superconducting dome here, just from a normal state property. And this strongly suggests that indeed these nematic fluctuations might be connected also to the superconductivity or superconducting pair mechanism. Yeah. Okay, you can compare this behavior with these two domes to the situation, for example, in this 1-2 compounds where we did the same experiments and others did this as well. And you see there's a completely different phase diagram here where magnetism disappears. You have this enhancement of the fluctuations here occurring at the same doping where this quantum critical point for magnetism occurs. And that's really different. So you can clearly separate that. And this, of course, points to this peculiar role for the nematic fluctuations. It's peculiar for superconductivity, but I would say it's also crucial to understand very unusual normal state properties which we have in these materials. And this brings me to the second part of my talk, and this is dealing with the strain-dependent thermoelectric properties. So you can measure not only resistivity under strain, you can also measure more complicated transport properties under strain. And this, what we developed here is a technique to measure thermoelectric coefficients as a function of strain. So again, starting point is this piezo stack. We take the single crystals, put it on top of that. Now we apply a thermal gradient. So we have a heater here. So we apply a temperature gradient here. Using a thermocouple, then we can measure the temperature gradient, which we obtain by the heater. That's one ingredient. And using these contacts, we can measure the thermal power or Seebeck effect. And if you apply an additionally a magnetic field perpendicular to this stack and measure the transversal voltage, we can also measure the Nernst effect. And this we did also for these samples. Again, the strain, the maximal strain which we can apply here is very, very small. It's below 0.1%. Nevertheless, we can measure changes of the thermal power, and that's just shown here. That's a typical experiment. What we do here. So we switch on heater, get a temperature gradient. Then we switch on this piezo, apply a strain. From this temperature gradient, we get a voltage here. This is the Seebeck voltage. If we change the strain, which we get an additional change of the thermal power gradient, we switch off the piezo. It make it a little bit negative. You see this change of the thermal power again, then switch off the heater. And you can do that at different temperatures. And here you already see a nice thing. So thermal power itself changes sign when you change temperature. The effect of the strain does not. It has the same. And the same thing you can do with a more complicated measurement, the Nernst signal. Here you even have to measure at different field orientations, minus and plus 14 Tesla. And again, you see directly in the raw data, you see the substantial change of these Nernst or Seebeck signals when you apply this tiny strain. And then you plot again this change of the thermal power as a function of this strain, so 10 to the minus 4. And then you see this straight lines here. And from these straight lines, you can derive again something like nematic susceptibility, now based on more complicated transport properties which are not measuring scattering anymore. They measure in detail Fermi surface, for example. Our Nernst effect is even more complicated. The main message here is, and that's really a take-home message in some sense, that these systems are so sensitive on tiny changes of the lattice constant, if you want, tiny changes of strain, that really the whole electronic system reacts. That's really far away from a conventional metal again. So we really have a system where we have very, very strong coupling between lattice degrees of freedom and electronic degrees of freedom. And that's not mediated by magnetism. That's what we saw in the last time. So we can play our games now. We can plot now these derivative strain thermal power versus strain as a function of temperature. It's not a big surprise that we again see something like a Curie-Weiss behavior again for the parent compound, but there are already surprises. So if you look here at the absolute value of the thermal power, as already shown you from the raw data, the absolute value of the thermal power changes sign. And that's due to the fact that we are dealing with a compensated system. So we have hole and electron-like charge carriers which are of the same number. That's at least in the parent compound. So the absolute value of thermal power changes sign, the derivative does not. And this already tells you, and that's maybe also some, let's say, some question to theory. This already suggests that these nematic fluctuations are band selective. Apparently, they do not act in the same way on the negative and positive parts, or the parts leading to negative and positive thermal power. That really looks a little bit that they all mainly act on the electronic bands. So we have this increase. You can, again, do the same story as a function of doping. In these 3.5% doped systems, we have then a negative thermal power. So we have added electrons. So we have electron bands. So the sign is the same, but the size is different. You see, again, just here looking here at the absolute value, it's becoming smaller. If you go for the resistivity, the absolute value becomes larger when you add doping. So you already see, we really measure something different here. So the concentration dependence is different from that, from the kinematic susceptibility derived from the resistivity. Okay. We also did such experiments meanwhile on other 1 to 2 compounds, barium 1 to 2. You also see this increase of this change of the thermal power as a function of temperature. And it's remarkable that these intermetallic compounds, which is so much different from these crazy oxide or oxo iron oxides, lanthanum oxide, iron arsenide, still has similar size of these derivatives. That also might be a message that we can really measure something which is rather generic for these systems. We will see. So strain-dependent transport, can we go beyond Curie-Weiss analysis? And we did first stand. I will not go in details here on all these concentration dependence, but just mention that that in principle, we can learn a little bit more, and it's straightforward to do that. So in principle, the Seebeck effect can be written in the form that it's a product of a so-called Peltier tensor times resistivity in this way. And then this Peltier tensor is the energy derivative of the conductivity. And this energy derivative means that you're really very, very sensitive to details of the Fermi surface, of the density of states of Fermi surface. What's well known is if you have a peak of the density of states of the Fermi surface, the Seebeck effect becomes very large. And a similar formula can be written up for the Nernst effect. And if you now have a strain, you can then argue that, of course, you have two components for this Seebeck effect. A component which is strain derivative related to this Peltier effect, to strain effect related to the Fermi surface, if you want, similar languages or simple languages, and a strain derivative which comes from this resistivity part. So this is what we measure by measuring the strain derivative of the resistivity. And the message is both are of similar size. Sign is sign depends on the Fermi surface part for this guy here, but both are of similar size. So you really have an additional quantity here besides the nematic susceptibility which we are used to from the resistivity. And this is also, of course, the reason why we have these different concentration dependencies. You can go a step further and can take these measurements of resistivity, measurements of Seebeck effect, and can calculate the strain derivative of the Nernst effect according to this formula. So that's all measured quantities. And all these measured quantities are give this yarrow curve here, and then you can measure directly the strain derivative of the Nernst effect, and then you see a one-to-one correspondence. And that's a surprise. It never works if you do it with pure compound. Again, telling you that these strain derivatives is really a very important aspect. That's really the most important aspect for these electronic properties of these 1111 type. And let's say the take-home message for these first two parts, that we have now the single crystals available. We are still working on having better systems. The hope is that we at some point will get really nice single crystals also for the systems which have the highest CC in these iron-based superconductors, about 60 Kelvin. But what we know meanwhile already is that we can clearly separate the magnetic instability and the superconducting instability with respect to their coupling to the nematic fluctuations. Both are coupled to the nematic fluctuations. We have a strong coupling between the electronic degrees of freedom and these strain derivatives. And I personally believe that this is mediated by orbitals. So this is 1111 type compounds. I will take the remaining time, still have a couple of minutes, to switch gears to completely different compound, and this will make clear that these iron-based superconductors are very, very different in their respective. And this lithium iron arsenide is very different. In the parent compound is already a superconductor. There is no structural phase transition, so no evidence for long-range nematic order, no evidence for long-range orbital order. There is no magnetic transition found so far in these systems. And still it's a nice superconductor. It's a very nice system for surface science. You can measure the superconducting gap with extremely high precision using photoemission, and this has been done by us, but many other people as well. You can also do very nice SDM measurements in these systems. Okay, and there is a surprise. If you do a very detailed analysis of the superconducting state or the superconducting gap as a function of the position in K-space and plot this, and this is for the big pocket here for one of these, let's say, the part of the Fermi surface in this system, plotted as a function of this direction, you see this line, and this apparently has two-fold symmetry. It's not a tetraagonal symmetry. It's only a C2. This looks a little bit like a broken C4 symmetry, as we, of course, used it in the systems where we have the nematic phase transition. Okay, that was first reported in this paper. We did also analysis of the Fermi surface, and also if you measure the size of the Fermi surface in the same experiment along X, and Y, you see a clear difference, which is of the order of about a couple of percent. A big surprise. We did more measurements meanwhile. We repeated the measurements with the same equipment. We also used a completely new type of detector, the so-called FESUMA Fermi surface mapper, which is a very great method to do a simultaneously mapping of the Fermi surface with one shot. We used a laser source. We used also a synchrotron source here. Details are described in this very recent publication. And we also, using this equipment, we also can follow now the changes as a function of temperature in detail. This is just a Fermi surface. And now we're using a laser. We are close to the gamma point. We are measuring just the size here of this small pocket here of the Fermi surface, above TC, below TC, difference, and difference again clearly has a C2 symmetry. And again, we can now see this difference between which emerges now as a function of temperature. So that's just a situation where you clearly see this leading edge gap, and then we see this emergence of this difference, emergence of nematicity in the superconducting state as a function of temperature. Okay, and that's again a big surprise, and I have to admit we do not really understand what's going on here. No? So we can mimic this thing. We found this now in for all parts of the Fermi surface. We found it for the electron parts of the Fermi surface. We found it for the big hole pocket. We found it also for the small hole pocket. And I think from experiment, We did all what we can do to prove it, to reproduce it, to use different techniques to show that it's really there. There is also some kind of theoretical description, which was put forward by Andrei Shubakov in this paper here, where superconductivities, different superconducting components play a role to induce this nematicity. But of course, I think there's also question marks, for example, domains and something like that. Why don't we see any twinning here and so on? There's a lot of things which we really cannot answer. So what we wanted to do now, and what we did in the last month, was to look whether this nematic instability of the superconductivity, is it also showing up in these usual nematic susceptibilities? And here I will rush a little bit through the data. So what we also did is now measurements of the nematic susceptibility by doing this resistivity measurements as a function of strain. And the message here is, if you do that, there's nothing. There is no indication of nematic instability if you measure the resistivity as a function of strain. Here, these are some, then we add some impurities here, some vanadium, so some hole doping, some electron doping, and you still, everything remains small, no strain dependence of the resistivity. Just for comparison, the other very similar system, structurally very similar system, you really see this nematic instability here, and there's basically nothing in the lithium iron arsenide. So a puzzle. So we see the nematic whatever in the superconducting state from APES, but in the normal state, at least, we do not see anything. Then normal state, so let's just send the same data is described in this recent paper. The next thing which we tried was NMR. So we can also probe this nematic instability or the change of the orbital degrees of freedom, let's call it like that, charge distribution, by applying a strain and then measuring the electrical field gradient. That works very nicely in 1 to 2 compounds, where you can follow these, you can derive the nematic susceptibility also from, let's say, from this local probe. Also, you can do it in the superconducting state. So we try to do the same, or did the same experiment, and again, in lithium iron arsenide, try to see any indication of orbital degrees of freedom, of changing of electrical field gradients as a function of strain. And now we can really have a huge strain, which we apply here, and there's nothing. No evidence for increase of nematic susceptibility at low T. That's just the message. And even worse, then we did a further very tricky experiment. We use this dilatometry, looking for anomalies at the superconducting transition, which occurs here at 17 Kelvin. And this is basically noise, what you see here. It's very small signal here. And again, at the superconducting transition, there is no change of the lattice, no change of nematicity, visible at least if you measure the lattice constant. And just for comparison, if you do the same experiments, even in the strongly overdoped compounds here, far away from any phase transitions, you still see this very nice phase transition, and then you can replace it. You can show that it's just this nematic instability, which you show here. But this is not the case in this lithium iron. So there's no evidence for lattice distortion due to nematic order. And of course, then there was the idea that it's not a superconductor at all. So we measured them in the magnetic field. And indeed, in the magnetic field, we find huge anomalies and even some evidence for nematicity occurring. And this is the next puzzle which we are facing here for this lithium iron arsenide. Whether this is, we have measurements are in progress, whether this is connected to APES, we still have to settle. But that's, let's say, the first indication that we really have something also from macroscopic. But this already brings me to the end of the story. So just a summary. The first 2 parts I discussed this 1111 type systems. There, the main step which we have now is that we are able now to produce series of single crystals. For the first time, we can do sophisticated measurements. And the main message here for you is that we can clearly separate magnetic and nematic fluctuations, and we can clearly show that the electronic properties of these systems strongly couple to these strain dependencies, strongly coupled to the nematic instability, strongly coupled to the orbital degrees of freedom. And you can see that from the superconducting dome, and you can see that from all kinds of normal state properties which we measure. And there's clear that's not many of these instabilities, many of the bad metal behavior which we have there is not coming from magnetism, but it's instead coming from these other degrees of freedom. And then I flashed recent results on lithium iron arsenide, where we have this very surprising observation that we have a breaking of C4 symmetry if you measure photoemission in the superconducting state. So emergent, it looks like emergent nematicity in the superconducting state, again, pointing to coupling between superconductivity and nematicity, similar as we have discussed it in the other systems. However, all our usual probes do not show the same kind of coupling between electrons and strain, which we are used to for the other systems. And that remains a question mark how to combine these two observations here in the systems. And the magnetic field may indicate that there is something, but there we are currently working on it. So that brings me to my end. Again, thanks to all the people who contributed, and thanks to you for listening.
Okay, Bernd, thank you very much for your beautiful presentation. And questions? Please.
Thank you, very nice presentation. Concerning your studies on the lithium iron arsenide and the Fermi surface deformation crossing TC, you use basically deep UV laser, I assume. What would be the pulse duration that you use?
So I think the first thing is for the first studies we use synchrotron mainly, no? And for the laser polarization, I know that Sergey did many experience on that for different polarizations. So I think that was not dependent on the polarization what we are shown there. So we see it for different things.
Yeah, no, I was saying the pulse duration, the pulse width.
The pulse duration. No, that was a
pulse,
CV laser. CV laser is first.
The pulse time duration.
Yeah, I think it was a continuous wave mode, as far as I know. Don't kill me. So please have a look on the paper. It's written there. Yeah.
Okay,
so
because if it's not a very short pulse, you have a mixture of mechanisms interacting, which are thermal and electronic. That's why.
Yeah.
Thank you.
Yeah. Okay. I agree. So, but you know, this is just an additional experiment. So we did the main experiments we did on the synchrotron, not using the laser. We just used this additional equipment which we have available here now to recheck the things. So it remains a miracle. So we have this two symmetry, and now we have it for many different configurations, and it seems to be very stable. I think that's the message which I can give you.
Okay, thank you. One last question, if any. Well, if not, let's thank Bernd again, and we have.
Thank you very much for listening.
Certificate for you as well.
And bye-bye.
And let's thank all the speakers of plenary session now. And Bernd, thank you very much. And well, the session is closed. The next one is at 10. high-temperature superconducting twisted Wonderwalls heterostructures.
Yeah.
Nicola, please.
I changed a little bit the title, but yes, basically, yes, it's that. So, thank you. Thank you for the organizers and the chairman to give me the possibility to give this talk. And so this is the outline of the talk, and I will talk about, first of all, an example of pair-time symmetry breaking, the dynamic mode transitions, and can we expect theoretically parity time or time-broken symmetry states from a twisted cuprate heterostructures? Why these twisted cuprate heterostructures are so difficult to make? The problem of the oxygen, and measuring the Josephson coupling between twisted cuprate heterostructure. I will show some data in experiments. Then with the detection of the second harmonic modulation in the Josephson effect at very high temperature and specific angle in these devices. And further work also is in progress to the topological state in those systems. And also some recent results towards the integration of hybrid superconducting and thermal circuit with the exotic mechanical and electronic properties of twisted cuprate heterostructures. So I would like to thank, first of all, my group, and Christian Sangao, Tommaso Confalone, Miki Martini, Sanas Shokri, Yejin Lee from the FW Dresden, and also from visiting PhD student from the University of Napoli, Giuseppe Serpico, and Aulin from the Max Planck Institute. And also the collaborators, Cornelius Nisch, Valer Vinocourt, and Domenico Montemurro, Francesco Tafuri, Valentina Brosco, Uri Vol, Gendagu, of course, that provides the crystal that we are going to use, Kenji Watanabe, Takashi Taniguchi, Philip Kim, and Pavel Volkov. And also some special thanks for people and technicians that helped me on this way. So now, even if you use a single superconductor, like a conventional niobium structure, depending on how you realize the architecture, you can get very exotic state. So the architecture is fundamental in geometry. In this case, what you see is 90,000 Josephson junctions are organized in a square lattice of proximity superconducting island on top of a gold substrate. What happens if you apply a magnetic field perpendicular to this kind of a system architecture is that you will form a Josephson vortex that you see on the right. A Josephson vortex which will start to move in one direction across the islands. Now, of course, this is happens that when you move the system to an equilibrium state, so you can think about this Josephson vortex to some extent also like atoms in an ultra-cold atom optical lattice. So if you apply a current, then what you will see is that this system goes in an unequilibrium state. And depending on the current that you apply and the magnetic field that you apply, you can basically move the system from a vortex mode insulating state. There you see the differential resistance and the filling factor on the x-axis, which tells you basically how many Josephson vortices in which kind of crystallographic configuration are organized in your superconducting array. So you will have, in this case, with one Josephson vortex for each plaquette of superconducting islands. Then you can move the system from a non-equilibrium state, that is the vortex mode insulator, to another non-equilibrium state, which is the vortex metal, or responsive metallic of the vortex lattice. And you can do the scaling, and what you discover is that you are basically in the liquid-gas transition universality class, or in the mode class at finite temperature. And then if you you can also describe the dynamic mode transition as a parity time symmetry breaking phase transition, with the mode insulating state corresponding to a regime of Hamburgian parity symmetry with a real energy spectrum. So this experiment has been reproduced also in different configuration, and in this case is a triangular superconducting island proximity array. And the results are similar. So the dynamic vortex mode transition has been observed in multiple configurations. Now, we know so that the architecture is very important and can determine novel phenomena even if you play with the same material. So it is known from a long time that cuprates, and especially the BISCO, as we have this morning, they have, by spectroscopy, thermodynamics, scanning tunneling microscopy, the wave gaps. And the wave order parameters, scusate. So it is not so known, and people have proposed and have thought for a very long time, how to exploit these nodal properties of this material to create interesting system. Now, one aspect that has been considered in the past is that there is a proposed inhibition of node-to-node quasi-particle tunneling at finite twist angle along the vertical c-axis of the junction. And this can lead to interesting macroscopic phenomena, quantum tunneling phenomena. Also, more recently, there has been some theoretical work, I also was in some of them involved, where basically, if you study the quantum coherent tunneling, you could propose that on the vertical axis of this Johnson junction, around some specific magic angle, you can have the mixing of these two order parameter, of this nodal order parameter, so that you get an imaginary component. And so, at some specific angle or in some range of angle, and this is very difficult to quantify specifically for theory because DFT calculation requires some parameters that are also uncertain in experiments, then it happens that basically you could expect to have time-broken states in those systems. And not only, you can also realize spontaneously time-broken states or dynamic time-broken states, depending at which angle you are. So this means, for example, that if you have a nodal gap, you apply a current across your Johnson junction, and then you basically deplete the nodal gap, and you open, you open a gap. Okay, so then the system completely changes. And these are dynamic state and spontaneously broken state are also what I'm going to discuss. First of all, realizing cuprates nano devices is difficult. It's really difficult. And has been for 30 years people trying to realize C-axis Johnson junction. Now, what is the big deal? So first of all, in plane Johnson junction has been realized. D-wave superconducting order parameter have been measured. And these junctions add Cooper pairs with a coherence length of 2 nanometer about. So you could be a little bit forgiven if you have some sort of disorder or meandering at the interface. But if you speak about the C-axis Johnson junction, which had all the interesting properties I'm speaking about, and people have for long tried to realize, then you have a coherence length of 0.1 nanometer, which means that basically for realizing devices, microscopic devices, you need to have angstrom precision. And now people have realized vertical junction using BISCO, for example, bulky crystal in the 1999, whisker junctions, and so on, and even recently thin flake. All these methods showed an approximate no angular dependence except of the critical current density, except for the case of the whisker, where however the cosine dependence that you expect from D wave was not very evident. All these methods showed that the junction, when they are realized, they are basically insulating. But what they do is to restore the superconductivity by introducing oxygens at very, very high temperature. So they have these kind of things in common. However, we know that cuprate material are very sensitive to millielectron-volt energy range and are very sensitive to oxygens. Cuprate, some of them, especially for example, some of them, like there are like lanthanum copper oxide, many others, but so they're oxygen ion conductor, so the oxygen are thermally mobile. And also, there has been measurement and experiment and theories that says that basically the topology, if you want to call like that, or at least the ordering of this case space, the case space ordering a real space of the oxygen in a material is very important for the property of your material itself. Last, the oxygen interstitial is one of the most vagabond of the elements that you can imagine on the periodic table, like hydrogen. And although it's recognized for the functionality of many complex materials, it's very difficult to control. For example, X-ray space mapping, like you see in this picture on the left, show how the case space ordering of this oxygen interstitial in lanthanum copper oxide vary across a space of several microns. So the oxygen R-case space orders are strongly correlated with the high temperature superconducting properties of this system. And you can also start to control this X-ray, this oxygen ordering if you put yourself close to the temperature when the oxygen starts to be mobile, which is 200 Kelvin. Then you apply X-ray flux, as you can see on the rear, and then you see this case space wave vector related to the oxygen ordering increasing in diffraction. And then if you quench, depending on which stage of the order you are, the system at low temperature, you will see different TC and increasing with the case space ordering of the oxygen interstitial. So you can control. So now BIBISCO itself, so this is just to show how sensitive the system are to oxygen, how much important it is to understand deeply what the oxygen are doing. And so the BIBISCO generally, as shown by Novoselov and others, can be stamped with a Scotch tape on a substrate and on thin limit, on two-dimensional atomic crystal, by breaking the bismuth oxide bonds. The problem is that when you do that, the oxygen basically boils in the system, and the system becomes insulating. More recently, we have done some work in two different groups. I've shown that you can isolate the high temperature superconducting atomically thin BIBISCO down to very, very thin crystals. And this shows that you can retain the maximum critical temperature for the case of bismuth 2212 of 90 Kelvin down to the very thin limit. Now, there are something that you have to preserve when you do that. First of all, it's very remarkable. This is an X-ray mapping done with a 50 nanometer beam on top of a very thin BIBISCO crystal. And you see the superconducting transition temperature. And on this right corner, you see a plot, an histogram, and you see that the variation, the sigma of the case space order of the superlattice modulation, when you are in the very thin limit, varies only of 0.002. So this means that when you go to the very thin limit, the incommensurate modulation that we have heard before is really stable, is there, and doesn't change at all, or change very marginally. Now, so then we needed to develop new method to transfer this material, because the oxygen RK configuration, we know that must be frozen below 200 Kelvin, because above the oxygen are mobile, in order to preserve the ordering. And as well, we needed to preserve the lattice, like the incommensurate lattice modulation, from interaction with any sort of water molecule. Because in any possible situation, even if you are at high vacuum, you will have water molecule that will come and diffuse on top of your surface. We are talking about here about surface science, okay? So we developed some methods. So it turned out also by a matter of luck, actually I would say, that if you lower the temperature very much in an inert atmosphere, the PDMS becomes has a glass transition close to minus 123 Celsius. Now, most of the people that work on 2D materials, they generally realize the transfer and the stacking of graphene, TMDCs, and all the possible field that you can imagine in 2D materials is done with PPC, NPC polymers, which forms a liquid when they cross the glass transition, and then by freezing again, so this liquid encapsulates your crystal, and when you lower the temperature again, it freezes, and then you have enough force to tear apart your graphite in graphene flake, and so on and so forth. But if you do that with the BISCO, you will devastate your system, without mentioning that for doing this method, you have to use solvent, and solvent contains waters, so you are going to devastate twice your system. So you really cannot do anything of this. So we know the oxygen are mobile before below -70 degrees Celsius, so it turns out that if you exfoliate the BISCO flake, use the PDMS, and the PDMS goes very close to its glass transition temperature without overcoming it, it becomes like a Scotch tape, really a Scotch tape. It becomes sticky like incredibly. Okay, sure. So then what you can do is to restack this system on top of each other and give a twist. This is impossible, okay. But so this is, so to understand how sensitive are these materials, you can see that if you have the interface exposed to the atmosphere and you use this method, then you, even though you see the same superconducting critical temperature, you will have very different Johnson characteristics. But if you encapsulate the system because you have a high vacuum evaporator, then you can protect the system from water molecules, and you can measure 1.2 kiloampere centimeter square as intrinsic Johnson characteristics. So I'm going a little bit fast. So you can realize this with different methods, with cryogenic transfer plus encapsulation in an evaporation at high vacuum, or with cryogenic transfer plus evaporation without encapsulation in ultra-high vacuum. You see, so then all the samples that we measured that are 30 more have superconducting transition around 90, strong hysteresis, and critical temperature that are, and critical current that are one of the intrinsic Johnson junction. If you look at the raw data, you can already see here in the dynamic resistances that there is some changing depending on, in this table, depending and where each plot is an angle. And now, if you look at the TM picture, you see the quality of the interface that we have realized of the supermodulation on top of the BISCO flake. These are atoms that you see, and where you see this modulation is basically where you have tear apart the crystal. And you see that the ICRN for different methods that we have used always show a D-wave dependence. And I very quickly finish because otherwise. So what happens is if you are at a specific angle around near 45 degrees, you can see very special state appearing like fractional Shapiro steps, so second harmonic modulation, so changing the current phase relationship. Also asymmetry in the Fraunhofer pattern and fast oscillation, as you can see here. Finally, in order to improve our method, now we are trying to go in a hybrid superconducting system, so we are developing another method to realize and in order to combine a very complex circuit. So for example, we can, sorry, I have to go fast because otherwise I don't finish. But, so we are working on this. Okay, so thank you very much. Yes.
Thank you very much, Nicola. Now, questions?
Technical question. You mentioned psi C, coherence length in the direction being 1 angstrom.
0.1 nanometer.
So yes,
yes.
So it's 1 angstrom.
See.
So how do you know that this is it's extremely short?
Well, in literature, most of the time people, there is a very strong, not from my data, I know, but in literature there are several methods that shows that, I mean, people have measured these properties.
Okay, thank you. Over there.
Do you know something about broken of particle Hall symmetry in D-wave superconductors and the possibilities to realize for example, like diet effects, different diet effects. Can you comment on that?
Sure. So we have some evidence that I'm not showing here because it would be too long. And we are still measuring where you may have this kind of effects in the system. But at the moment, I just want to point the fact that we have some special effect around some angle, and we are trying to basically understand from where they come from.
Okay, thank you. Well, unfortunately, we have to move on to the next. Sure. Thank you very much, Nicola, again.
Thank you.
Exchange. Thank you very much.
Thank you very much.
Alexei Mironov will be talking to us about the effect of impulse voltage on the superinsulating state.
Okay, I want to thank the organizers for inviting me on this beautiful conference. And today I want to continue speaking about superinsulator and about difference between superinsulator and usual insulator. And firstly, I want to say about what's mean superinsulator. Superinsulator, this is dual system to superconductor, but opposite it. Same as superconductor, superinsulator is non-dissipative system, but they have infinite resistance or their conductance. And this state was observed in many materials like titanium nitride, niobium titanium nitride, indium oxide.
Alexei, can you move your microphone up onto your shirt?
Okay.
Well, if you put it on your shirt, then it will not make so much noise.
Okay. Here is not. Maybe this is better. Okay. Now. Also, the state was observed in some artificial network which consists from capacitance and inductance with right parameter, but I will not speak about it. Okay, what we use? We use titanium niobium nitride films. Here is cross-section in high resolution electron microscopy, and here's niobium titanium nitride film. It's enough homogeneously. Wait. In plan view, you can see many crystallites with size around 5-6 nanometers. Thickness of our film around 8-10 nanometers, depends from sample. And what we see in resistance of this film. Okay, and here you can see temperature dependence of resistance for many samples with different thickness. But and you see here transition between superconducting and superinsulator states. For next experiments, we use only superinsulator films. And firstly, I want to say about this superinsulator states. If we will change in distance between contact, we will see that this superinsulator also changed. For example, Okay, in first picture in left upper, we see temperature dependence of resistance for 5 different distances between contact, and when distance is big, we see good insulator with temperature dependence stronger than activation, like as hyperactivation. But when we decreasing this distance between contact, our insulator destroying up to metal behavior with saturation. We can describe this behavior with Polyakov strings and monopoles, about which Carla speaking several days again. But I will not stop on it. Also, the strings effect on current voltage characteristics with fantastic homogeneous of electric field. And what we can do with this system. Here we see only behavior at DC current. This is not enough. Let's speak about high frequency behavior. Of course, we can firstly measure capacitance or inductance of our films, and this results was presented several years ago, and there was many problem with measurements because different techniques give us different results, and there we couldn't understand why. And now we want using impulse voltage and see what's happened with our system. First, unfortunately, doesn't work normally. Okay, then we will see only last picture. Okay, if we using square impulse of voltage, start impulse from 0 second, stop impulse at 50 microseconds. What we see, in first time, several microseconds, we didn't observe any current. And only after time, we see a jump of current to normal value which we measure in DC measurements. If we will increase in temperature, this behavior will disappear. Unfortunately, this work not very good, and I'm afraid you cannot see it. Animation was broken. Okay, and with increasing of temperature, we can transform our curve from superinsulating behavior to usual insulating behavior with exponential growth of current when we turn on voltage. Okay, let's see what's happened if we will change maximum of voltage in our system. You see here that with increasing of voltage, time between starting of impulse and starting of growth current is decreasing. And if we analyze this behavior, we can plot this picture. Here is time between starting impulse and starting growth current versus voltage shifted by several voltage, and in double logarithmic scale. In this scale, we see linear behavior of our dependence, but here is two different parts, which divided by VC2 voltage. At lowest voltage, we have behavior with 1/2 power. With voltage higher than VC2, it's changed to 3 divided 4. Why it's happened? There is a long theory. Firstly, we can say that at voltage below VC2, our string will be destroyed, and charges which this string consists moves to different side of our samples, and of course, when voltage is increasing, these charges move quickly, and time is decreasing. Then we should think about velocity of phase slips at voltage higher than VC2, but I hope in next maybe a conference, Carlo or Valery or Christina will talk about more carefully, and I will not speak about it. Okay. Let's speak about this value VC2 and this value Vpro. Let's compare it with threshold voltage for our superinsulator. And here you can see current voltage characteristics for 3 samples with different degree of disorder, and this arrow shows how changes voltage from 0 to maximum value, or from maximum value to 0, and you see here small hysteresis, and VC2 is really upper threshold voltage, and the probe have value less than any of our threshold voltage, and we think this value is comparable with VC1, which we usually cannot observe in our current voltage characteristics, because current there is very, very, very small. Why we observed it at high frequency? Because we have impulse voltage, okay, with short distance between them. If we will increasing time between impulse of voltage, then behavior in this area is disappear. For example, at time between voltage around 1 millisecond, we doesn't see anything in this area, but in this area we see usual behavior with same figure, no problem. Okay, and next slide. Showing what's happened with system if we change impulse, if our impulse of voltage not between 0 and maximum voltage, but between plus maximum to minus maximum. And we see here what's happened. When sign of our voltage is changed, sign of current also change. Value is smaller than than before changing sign, but after a small time, you can see that current is decreasing, reach minima, and only then again increasing and reach normal value which we observed at DC measurements. Why it's happened? Okay, if we again speak about strings, about monopoles, about charges, when we change sign of our voltage, we need firstly reverse our strings, and only then they will move and current is appear. Okay, as a result, we think that this decreasing of current, because we should reverse our charges from different side. And also we can construct similar pictures previously with dependence of this time versus voltage. And also we can find linear behavior in double logarithmic scale, similar from different samples, but theory for this is not here. And really that's all what I want say today, and thank you for your attention.
Well, thank you very much, Alexei. Other questions?
Can you make a broader comment on the formation of superinsulating state from microscopic perspective?
I don't know what's happened. Unfortunately, we haven't microscope with temperature below 100 milli-K. But in at room temperature, we didn't see any difference between superconductor and superinsulator.
Thank you.
Well, it depends, if I can make a comment, it depends on what do you mean by the microscopic picture, so to say.
We have a Cooper pairs in case of superconductor, right? We have formation of kind of Bose-Einstein condensate of quasi-bosons, right?
Yep.
That's behind superconductivity. And if we talk about superinsulator, so what's a kind of foundation, microscopic foundation of possible superinsulating state?
Okay, yeah, on this level, from the permission of the speaker, I can answer. If you like. Do I have a minute to reply?
Can you?
Okay, so basically let's call it microscopic picture is as follows. The systems in which we observe superinsulating state are the system which experience superconductor insulator transition. If you have such a system, as Carlo described in his talk, there is self-induced electronic granularity. So basically around superconductor insulator transition, the system looks like an array of superconducting droplets which are contained by Josephson links. Now, then you have two competing energies. One is Josephson coupling and another is Coulomb energy if you put additional charge on this superconducting droplet. Now, if Josephson energy wins, then you have a superconductor. If Coulomb blockade is stronger, you have insulator, but if you look at what happens in this insulating phase more attentively, you will find out that this phase is absolutely dual to superconductivity, in a sense that you can show that if you have the system experiencing superconductor insulated transition, there are monopoles which are generated in this system. And basically, super insulating system is exactly dual to superconductors in a sense that you have condensate of monopoles. And this condensate of monopoles squeezes the Coulomb interaction between charges in exactly the same way as Cooper pair condensate squeezes magnetic field into these filaments, which we call abricosal vortices. And when you squeeze this electric field into these electric strings, this phenomenon is very well known in quantum chromodynamics. This formation is called Polyakov strings, and exactly these Polyakov strings which prevent charges from moving. This is the phenomenon which is absolutely identical to what is very well known as quark confinement in hadrons. So you have this electric string which keeps charge and anti-charge together, and they cannot move until the string breaks, which happens at finite temperature. And therefore, in a finite temperature interval, you have the state with infinite resistance or zero conductance, mirror image of superconductivity. So this is the microscopic picture.
Thank you for a very excellent explanation. Thank you.
One question.
I would like to ask about expression for the calculation of conductivity in such systems. As I understand, you use a ballistic regime of calculation conductivity. What is the reason?
I can't say because I'm not a theorist.
I have a question for you. On your slide 10, could you go to your slide 10, please? Yeah, this one. So you fit your power law to several different, exponentials here, but each exponential is a rational number, and you typically only expect rational numbers coming up when you have a mean field theory. So I was just curious why you stuck to rational numbers rather than any number.
Really, theory predict 1/2 only for voltage between VC1 and VC2, and 4 it happens.
If I can also make a small comment on that from your, again, permission. Okay, basically what is shown with this 1/2 scaling, this is basically the first ever experimental observation of this Polyakov string. Because if you go to this like quantum chromodynamics papers, you will read like, okay, tons of like material explaining why it is impossible to exercise an experiment where you can see this quark motion. What is happening here in this small, okay, small voltages above the threshold is that basically you pull stronger the string, and since the potential is linear, then actually this is like, okay, 8th grade elementary mechanics calculation, which shows that it should be 1/2 just because of the linear tension of the string. And what concerns, okay, the reason that like, okay, other rational powers were chosen, that's because, okay, since you have this like, again, linear string tension, but okay, you apply, okay, higher force, there are some scaling considerations which are still hypothetical, but which produce exactly, okay, this kind of rational numbers, but this is a little bit premature to, like, need a little more work.
Thanks. We should thank our speaker and move on to the
Yes.
next speaker again.
Can you give from your beautiful hands?
Alexei?
Well, thank the speaker again. And now we go to our online talk. Our next speaker is Jose Vlada from Aalto University in Finland. Okay, she's here.
Yeah. Hi. Can you hear me
Yes,
well?
yeah, yes. It's like
Yes. Great. Wonderful.
yes.
So let me then
What
share my
please,
screen.
what
So now you see the presentation in full screen mode, right?
Yep.
Yeah, wonderful. Well, thank you so much for the wonderful introduction. And let me start by thanking Valerie for the wonderful opportunity of talking today here. And I would also like to apologize for not being able to be there in person, but it's really thrilling to be here in this session. So today I'd like to tell you about how we can create topological and nodal superconductors with van der Waals materials, and in particular, how we can drive materials that are in principle conventional superconductors to this more unconventional regime. And the story I'm going to tell you today is based on two experimental findings that the group of Peter Lidgerth at Aalto University had, and we provided the theoretical support. And of course, there was many people involved in this that I will tell you about. So the background for today's story is the van der Waals world, the world of two-dimensional materials in which, as you well know, we have many different types of orders. So we, of course, have some metals such as graphene, that it's the most well-known one, but we also have insulators, superconductors for electrics, semiconductors for magnets, quantum spin Hall insulators, multiferroics, and even quantum spin liquid candidates. And the most important idea of these materials is that besides the fundamental interest that each one of these materials has by itself, we can actually also create much more exotic forms of quantum matter by properly combining these materials. And this idea essentially relies on a relatively simple chemical fact of these materials, which are the weak van der Waals forces, which essentially tells us that we can take any two materials from the previous list, put them on top of another, and combine any electronic orders that we want. And in this way, we can combine conventional superconductors with ferromagnets, or with topological insulators, or with antiferromagnets, and so forth. And what is also very important in these materials is that we cannot only combine different electronic orders, but we can also twist the materials one with respect to each other. And this degree of freedom of twisting the two materials allows us to control what is the different coupling between the two materials, and most importantly, to engineer new electronic states that have a lattice scale associated to this Moiré superlattice. And just as a paradigmatic example of how this idea of combining two-dimensional materials and twisting the angles is very, very powerful, let me emphasize the case of twisted bilayer graphene, the simplest twisted van der Waals material in which we take two layers of graphene on top of another at a certain angle. And in this material, just depending on very teeny tiny details of your structure, such as the angle that you have or the bias that you apply between the two layers, you can realize a huge plethora of electronic orders. You can get superconductivity, topological networks, different types of topological insulators, correlated insulators, including multi-insulators or charge density waves, quasi-crystalline physics, and even fractional churn insulators. And all this appears just in a twisted bilayer graphene, which is the simplest van der Waals heterostructure. So if we now look at the previous list of van der Waals materials, and in particular we start focusing on superconducting-based van der Waals materials, we can imagine that we will have a huge degree of freedom that perhaps will allow us to see superconducting states that are very, very challenging to see in other compounds. And that is essentially the idea for the experiments that I would like to tell you today. So today I'm going to talk about two different sets of van der Waals materials. First, I'm going to tell you how we can create topological superconductivity in chromium bromide niobium diselenide, so in a heterostructure combining two different two-dimensional materials. And second, I would like to tell you how we can take a two-dimensional material that in principle is a conventional superconductor and drive it to the nodal superconducting regime by growing very specific samples. And before going to the physics part, let me emphasize that all the results I'm going to show you today wouldn't be possible without the amazing work of many people. And in particular, you see all the people that are responsible for the experimental work, that it's, of course, the most important part. In particular, Somesh, Mohammed, Marcus, Lin Hao, Williams, Shabulinu, Mohammed, and Peter Lider, that it's the leader of the atomic scale physics group at Aalto University. And of course, I would like to also thank once and Marian, two PhD students in my group that did the theory supporting these findings. So let me start with the first material. So naive diselenide on top of chromium bromide. And let me tell you how we can see topological superconductivity, and in particular, a topological superconductivity driven by the Moire pattern between the two materials. So as a starting point, let me remind you what is the idea of topological superconductivity. So if you think about a superconductor, you essentially have an electronic structure that has a gap that, and this gap appears because of the pairing between the different electrons. And we can, of course, have conventional gapped systems that are topologically trivial, namely that they have a gap in the bulk and at the surface. And we can also have topological superconductors that have a gap in the bulk, but that in the surface have gapless excitations, and in particular excitations that are topologically protected. And these excitations are what are usually called Majorana excitations. And of course, topological superconductors are really, really hard to find in nature. So in the last few years, there have been many, many different strategies to engineer topological superconductivity by combining different materials, including atomic chain semiconductors, different iron-based superconductors, heavy fermion superconductors can natively have topological superconductivity. They can also be engineered with topological insulators. And the story that I would like to tell you today, which is how they can be engineered with two-dimensional materials. So from the fundamental point of view, if we think about any recipe for engineering artificial topological superconductivity, the only thing that we need to know is the following. If you want to have a topological superconductor, you just have to combine two different ingredients. First, a S-wave superconductivity. This is the conventional superconducting order that can come from any conventional superconductor. And second, helical states. And these helical states can appear for many different reasons. They can come from a topological insulator. They can be artificially engineered by combining spin orbit coupling effects and the exchange couplings or magnetic fields and so forth. What is important is that if you combine these two ingredients on the right footing, you can essentially realize an artificial topological superconductor, essentially because these two ingredients give rise to the so-called Kitaev model. And all the previous recipes to engineer artificial topological superconductivity rely on, in one way or another, in this relatively simple idea. And this is exactly what is the basis for artificial topological superconductivity in this van der Waals heterostructure. So in particular here, we will have a monolayer of chromium bromide on top of naive diselenide. And the breakthrough finding that happened 2 years ago was the observation of topological superconductivity in this hybrid heterostructure, and in particular, topological superconductivity that was proved by a full gap in the bulk and gapless states on the surface. And here on the right, you see the spectroscopy at the surface. But now, two-dimensional materials can be misaligned, right? And that sample where they saw topological superconductivity certainly had a Moire pattern. So let me tell you a little bit what is the relevance of this Moire pattern. And for that, let me start with a very simple model, a one-dimensional system with a Moire pattern. And in this one-dimensional system, if we think about in which energy windows we can get topological superconductivity, in the absence of a Moire pattern, we can essentially get topological superconductivity at the very top of the band and at the very bottom of the band. And the reason for this is because in those two regions, we essentially have parabolic dispersion, and parabolic dispersion is something that we need to be able to get these helical states. Now, if you start thinking that you take that electronic structure and you add a Moire pattern, maybe by putting your one-dimensional system on top of another one-dimensional system that it's incommensurate, what will happen is that your bands will get folded and you will develop mini-bands. And in particular, these mini-bands will have new tops of band and new bottoms of mini-band. And this is actually the key point for understanding what is the role of Moire patterns in topological superconductivity. So if you now look at this folded band structure that has new mini bands driven by the Moire pattern, and you start thinking about in which parts of your band structure you can get topological superconductivity, what you have is that now you can get topological superconductivity in many other energy windows in your electronic structure. And in particular, you can get topological superconductivity every time that you have a miniband top or a miniband bottom. So if you compare in which regions you can get topological superconductivity without the moire with the regions in which you can get topological superconductivity with the moire, what you automatically see is that the moire pattern essentially increases by a lot the range of energy windows in which you can get topological superconductivity. So this idea alone tells you that moire patterns in two-dimensional materials are very likely to help you to get topological superconductivity because of this very simple idea. Now, let me show you how this is of relevance to the experiment. Here on the left, you see a topography of the chromium bromide niobium diselenide heterostructure. And what you very clearly see is that there's a moire pattern that arises due to the both different lattice constants between the two materials and also a relative twist angle. And in the following, I'm going to focus on telling you what is the spectroscopy in 3 different energy windows: inside the gap, and in the so-called Yusheva-Rusinov bands, which are essentially the bands that give rise to topological superconductivity. So now, if you think about the effective Hamiltonian for this system, the simplest thing that you can consider is that the moire pattern is essentially going to modulate the exchange coupling between the two materials, and in particular, is going to generate an exchange coupling with a profile that follows the moire pattern, which is essentially the picture that you see on the left. Now, if you go to the experiment and you look at the location of the Yusheva-Rusinov bands, so these bands that give rise to the topological superconducting state, what you actually see is that those states are perfectly following the moire pattern, and in particular, they follow the exchange profile that one would expect that it's going to exist between the two materials. And of course, that modulation of the Yusheva-Rusinov bands is something that one gets automatically in a theoretical calculation with that exchange profile. Now, the most interesting point is that one can see what is the impact of that modulation of the exchange profile in the edge states, in the topological edge states of this material. So here on the left, I'm showing you how the experimental DITB is for the Yusheva-Rusinov bands at an energy that is above the gap, so where you essentially see the bulk states, and what you see is that there's a profile that follows the moire pattern, so there's a small modulation, and of course you also see that in the theoretical calculation. And if you now go to energies inside the topological gap, so energies where you see the topological in-gap states, what you actually observe is that there's a modulation of the edge states that again follows the moire pattern, which is essentially what you see also in the theoretical calculation. So to sum up, in this chromium bromide niobium diselenide heterostructure, we see that the moire pattern clearly modulates the electronic structure, and we know from a theoretical point of view that moire patterns essentially allows us to get topological superconductivity, or at least increases much more the phase space in which we can get topological superconductivity. So in short, moire patterns in these materials can actually be a very powerful way to drive these systems towards the topological superconducting regime. Now, the second story that I would like to tell you is how we can get a different type of superconducting state in a slightly different material, now in another dichalcogenide material that is tantalum disulfide. So the idea for the second part of the talk is that we can have a different type of unconventional superconducting state, which is a nodal superconducting state, which is of course the well-known superconducting states in high TC superconductors and other types of correlated superconductors. And the basic idea is that if you compare the density of states of a fully gapped superconductor with a nodal superconductor, what you get is that in a fully gapped superconductor, you have a hard gap, so you have a U-shaped density of states, whereas in an unconventional superconductor, you have a V-shaped density of states. And we usually consider that V-shaped density of states are essentially driven by some unconventional pairing glues, such as magnons or plasmons or valence fluctuations, and so forth. From the point of view of two-dimensional materials, for a long time, it has been considered that two-dimensional dichalcogenides, such as niobium diselenide, tantalum disulfide, they were relatively, let's say, simple, conventional S-wave superconductors driven by electron phonon coupling. in the last few years, we realized that that is actually not the whole story. And in the last few years, there have been some very strong experimental signatures that two-dimensional dichalcogenides, especially when driven to the purely monolayer limit, are very close to being correlated superconductors. And in particular, they may show signatures of different types of unconventional superconductivity. And let me emphasize two of these cases. The first case is the case of tantalum disulfide, where some signatures of F-wave superconductivity were found almost 10 years ago. And the second one is a very recent experiment where in a monolayer niobium selenide, it was observed that legged modes appear close to this superconducting gap. And these two signatures are essentially a signature that the materials are close to being correlated superconductors. So in short, the take-home message of this part is the following. If you take tantalum disulfide and you create a monolayer that has some sort of disorder, the superconducting state that you will get is a fully gapped superconductor, whereas if you create an ultra-clean monolayer of tantalum disulfide, you get essentially a gapless nodal F-wave superconductor. And from the theory point of view, this is actually relatively simple to understand. And this comes just from the effect of disorder in unconventional superconductors. If you have an S-wave superconductor and you start increasing disorder, essentially you do not impact too much the superconducting gap. This is, of course, well known as Anderson's theorem. You have an unconventional superconductor, in particular an F-wave superconductor. As you increase the disorder, you essentially close the gap, and eventually you will kill the unconventional superconducting state. So unconventional superconductors are often very, very sensitive to disorder. And from the electronic structure point of view, essentially what we expect is that an S-wave superconductor is going to have a fully gapped electronic structure, whereas the F-wave superconducting state is going to have an electronic structure that has a gap in certain parts of the Brillouin zone and that it's gapless in other parts of the Brillouin zone. And from the point of view of the, let's say, Fermi surface, what we expect is that in the nodal superconducting state,
Jose,
even when we have
Jose,
superconductivity,
we need to take questions in 2 minutes.
All right, thanks for the note. In the nodal superconducting state, there are some parts of the Fermi surface that are going to remain gapless. All right, so now let me show you how the experimental spectroscopy looks like in these materials. In the dirty sample, we get a U-shaped density of states that we can very well fit with a conventional BCS formula for an S-wave superconductor. And if we now go to the ultra-clean limit, we get a V-shaped density of states that now we can very well fit with an F-wave superconducting order, and with a nodal superconducting order in particular. And what is even more interesting is that if we look at the ultra-clean sample at energy very close to the gap, we see that there are some inelastic excitations with a very well-defined, let's say, wavelength that we believe are a signature of the underlying pairing glue of this unconventional superconducting order. And let me emphasize that this is very similar to the pi-pi excitations in high-TC superconductors that are associated to the antiferromagnetic state. And the last signature of unconventional superconducting order is that if we take the ultra-clean sample and we apply very large magnetic fields, we essentially open a pseudo-gap in the electronic structure. So this is a pseudo-gap that gets enhanced by the magnetic field. That it's also very similar to the phenomenology in some correlated superconductors. So this is everything that I wanted to tell you today. So if I can ask you to remember something, please remember that Wonderwalls materials offer a platform to realize topological and nodal superconductivity. And with this, I'd like to thank you for your attention and look forward to your questions.
Do we have any questions from the audience?
Perhaps the reason why there is no question is that your results are really new. I propose that the shift from the single band Hubbard model to manipulating lattice symmetry and lattice geometries of standard superconductor. And this is really a fantastic result. My best wishes for your career.
Yeah, well, thank you so much for your very nice feedback.
So I will ask a question. What do we learn? I mean, okay, so we can do, your talk was a little bit quick, and so we can do topological and nodal superconductivity with Wonderwalls materials, but did we learn something new from your experiments?
So what we did learn is that two-dimensional superconductors that were usually considered to be conventional can be driven to the unconventional regime. And in particular, that we can use all these knobs of, let's say, using different magnetic substrates to drive conventional superconductors to unconventional regimes. And of course, what would be very interesting in the future is to try to get to superconducting regimes that we do not see in bulk compounds, which is, of course, some of the things that we are trying right now.
So what is your definition of unconventional superconductor?
So anything that is not S-wave. So that is, of course, one specific definition. There are, of course, others.
Okay, thank you for the very nice talk, and let's thank our speaker again.
Yeah, thanks a lot for the opportunity.
We come back at 11:30. There's a break now.
And then this is called academic community. Let the people sit down and to prepare comfortably, enjoy your talk. Okay, so let's start the continuation of our session, which is Topological Quantum Matter session. And our first speaker here is Erika Carlson from Purdue University. And the title is Critical Nematic Correlations Throughout the Doping Range in BISCO. Erika, please.
Thanks. Thanks for being here, and I'd like to thank the organizers for inviting me to this lovely conference. It's been very stimulating, lots of great ideas running around, and it's my first time in Turkey. It's absolutely lovely, so thank you for the invitation. My theory collaborators are Karin Dahmen at University of Illinois, as well as some of my PhD students. This is now Dr. Ben Philibam, and current students Forrest Simmons and Shuel Gu. Our experimental collaborators include Eric Hudson at Penn State and Jennifer Hoffman at Harvard University, as well as some of her group members, Conley Song and Liz Main. Our funders include the National Science Foundation, Department of Energy, Department of Education, Research Corporation, and actually Department of Defense I did not yet add. So the ways that we classify phases of matter, I mean, of course, you know, we heard a talk in the earlier session about how we have a zoo of phases. We have to figure out how to understand them. So we have a couple of big tools for this. One of our big tools is symmetry, and this is where we're looking at the symmetry of the phase and how the symmetry changes as you go from one phase to another. So that's a symmetry classification. One of the things we have to keep in mind is that the symmetry classification of phases of matter is a long distance and long time criterion. So for example, one of the differences between crystal and liquid would be their symmetries, and the crystal breaks not just the rotational symmetry of free space, but also the translational symmetry of free space. The liquid does not, but that's only on long time scales and on long length scales. If you observe the liquid on short time scales, it's very bumpy, right? And if you observe it on short length scales, it's very bumpy. It's only when you take, you know, say the time-lapse photography of this that it becomes smooth, and now it retains all the symmetries of free space. So the symmetry distinction includes implicitly long distance and long time criteria. Topology is another way that we categorize things, and these are simply objects with different topologies to them, different numbers of holes in them. And there's an implicit criterion in here as well of a long distance criterion, because you need some sort of edge or a boundary condition in order to define the topology. And so these, of course, have gotten us a lot of mileage. However, we're running up against things in quantum materials that challenge those paradigms. And the paradigms, well, we need new ways to think about phases of matter in systems that do this sort of thing. Now, we have many fascinating and a growing number of spatially resolved probes, and this has been excellent. And what they've shown us is a lot of pattern formation. So this is just a collection of examples of pattern formation happening to the electronic degrees of freedom in quantum materials. The two on the left are metal insulator transition materials. This is vanadium dioxide. This is neodymium nickelate. And the metal insulator patterns are being visualized using scanning near-field optical microscopy out of Dmitry Bazov's group. And so the different colors just tell you metal and insulator patches. And you can see there's a lot of intermediate scale structure here. And there's mesoscale structure that's missed by the definition of a phase of matter, whether it's by topology or whether it's by symmetry. The symmetry definition is blind to this because it's going to ask you about the long distance correlation properties. In the upper two panels, we have cuprate superconductors visualized by scanning tunneling microscopy. This is data out of Seamus Davis's group. This is data out of Jennifer Hoffman's group, and I'll show you the detailed analysis of this upper right one in this talk. And what's visualized here is stripe orientation. So the electrons make some sort of local charge density wave, and then what's visualized here is the direction that that wave goes in, one way or the other. And you can see that there's structure on multiple length scales here. This is another metal insulator transition material, V2O3, visualized with photoemission spectroscopy. This is strontium iridate, scanning tunneling microscopy out of Milan Allen's group at Leiden, visualizing Mott versus pseudogap. But the theme here is that there's a lot of different instances where quantum materials show interesting pattern formation and textures in the electronic degrees of freedom, kinds of things that are missed by the typical definitions of a phase of matter. So we need new ways to think about these things. And I'd like to remind us of something that happens at a continuous phase transition. So at a continuous phase transition, we get some very interesting phenomena that I think is related to what we're seeing. So this, in the test tube, is a video that is playing of, we have a mixture here in the test tube at high temperature. It doesn't actually matter what the mixtures are because the unmixing transition has universal properties. So two liquids mixed together, I think it's cyclohexane and methanol. And then as they lower the temperature, they're going to unmix. So you'll watch the unmixing transition, and you'll watch as they lower the temperature, the heavier liquid will gather here in the bottom. But first, we're going to see critical behaviors. So you see these fluctuations starting at the top. That's the beginning of criticality. And you see these white tendrils coming down. And as we get closer and closer to the transition, the white tendrils are overtaking more and more of the test tube, until finally those white tendrils overtake the entire size of the system. This is critical opalescence now, where you've got fluctuations on all length scales. Because you have fluctuations of the density on all length scales, you're scattering all wavelengths of light, and so it turns white. That's critical opalescence. And if we let the temperature go down a little bit more, you start to see the dense liquid is starting to gather at the bottom. Now, what's lovely about this particular demonstration is that you can see the correlation length. So right at a critical point, right at the second order phase transition, the correlation length goes to infinity, and all properties of the system take on power law characteristics. And so, for example, the density has fluctuations on all length scales. If you're a little bit away from the critical point, now the correlation length is finite. You still get critical fluctuations, but they only happen within a correlation volume. So when you observe the system on length scales smaller than the correlation length, you still see the critical behavior. Okay, and you can see that lovely visualization here. This is a critical fluctuation everywhere where it's white, and so you can see the correlation length is as long as the white tendril. And when we were a little bit farther away from criticality, right when those white tendrils started, you can see the correlation length there starting off small and then growing and growing and growing as the fluctuations, as the correlation length increases, and then it finally overtakes the entire system. So what's lovely here is that everything goes power law. And if we could take a zoom in and a zoom in of the density in the critical areas, we would see that because it's power law, it's self-similar. It looks the same on different length scales as you zoom in, which means there's a fractal nature to it. It's a disordered fractal, but it's fractal in nature. And when you have this second order behavior, there's universality. So there's universal power law behavior in the sense that all mixtures share universal features at their critical point, such as the critical exponents. So what does that have to do with this pattern formation? This pattern formation actually has structure on multiple length scales. And I'll show you how to see that there's actually a power law hiding in there. And we'll analyze it from the perspective of critical phenomena and see what kind of progress we can make there. So this is a visualization of scanning tunneling microscopy out of Jennifer Hoffman's group. This is BISCO 2201, so a single layer BISCO. It's an underdoped sample, transition temperature 32 Kelvin. The data is taken at 6 Kelvin, so low temperature. This is a 65 nanometer by 65 nanometer field of view. And what Jenny's group has done is in a local region, they take a Fourier transform of the R map. The R map is where you take the current at 1 voltage and divide by the current at the negative voltage. So for example, this one is current at 100 millivolts divided by current at minus 100 millivolts. One advantage to that is that the matrix elements cancel out there. And so it's a nice way to highlight changes in local electronic structure. And so they take a local Fourier transform in any given region of space. They see structure. This is the Bragg peak of where the copper atoms sit. And then there are these satellite peaks that can come up that indicate local charge density order. And they're in two different orientations. So here, if they're along this diagonal, then we color them red. If they're along this diagonal, we color them blue. So for example, in this region, where the stripes are running diagonally to the right, the wave vector appears here. And so we color those regions blue. If the stripes are in the other orientation, diagonally to the left, we color the regions red. So this is a map coloring the orientation of the stripes in this system. And so now if we think about what's going on with the spatial structure here, there's actually a lot of texture in here. I can actually, this big this big green line that I drew shows you one large system spanning cluster. So this red cluster, actually, you can walk from one side of this sample of this field of view to the other by making nearest neighbor steps onto red pixels. And so there's one large connected cluster. There are several medium clusters. I've highlighted those in yellow here. So the blue clusters are medium scale clusters. And there are many more tiny clusters. So I've circled some of the red clusters that are tiny. And so already you can see a hint that there could be power law behavior in there, because you have structure over multiple length scales, and you have a small number of large objects, but a large number of small objects. So in fact, there is a power law distribution here. And I'll argue that it indicates proximity to a critical point, that critical behavior is driving this pattern formation. And if critical behavior is driving that pattern formation, we can get critical exponents out of it. Now, to discuss critical exponents, I need a model. So in this case, we have that the stripes are in one orientation or the other. An either or variable you can model with an Ising variable. So I'll call stripes that are diagonally to the right, sigma equals +1. Stripes that are diagonally to the left, sigma equals -1. We make the reasonable ansatz that neighboring stripe patches want to be aligned. So that's a ferromagnetic interaction. We allow that interaction to be in the plane, of course. It's a layered system, so there should be interactions within the plane. Because of the layering, the interactions are weaker between planes, so that's why I pulled off this interlayer coupling. That allows us to change that parameter from all the way from a 2D system. Maybe the interlayer coupling isn't important, and maybe we should just think about 2D correlations here, all the way to a fully three-dimensional system. Now, how should we model disorder in this system? So we model disorder here using a random field term, and here's why. So the interesting stuff is happening here as a function of doping. And here, doping is chemical substitution. It's uncontrolled, and so it gives you disorder patterns. And so you can imagine that in any given region of space, there's a pattern of disorder of dopant atoms, and their particular pattern breaks the rotational symmetry of the host crystal. So in one region of space, that disorder, those dopants would tend to drag the stripes in one direction, and somewhere else they'll tend to drag them in another direction. That's why it couples linearly to the order parameter as a random field term. There are other ways that disorder can come in. You can ask me at the end of the talk, but the other ways are irrelevant in the renormalization group sense. It's a simple phase diagram. You're either in the ordered phase or the disordered phase, and the transition out of it is always second order, always critical. And so then what we're looking for here is the different critical points. What are the controlling critical points? So the blue arrows on every phase transition line tell you which way you need to look for the fixed point that's controlling the critical behavior of that line. And so we have a few different fixed points here. We can be in the two-dimensional limit or in the three-dimensional limit. We could be in a limit where disorder doesn't matter for the pattern formation, or we could be in a limit where disorder matters. Or we could be, maybe things don't interact at all. Maybe this pattern formation is just a flip of a coin at every region of space on the surface of the sample. Maybe it's not interacting. So we include these 5 fixed points in our analysis. So if this pattern formation is due to proximity to a critical point, then I claim that critical exponents are encoded in this pattern. We just have to learn how to get them out. We're used to deriving critical exponents out of experiment by a sweep of some parameter. So for example, we might measure magnetization versus a sweep of temperature and get one critical exponent, or versus a sweep in external magnetic field and get another exponent. Here, you don't have to sweep anything. In a sense, the sweep has already been done as a sweep in position. So there's enough information in here, I claim, to get critical exponents out. So what can we get out? We can get out the whole fractal dimension. So this is the question of these boundaries. How lacy are these boundaries? And when we analyze that, we would be looking at the radius of gyration of a cluster versus its perimeter. When plotted on a log-log scale, it's nicely linear. This is out of the data. And so we have more than two decades of scaling, so we're confident in our ability to extract this critical exponent. I'll show you in a few slides what number it is on a chart. We can also get out the volume fractal dimension. So here we plot the radius of gyration of the cluster versus its volume. This is the question of how Swiss cheesy is the cluster. Are there holes in it? Are there holes inside those holes? That kind of question. And the volume is measured by how many pixels does this cluster cover in the image. We also take a histogram of cluster sizes, similar to the analysis done here by Bianconi's group. So here you would look at the number of clusters that are a particular size. We've analyzed here actually the moments of the cluster size distribution, but it's the same idea. You count how many clusters are of a particular size. This is also nicely power law. And then you can look at correlation functions. And these turned out to be a bit of a mystery to us. I'll tell you the mystery. You would expect, we all expect the spin-spin correlation function to go power law at these critical points. And the spin-spin correlation function is simply these two spins a certain distance apart. Are they aligned or are they anti-aligned? Okay, that's the spin-spin correlation function. And when Jennifer Hoffman's group plotted that in this data set, it plummets. This is a log-log plot. If it were power law, it should be linear. It just plummets. It's basically an exponential decay. So that was troubling to me. But then Jenny's postdoc, Les Main, had the stroke of genius to plot the pair connectivity function. So this is a measure from percolation theory. It's to track the order parameter from percolation theory. So the pair connectivity function asks the following question. These two spins that are aligned, are they in the same connected cluster? So if the spins are aligned, can I walk by nearest neighbor steps on same color pixels all the way to that other spot? So it's a question of connectivity. And this turned out to be power law. However, it's not a percolation exponent. So this exponent that comes out of the analysis is not percolation. And it turns out that, in fact, people hadn't studied this correlation function for the Ising model. So the pair connectivity correlation function, it turns out we calculated it in several different Ising models, and it also goes power law. It was actually already known from the 70s that it goes power law in the 2D clean Ising model, but we showed that it goes power law in the 2D random field Ising model and on free surfaces and on slices of the 3D models. So it's also critical in those. Sorry, it's also power law at all those Ising exponents. And I'll skip that analysis because of time constraints. So let me walk you through what these charts are. The horizontal lines are the exponents that we extracted from the data set on BISCO. And then the width of that line is the error bar. Okay? And then the circles are theoretical calculations of those exponents. And so here we have the Fisher exponent, which is about the cluster size distribution. Here we have the pair connectivity correlation function exponent, the one I said is also power law at Ising models. We have the volume fractal dimension here and the Hall fractal dimension here. And then it's we figure out which ones are closest to the experiment. The left two columns are about the clean Ising model, whether 2 dimensions or 3 dimensions. The middle column is about percolation physics, so this would be just non-interacting. Because it's non-interacting, you only consider the 2-dimensional case because the observation of the STM is on a surface. And in the last two columns, we have the random field Ising models, whether 2 dimensions or 3 dimensions. And you can see, for example, that as is the usual case, critical exponents are sensitive to dimension. Here as well, in the clean Ising model, this critical exponent is sensitive to dimension. So what kind of inferences can we make based on this? Based on the pair connectivity exponent, we can rule out the clean Ising model in 2 dimensions. So this exponent is not matching. I know they look close on the graph, but this is the 0 line. And so this is about 0.2, and this is, this is about 0.1, and this is about 0.26. And so they're outside the error bars of each other. So it's not matching a clean Ising model. It's also not matching percolation. And so this right here, the volume fractal dimension is actually pretty far off as well. The random field 2D Ising model is off as well. The Hall fractal dimension in that case is not matching. So we've ruled out a few models with this analysis. What's left is the 3D models, actually. So this analysis isn't enough to distinguish for us between the clean 3D Ising model or the random field 3D Ising model. So you can't tell from this. It's just the numbers are too close to tell whether the disorder is mattering for the pattern formation. But I am excited that we can rule out the 2D models, okay? So that means the structures that they're seeing on the surface are coming from the bulk. And so this is, I'm particularly excited about this because critical exponents are sensitive to dimension. This is a general method for any surface probe that sees multi-scale pattern behavior. If they're seeing critical behavior, if they do this critical exponent analysis, this gives a way for the surface probe data itself to diagnose the dimension of the phenomenon. Okay, and this is great. This has been a standard critique of surface probes, is that they're only measuring the surface. So, so here's my analogy for here's my analogy for why this should work. You're used to diagnosing fractals out of windows. This happens to you sometimes. Sometimes you look out of a window and you see a tree, and that's fractal. But you know that tree fills space. You can just tell by looking at it, right? In your experience with trees, it's something that fills space, and then you're seeing the 2D projection into your eyes. This is a fractal that doesn't fill space. This is frost growing on the window. It's a two-dimensional fractal, and it looks completely different. You wouldn't be confused, okay, between the case where it's something growing on the surface and something that's in the bulk. Likewise here, what we've done with a critical exponent analysis, by similar means, we include the fractal numbers here as well as some other critical exponents. We've ruled out this case. It is not the case that this pattern formation is some pattern that's growing only on the surface like frost growing on a window. This is much more like the tree that's happening deep inside the material, and then we see the intersection of it with the surface. So, yeah, we've ruled out the 2D case. It's a 3D phenomenon. Now, another curious thing that came up here. So we can say that there are 3D critical nematic textures happening in Bisco. I call them nematic because of the broken rotational symmetry. So a liquid that breaks rotational symmetry is a nematic. So since we're tracking the stripe orientations, we're tracking just the nematic order parameter. So this is a generic phase diagram of cuprate superconductors. Temperature is a function of doping. And what I showed you is inside the superconducting dome, and I showed you the underdoped 32 Kelvin sample. But between them, Jenny and Eric have samples that cover the entire doping range, from underdoped to optimally doped to overdoped. And so we did this same analysis on all those different dopings, 5 different dopings. We see the same critical exponents at every doping. That's good. That's consistent with critical behavior. As a function of parameters, the critical exponent should not shift. What should change is the correlation length, like we saw as we went through the demonstration with the test tube. The correlation length grows to infinity at the critical point and then comes back away again. However, what was curious is that we could not detect a change in the correlation length. I was expecting to see that as a function of doping, we would see the correlation length blow up at a particular doping, and that would be the critical doping. But in fact, we just see 2 decades of scaling throughout. It's scaling, it's power law scaling throughout their entire field of view. So what we can say is that the correlation length exceeds their field of view throughout this entire doping range. Now that's also, so these are the different dopings, 2 different underdoped, optimally doped, 2 different overdoped samples. And so that is curious because this is a very large critical region. Okay, so this is not like the case of, say, superfluid helium where you have to get insanely close to the transition to see the criticality. This is very robust, large critical region. So that's a bit curious as well. And it's that broad criticality, the fact that there's critical behavior, power law scaling out to the entire field of view through the entire doping range, that's actually helping us distinguish between the clean case and the random field case. That broad critical region is characteristic of random field models. So you can get 2 decades of scaling even 50% away from the critical point in a random field model. So the random field, the very large critical region of the random field model explains the doping independence that we saw. Now the prediction would be, give us larger fields of view, and then we should be able to detect that correlation length, and that the correlation length should be a function of doping. So we'd love to have much larger fields of view. I think we will have to go to a different probe because STM experimentalists don't want to give me, times 100 dynamic range here. Okay, thanks. Also, the static nature of the patterns is closer to random field physics than to the clean Ising model, which would be expected to have some temperature fluctuations. The static nature here indicates, so this is the data in the middle. Sorry, this is Bisco, the data I showed you before. This is a visualization of textures that would come out of a 3D random field Ising model measured at a free surface. So these are simulations out of my group, or a clean 3D Ising model at a free surface. And so the fact that these patterns that are seen in an experiment are static are another indicator that it's random field physics, because the barriers to equilibration go sky high in random field models. Rather than the usual critical slowing down, they have extreme critical slowing down. The time scales for equilibration blow up exponentially as you approach the critical point. So, our conclusion here is that Bisco has 3D critical nematic correlations throughout the superconducting doping range. And there are large barriers to equilibration, inhomogeneity there. This is the fixed point that this pattern formation is near. But moreover, I want to emphasize that this is not a quantum critical point. So what does a quantum critical point look like? Quantum critical point, as a function of some parameter, you're increasing quantum fluctuations, and the critical region is actually pretty narrow. It's confined to, in this case, it would be confined to the critical doping, and come up in a wedge at temperatures above that doping. It's a narrow range. Whereas what we're seeing here is that the data set coming out of Hoffman and Eric's group is critical throughout the doping range. It's not like quantum criticality, but it is like random field criticality, which is a classical zero temperature criticality. It just has a much, much broader critical region. So the critical region here in a random field model is huge. Like I said, you can get 2 decades of scaling within a factor of 2 of the critical point. So I claim that this looks much more like this case. It's not a quantum criticality because it's a very broad critical region. And I will leave you with those ideas, and thank you for your attention.
Thank you very much, Erica. Great. Questions, please. Antonio, and then it will be you.
Thank you for this beautiful talk. I just wonder, in your theoretical model for like physics for ladies, you can interpret your theoretical picture as insulator and metal, blue and red, like insulator and metal.
Right.
It's okay?
Yes.
So if it's this, we have published recently a paper on mercury compound, superconductor, that are the critical point of strain.
Okay.
And doping, and then you have 4 decades of power law.
4 decades, okay,
4
nice.
decades, and now we can go to 6 decades. Because now we can do with the X-ray beam, you can go from 10 nanometer to 500 micron. So you can have full decades, so we got 4 decades up to now, at the critical point of strain and doping.
Very nice. Very nice. I will
yeah,
talk
there is
to you
a lot
about
of work. We go very slow, but
yeah, yeah, very nice. I mean, we have actually analyzed it for these metal insulator transition materials, for neodymium nickelate and for vanadium dioxide. But I would love to have access to data sets that have more dynamic range.
Yeah.
Yeah.
But it's coming.
Very nice.
Okay, so this is more like a comment than a question. I think a percolative transition can be both first order and second order. And essentially what you call a wide critical region is a characteristic of a first order transition, which is always a crossover in the average quantities. And the smoking gun is essentially whether your percolative cluster is staying pat on the scale of the experiment, or it is changing very quickly on the scale of the experiment. Because in a first order transition, the typical situation locally is that when something flips, it flips. And it stays that way. And you need a lot of samples to build up the average behavior at a given point. While in a second order transition, you sit at a given point, this is standard molecular field theory, and you see everything in time happening on that one point, you see. So I think that your results actually point very strongly in the direction that we have a first order phase transition and not a quantum critical point.
Well, okay, so I appreciate the comment. We should talk more about that. So in the models that I used, if I wanted to see the first order behavior, I would drive as a function of applied field. And now let me just put up the Hamiltonian here. So there is a first order phase transition in the model, for sure. You would add another term, which would be applied field. And so as a function of applied field is where you see the first order nature of the phase transition. And in fact, that's actually relevant to our comparisons to metal insulator domain physics. So when we're looking at metal insulator domain physics, since they're going from fully metal to fully insulating, that is in the first order direction. And so it definitely comes up there. But there is a range in which there is a critical endpoint still. And so there's this range where the critical endpoint comes back and affects the pattern formation in the first order, on the first order line for a little bit near the critical point. So I agree with you. We see that in the metal insulator transition materials. here, if you wanted to see the first order behavior, I mean, we should talk more. I would love to know more if you think there's true first order behavior in here. But my understanding is that from this model, well, at least theoretically speaking, the way I would get the first order behavior is with an external applied field. And the way you would have an external applied field in this physical system is something that couples to the stripe orientation. So I would need strain. And so we have talked with experimentalists about applying strain. You know, uniaxial strain in one direction as you cool versus, say, uniaxial strain in the other direction as you field cool, and looking at those differences. And that should be the first order line. But we should talk more.
Okay, I agree with that. I'd just like to point out that the question is what you need to do in the model to get what happens in reality. Okay?
Yes.
And the question is whether the spanning cluster in real BISCO is sitting there or fluctuating quickly.
Oh yeah, it's static. Now this is at 6 Kelvin.
That's my point. That's my point.
It's 6 Kelvin, right?
It's static.
Well, it's static, but a good reason to expect static here is because the timescales to equilibration have gone through the roof, right? So the timescales, I mean, the random field Ising model is notorious for long equilibration times. This is why permanent magnets stick around, right? You have just an insanely long equilibration time. Yeah.
Okay, please.
So not all of us are lucky to have STM probe, but we can still measure, most of us can measure penetration depth or coherence length as a function of temperature. Can you predict critical exponents?
I will think about that. I will think about that. The connection we would have to make would be between you say the coherence length and the coherence length and the penetration depth, right? So we would have to work very hard to put in the superconducting order parameter on top of these textures to make those predictions. It's a very nice idea. Yeah, we haven't gotten there yet. It's a good idea.
Okay, let's. Okay, before we thank the speaker,
I can
one
reply
small
to his question. So the external field is a strain, and that you have a first order phase transition. And then in order to get the coherence length superconductivity, you have to follow the idea of a Winokur, because you have a superconductor to insulator transition. It's clear, you can see from this phase.
So one small comment at this point. Okay.
Yeah, the critical response, they come from, you have to put a superconductivity in a complex method.
You use this, random field model as a just model, but it's always a question what disorder is doing, because it was an old paper by Alexander Finkelstein, which is classic now, but it looks like nobody ever read it. And what he showed exactly that what disorder is doing is actually to tune the Coulomb interaction. And therefore, disorder has nothing to do with this transition, and this is just the, sort of competition between sort of like Josephson coupling and Coulomb interaction. This is the first. Second, it's just, the comment to this notion.
Okay, so if I understand your prediction is that if I add the superconducting order parameter on top of this, the superconducting order parameter won't be sensitive to
for
the
example,
disorder.
So you tune it with the disorder, but it's fine. But another point to make is that, as Carla demonstrated a couple of days ago, it was a rigorous calculation of the superconductor to insulator transition. It's first order, and this is quantum critical point, period. The fact that it's first order does not mean that it's not quantum critical point. And what was, again, a rigorous prediction about this is that in the vicinity of this quantum critical point, first order, you do have this self-induced granular structure, exactly what Erica beautifully demonstrated. So everything seems to be quite consistent. Okay, so thank you very much again, and
thanks. Thank you.
Great. Thank you. And next talk, which is, I believe, online, right? Okay, so it's going to be Leshen Yang, evaluation of the electronic structure in ultra-thin films of intrinsic magnetic topological insulator. Please go ahead.
Okay, let me share my screen. Can you see my screen? Can you see my screen? Is everything okay?
We're hearing you all right, so please go ahead. Can you hear us?
Okay, okay, thank you. Good afternoon, everyone. I'm Le Xianyang from Tsinghua University. It's a pity that I cannot attend in person due to the difficult COVID situation, but I'm happy that I can join this wonderful conference online, and I'm happy to have this chance to present some of our recent results on the electronic structure of the thin films of manganese bismuth telluride. I would like to thank the organizers for the invitation. In this talk, I will first introduce the experimental tool and the research background. Then I'll compare the topological electronic structure of the bulk sample and the thin films. Then I will focus on the observation of the Rashba split band and its interaction with the topological surface states. In the last, I will give a brief summary. Okay, first the introduction. Our experimental tool is the angle-resolved photoemission spectroscopy, APES. The basic working principle is the photoelectric effect explained by Einstein. A photon beam excites electrons out of the solid materials, and an electron analyzer is used to collect the photon electrons, and the analyzer is their momentum and the energy. By a simple calculation based on the energy and the momentum conservation laws, we can get the energy momentum distribution information in the solid materials, which is the band structure of the solids. In nowadays, the capability of APES has been greatly improved. By focusing the incident beam down to tenths of nanometer scale, we can measure the local fine electronic structures with micro APES. By attaching the spin detector, we can measure the spin structure with spin APES. If we update the incident beam to pulse the lasers, we can measure the non-equilibrium electronic structure dynamics in time domain using time resolved APES. Accurate measurements of multi degrees of freedom of quantum materials will provide us more complete information. We use APES to search and study topological quantum materials. Before the discovery of the topological quantum states, the classification of matters was based on Landau's spontaneous symmetry breaking theory. This wonderful picture is challenged by the discovery of quantum Hall state in 1980 by von Klessen. In the quantum Hall state, the bulk of the state is insulating, but the edge is conducting. Each quantum Hall state can be described by the topological invariant or the chain number. There is no symmetry breaking in this quantum state. Around about 2005, the discovery of the topological insulator further expands the member of topological quantum materials family. Up to date, the family of the topological quantum materials includes many members, such as the topological insulator, Dirac and wire semimetals, and topological superconductors. It's interesting to note that the quantum chemical calculation recently has suggested that more than 70% of crystals are actually topological quantum materials. Our story today starts from the topological insulator. The major difference between the topological insulator and the normal insulator is the inverted band gap and the existence of the topological surface states. In the topological insulator, the strong spin orbit coupling plays a role as the external magnetic field in the quantum Hall state. The spin and the momentum of the surface states are locked, forming a gapless Dirac cone in the bulk gap. Due to this spin momentum locking, the electrons are immune to the backscattering induced by non-magnetic impurities. Therefore, the topological insulator is potentially useful for the low energy consumption electronic devices. In a prototypical topological insulator, such as bismuth telluride, the bulk band topology guarantees the existence of two-dimensional topological surface state with gapless Dirac dispersion, which can be directly visualized using APES. Time reversal symmetry plays a crucial role in the protection of the gapless Dirac surface state. On the other hand, already from the very beginning of the study of topological insulators, researchers have realized that intriguing quantum phenomena and the new states can be induced if the crucial time reversal symmetry is broken. An exchange gap can be caused in the topological surface state, realizing the so-called magnetic topological insulator. In this situation, a chiral edge mode can emerge with quantized conductivity if the Fermi level is tuned in the exchange gap. Such magnetic topological insulators are potentially useful for engineering a variety of exotic topological magneto-electric effects, such as the quantum anomalous Hall effect, in which the quantized Hall effect occurs without external magnetic field. Another example is the axion insulator phase, in which the gapped surface shows a half quantized anomalous Hall conductivity. By tuning the magnetic structure, other interesting phases can also be realized, such as the Majorana fermions if the superconductivity is involved, or the fractional chain insulators and the wire semimetals. Unfortunately, although the concept is clear and beautiful, it is not easy to realize magnetic topological insulators. Taking the quantum anomalous Hall effect as an example, it was originally realized in vanadium or chromium doped bismuth antimony telluride system. The observation of the quantum anomalous Hall effect requires both fine-tuning of the sample composition and ultra-low temperatures, making the experimental demonstration extremely difficult. It is thus highly desired to search for stoichiometric topological insulators with intrinsic magnetic ordering. In about 2018, the first intrinsic magnetic topological insulator, manganese bismuth telluride, was proposed and ignited intensive research interests. It exhibits a layered structure by stacking Wonderwalls septuple layers of manganese bismuth telluride. Each septuple layer can be viewed as an extra manganese telluride layer sandwiched at the middle of the well-known bismuth telluride quintuple layer. It enters an antiferromagnetic ordered state below 25 Kelvin. The antiferromagnetic state ordering is A-type and with the magnetization z-axis along the C direction. Although the anisotropic energy is only 1.7 millielectron-volt. Calculation reveals the band inversion near the gamma point with a bulk gap of about 200 millielectron-volt, suggesting its topologically non-trivial nature. Correspondingly, calculations predicted a gapped surface state in the A-type antiferromagnetic phase. The surface gap is predicted to be several tenths of a millielectron-volt, although it's different in different groups, making manganese bismuth telluride an ideal materials platform to realize quantum anomalous Hall effect. Soon, several remarkable breakthroughs have been experimentally realized in manganese bismuth telluride, including the quantized anomalous Hall effect, even at zero field. A phase transition from a chain insulator to axion insulator to a chain insulator, and the observation of a high chain number chain insulator. We used the APES to study the electronic structure of bulk manganese bismuth telluride. Actually, shortly after the theoretical prediction, many APES results have been presented to show its basic electronic structure. Experiments using synchrotron radiation show a large gap ranging from 50 millielectron-volt to 200 millielectron-volt, which depends on the photon energy used in the APES experiments. This suggests that the measured band gap is maybe from the bulk bands. Using synchrotron radiation source, we conducted APES measurements at relatively low photon energies. The basic electronic structure is very similar to other reports using synchrotron. We observe a clear photon energy dependence of the dispersion. The valence band top and the conduction band bottom, as well as the gap between them, all show a clear dependence on the photon energy, which is periodically varied. This suggests their bulk origin. Interestingly, at photon energies below 16 electron-volt, we observe a weak but resolvable states in the bulk gap, forming a Dirac-like dispersion. This Dirac-like band dispersion show weak photon energy dependence, suggesting its surface origin. In order to understand the nature of this in-gap state, we conducted laser-based RPS measurements with superb energy and momentum resolutions. As shown here, we observe a Dirac-like dispersion with diminishing surface gap, which can be better visualized in the zoom-in plot and the second derivative of the spectrum. The topological surface state with diminishing gap was also observed by other groups. At low temperatures, the bulk valence band shows band splitting near the gamma point. And this can be seen from the second derivative of the spectrum, which this splitting disappears at a high temperature above the nil temperature. From the temperature evolution of the EDC, we can see the evolution of this band splitting. This band splitting disappears above 25 Kelvin and suggesting a clear influence of the magnetic ordering in the electronic structure of the system. However, the surface state, this surface state remains gapless above and below the antiferromagnetic ordering, without clear change with the temperature. On the other hand, one can insert bismuth telluride layers between the manganese bismuth telluride layers, so forming other manganese bismuth telluride compounds such as 147, 1610, and so on. The insertion of bismuth telluride layers will suppress the interlayer antiferromagnetic coupling and introduce a ferromagnetic state in the system, which may favor the zero field quantum anomalous Four effect. We also measured the 147 system. It can be seen as inserting bismuth telluride layer between two manganese bismuth telluride layers. The sample shows an antiferromagnetic ordering transition near 12 Kelvin. And it enters a ferromagnetic-like state below 5 Kelvin. Due to the Wonderwalls coupling between different layers, there exist different sample terminations after cleavage. We can see here from the atomic force microscopy topography. In order to study the surface electronic structure on different terminations, we conducted RPS measurements with high spatial resolution by focusing the light beam into a small spot, smaller than 1 micron in synchrotron radiation and 20 micron in laser RPS. The RPS intensity map on the sample surface indeed show the existence of two kinds of domains with different spectral weight of manganese 3D orbitals. We also observe different core level spectra in these two different domains. We can see a difference from the overall dispersion on the two terminations as well here. We then zoom into the spectra near the Fermi level to study the termination dependence of the surface states. Our measurement reveals gapless surface electronic structure on both manganese bismuth telluride termination and bismuth telluride termination. The experiment shows gapless surface state on both terminations, and the overall electronic structures measured is consistent with the calculation, except that the surface electronic structure in the calculation is gapped in manganese bismuth telluride termination. Briefly speaking, the situation in 147 is quite similar to the situation in 124 system. We believe that there is a unified mechanism in the diminishing the surface gap in both materials. The observation of the nearly gapless surface state is beyond expectation, and we haven't fully understood this result. There are many scenarios to explain this observation. I here briefly introduce some of them. Firstly, considering the small magnetic anisotropic energy, there exist multi-magnetic domains of different magnetization orientations on the sample surface. These magnetic domains will mediate the surface state together and contribute to the nearly gapless surface state. The magnetic domains and the domain walls will indeed observed recently by magnetic force microscopy. The size of the domain wall is about 0.5 micron. The other scenario is the disordered magnetization on the sample surface, which recovers the time reversal symmetry and induces the gapless surface state. The third scenario is self-doping effect. Due to the self-doping effect, the gapless surface state is lower in energy than the gapped state. So therefore, this one is easier to be observed. Unfortunately, the true mechanism of the diminishing surface gap is still an open question. To make the situation more complicated, recent RPS measurements suggest the surface gap can vary from 10 millielectron to 70 millielectron volts, strongly depending on the samples. Some work also suggests the native point defects plays an important role in determining the surface gap. To test these scenarios, we used the laser-based micro RPS to study the electronic structure of manganese bismuth telluride. We built laser-based micro RPS system in our lab. By focusing the 7 eV laser beam down to 1 micro, we can scan in the beam on the sample surface. Therefore, we can measure the intrinsic electronic structure in a single magnetic domain. The scanning photo emission measurement on the striped gold sample shows the spatial resolution of our system to be better than 1 micro. The system also have the capability to measure the spin structure. Using this laser-based micro RPS, we scan the sample surface of manganese bismuth telluride at about 15 Kelvin. Unfortunately, at different sample positions, our measurement did not show a clear change of the band structure, except in near the edge of the cleaved sample, where the cleavage seems to be bad. The other spectra remain gapless. So it seems that the domain wall is not the major problem for the diminishing surface gap. Further experiments are still going on to study the spatial inhomogeneity of the electronic structure. Okay, next I will talk about the thin films of manganese bismuth telluride 1 to 4. In addition to the diminishing surface gap, we noticed several other peculiarities in the electronic structure of manganese bismuth telluride, which were previously ignored. First, there is this kink-like structure in the dispersion of topological surface state. Secondly, the surface state seems to be broadened and weakened as approaching the Fermi level, which is beyond the expectation of Fermi liquid theory. Thirdly, there is rush bar split band, which was attributed to a bulk valence band before. Fourthly, the thin film, which is more important, are still not sufficiently studied. Previous measurements on the film shows a drastic difference between the electronic structures of the films and the bulk. To understand this drastic difference and other peculiarities, we studied the electronic structure of the films using our laser RPS. The films were grown by MBE and were characterized by different techniques. We observe sharp streaks in the read pattern, suggesting the high quality of our samples. The in-plane lattice constant of our crystal is estimated to be 4.3 angstrom, in good coexistence with the bulk sample. The surface topography measured using STM show similar surface structure with bulk sample as well. The hexagonal lattice structure corresponds to the top surface of telluride atoms. Similar to the bulk sample, we also observe considerable defects, mainly from manganese atoms occupying the bismuth sites, or the manganese bismuth anti-site defects. The Fourier transform of the surface map gives an in-plane lattice constant of 4.2 angstrom, consistent with the bulk sample. The MBE grown samples show a high quality. Recently, Professor Kehe's group has successfully observed the quantized anomalous fall effect in the 5SL film. the overall shapes of the rho yx and the rho xx versus h are very similar to those observed in manganese bismuth telluride flake samples that was cleaved. The high field and the low field parts of the curves roughly correspond to the ferromagnetic and antiferromagnetic configurations respectively. In the ferromagnetic state and the high magnetic field, the absolute value of rho yx and rho xx always evolve inversely with magnetic field and with the gate voltage and the temperature, which is a signature of quantum Hall or quantum anomalous Hall effect. The quantum Hall effect is further excluded by the absence of transport features of Landau level formation. Therefore, the high field part of the data are dominated by the quantum anomalous Hall effect. Rho x reaches the quantized value of about 1, nearly 1, below 0.4 Kelvin. Okay, we use laser APS to study the electronic structure of these MBE-grown thin films. We can easily find the drastic difference between the electronic structure of the bulk and the 5SL films. Consistent with the electronic structure of the bulk samples, we observe the conduction band and the valence band with a gap of about 150 milli-electron volts. The topological surface state shows a diminishing gap, but no kink-like structure here. It merges into the bulk conduction band with a much weaker spectral weight. The band structure shows a clear dependence on the film thickness. In the 1SL film, we observe an M-like valence band with a band gap as large as 300 milli-electron volt between the valence and the conduction bands. Interestingly, the band gap shrinks in the 2SL film and then reopens in the 3SL film. Above the 3SL film, the surface state gradually emerges and finally evolves to the topological surface state in a bulk sample. The experiment is in overall agreement with our DFT calculations. According to the calculation, the topology of the odd number sample films and even number films are different. The even number films are topologically trivial. The chain number is 0. And in the odd number films, the 1SL film is also topologically trivial, but the films are chain insulators in films above 3SL film. Therefore, there is a change of the topology of the films above 3SL.
Excuse me, you have 5 minutes left.
Sorry?
You have 5 minutes left.
I think I have, yes, I will finish in time. We also noticed that the Fermi level of the films is different from the bulk sample. We thus use surface doping of alkali metals to raise the Fermi level of the film. Here is the evolution of the electronic structure of 6SL film with surface potassium doping. With increasing doping level, the band shifts towards higher binding energies. Interestingly, near 0.1 monolayer coverage. The surface state seems to separate from the bulk states. And the kink-like structure emerges in the surface state, which can be better seen from the second derivative spectrum. This spectrum looks very similar to the spectrum in a bulk sample. The interesting evolution of the band structure induces a Lifshitz transition of the change of the Fermi surface topology from a single circle to 3 circles here, and finally to 1 circle again. Okay, now I'll discuss the origin of the kink-like structure. We compare the band structure of doped film and the bulk sample here. Despite the broadened spectra, the basic electronic structures are quite similar to each other, including the kink-like structure, the weakened and broadened topological surface state near the Fermi level, and the emergence of the Rashba split band. The observation suggests that the electronic structure of MBE-grown film is actually quite similar to the bulk sample, except that the doping level and the surface condition may need to be modified. To understand the interesting evolution of the electronic structure, we also conducted a doping-dependent measurement on the bulk sample. With slight doping, the band shifts towards high binding energies. At heavy doping, both the rush bar split and the kink disappears, leaving a band structure similar to that of the thin film. We would like to emphasize that during the surface doping, the rush bar split band and the kink-like structure shift down or up together and disappears at the same doping level of the alkali metals. This lock-in behavior suggests a close relationship between the rush bar split band and the kink. We propose that the kink-like structure is induced by the interaction between the rush bar split band and the topological surface band. In the pristine film, the rush bar split band is unoccupied. With surface potassium doping, it gradually shifts down and hybridizes with the topological surface state, inducing the kink-like structure. At high doping level, both the film and the bulk sample show a similar electronic structure with only inverted bulk band and topological surface state within the bulk gap. The rush bar split band observed in the films and the bulk samples resembles that in the bismuth selenide after surface doping, which is related to the quantum well state formed after surface doping. Based on the 4-band model for topological insulators, we simulated the band structure of manganese bismuth telluride slabs. The surface doping mainly induces surface potential. Without this surface potential, the antiferromagnetic term opens a gap in the surface Dirac cone near the gamma point. When the surface potential is turned on, but the magnetic field is turned off, a quantum well state with rush bar splitting emerges. When both the surface potential and antiferromagnetic term are turned on, the rush bar split band coexists with the gapped topological surface state. Our calculation thus suggests that the observed rush bar split band in the film and the bulk samples are from the quantum confinement effect, similar to the tunable rush bar split band in bismuth selenide. The observation of the rush bar split band and its interaction with the topological surface state is not trivial. First, it will contribute to significant carriers to the system, which will play a role in the transport of the material. Secondly, it provides a platform to realize the rush bar ferromagnet, considering the surface ferromagnet of the sample. As proposed by the theory, the spin-optic coupling and ferromagnetism may open a gap at the band crossing point. Such a system is attractive for the anomalous Hall effect and possibly also for quantum anomalous Hall effect. Okay, I would like to summarize my results with these two videos. We reveal a topological phase change from a trivial band insulator in 1 SL film to a chain insulator in 3 SL film. We observe a rush bar split band interacting with the topological surface state in manganese bismuth telluride, which induces the kink-like structure. The surface states can be effectively manipulated by surface potassium doping, and the rush bar split band may establish a rush bar ferromagnet on the surface of the sample. Okay, I would like to thank my collaborators. The films were grown by Professor Kerher's group, and the bulk samples were grown by Professor Wang and Professor Guo. And APES measurement were conducted in Tsinghua University with help from Professor Yulin Chen and Zhongkai Liu's group. The calculation was done by Professor Xu in Tsinghua University. Okay, thank you very much.
Okay, thank you very much. A wonderful talk. Well, is there one urgent question, please?
Thank you very much for the nice talk. I have a question concerning this rush bar state. Why would there be the rush bar state on the surface of the bulk single crystal of MBT without any potassium deposition, on your opinion?
Yes, I think a possible reason is due to the defects which induces additional carriers on the surface. It's similar to the potassium doping.
What kind of defects that would be different from those that are already present in the bulk? You just cleave the bulk single crystals, the defects will be just there in the surface subtopo layer, which would be exposed by the cleavage. And so
Yes,
where
then
does
but the surface is always not ideal. It's there is a manganese bismuth andesite defects which can induce electrons or let's say carriers, which can induce the quantum confinement effects.
So you think they appear at the surface more than in the bulk? In the block
Yes.
layer at van der Waals material, which is like chemically
Yes.
inert and protected and stuff.
Yes.
Okay, thanks.
Okay, our time came to end, so let's thank all the speakers of our session once again. And move to lunch.
Good afternoon, everybody. So we are starting our half plenary session this afternoon. And we have one talk basically given by Joanna Szymanska. Excuse me if I pronounce wrongly, probably wrong. Yeah, she will speak about intelligent photons LED and their application. Okay, thank you. Please.
Thank you very much for introduction. Thank you very much for the organizer for inviting me here. Maybe I will try to pronounce the name properly. It's Joanna Szymanska. I work as a senior research scientist for Toshiba Research Europe, which is based in Cambridge. And the results that I will be talking about were achieved with collaboration with two universities, Cambridge University and Sheffield University, and these are the people who contributed significantly to our results and current state of the work. So in my presentation, I will talk briefly about the vision of future quantum internet. Then I will introduce on-demand and entangled photon pair sources. I will show a couple of applications in quantum networks, and then I will hopefully have time to talk to you about enhanced emission from circular Bragg gratings. So this is our latest type of device that we are working on, which is very hot and very promising. That's why I kind of try to load a couple of slides and pictures here. And then I will conclude at the end. So, vision of quantum internet. We believe actually that the internet in next couple of years is going to change drastically, mainly because of the progress in quantum technology. And obviously it will consist of a mixture of different quantum network types. We will have quantum encrypted classical communication in our networks. We will also have some quantum sensing arrays and remote programming of quantum processors. So all these elements will be, or most of these elements, we predict they are going to be based on quantum light, which is a fundamental resource for these applications. So I mentioned actually here a couple of basic elements of the quantum internet, but I believe the very, very basic one is the quantum relay. And most of my talk, we in most of our experiments, we perform simple experiments showing that we can relay the photons from one source to another. So we believe actually that quantum relays are the basic elements of the future quantum network. And essentially by using on-demand entangled photon source here, we are able to interfere one photon coming from the source with a photon coming from our source, with the input photon. And then by doing the Bell state measurements, which will reveal no quantum information, we can actually transfer the information to another photon, entangled photon, and pass it further distance, which eventually actually will, our information will end and reach side B, the receiver of the quantum information. So we believe that actually the source of the relays is this on-demand entangled photon pair source, and obviously this is the biggest challenge actually, how to create it and how to make it reliable. And I will talk about it in the next slides, actually how we managed to solve this little point in our graph. But in the meantime, I also wanted to stress that we believe that quantum relay will not amplify or purify quantum information because the qubits will still get lost in the fiber optics at the long distance transmission. However, they will have this unique feature that they will reduce quantum error rate for intermediate distance transmission, mainly because we will be able to switch on and off the detectors at certain points because we will know exactly when we are expecting a photon. Obviously, some of them will be lost, but basically this noise between the windows is going to be completely neglected, which is going to reduce the error rate. So this is additional advantage of using the quantum relays. So coming back to the heart of the quantum relay, of the basic element of the quantum internet, what do we want? We want a single photon source. And what does that mean in practice? Our ideal single photon source would produce individual photons at a certain time. One photon per pulse, exactly one photon, with fixed distance, repetition rate, and high efficiency. We would like the repetition rate to be in gigahertz, mainly because of the fact that this is the frequency which is compatible with quantum key distribution systems. What we don't want is multiple photon events occurring at the same time. We don't want any gaps, because obviously that will introduce some errors and some inaccuracies of our measurements. Once we've got actually such source, then we can actually start worrying about encoding our quantum information in single photons. And there are a couple of ways we could do. We could do polarization encoding, and this is the most typical and most widely used encoding of photons. We could use path encoding, time bin encoding. This is actually something that we are working in parallel right now. And also the fourth type of encoding is orbital angular momentum encoding. I'm not going to be talking about it in detail, but just briefly mention that there are actually a couple of ways. So back to our source. So what is our on-demand single photon source? So we chose to work with epitaxially grown quantum dots because they promise to be extremely efficient, well, extremely suitable for such applications. And what they are 3D semiconductor structures confined in a matrix of semiconductor with higher energy band gap. And typical dimensions are 15 times 5 nanometers. You've got a couple of AFM images showing you one fairly round and nice quantum dot, another one slightly elongated, and you can see the line scan in both directions showing that there is a difference. If we shine some light with the wavelength which is lower than the emission wavelength of the quantum dot, we will obtain a photon, basically a biexton cascade occurring in a quantum dot. So the carriers will relax to the ground state of the dot, and then they will recombine in two different polarizations. And this is a typical spectrum. Well, this is a clean, nice spectrum exactly showing us a line coming from biexciton and exciton here. So these quantum dots, they can be grown by MOVP or MB. What we need actually for these, in order to access a single one, we need them to be low in density, and we also need them to have a small fine structure splitting and long coherence times. And also what I mention is that here this is an XTM image of one of our quantum dots. You can see this is basically atomic resolution image of indium arsenide in, I believe this is gallium arsenide around. And also one thing I wanted to mention on that slide is that if there is a certain asymmetry related to the dot, we will have an effect which is called fine structure splitting, which means that our exciton and biexciton line will have a splitting when we measure in two different polarizations. So this is something that is obviously will have a negative effect on our measurement. We want it to be as small as possible, which means we need the dots to be symmetric, almost perfect. Some people actually say that quantum dots are artificial atoms. Again, I wanted to show you a couple of pictures. Again, XTM image of basically single atoms within quantum dots. This is a cross-section embedded in gallium arsenide. What we do, because actually such quantum dot will emit in basically in like all dimensions, we try to extract as much light from the quantum dot as possible. So one way, what we normally do is to add Bragg mirrors. So we've got a Bragg mirror at the top and semi-transparent Bragg mirror actually on the bottom, on the bottom and top. And these already enhance extraction of light in vertical direction. There's also other tricks. I'm going to talk about it in a moment, how to extract more light. But this is another thing that we work on, how to extract as many photons as possible from such quantum dot. And again, typical dimensions, again, it depends on the material system that we are using. So the diameter is about 30 nanometers, and then the height about 8 nanometers. Compared to the atom dimensions, you've got the diameter 0.1 and diameter and height. No, sorry, you've got the typical atom dimension is about 100 times smaller. So how do we make quantum dots? So there's been 2 talks yesterday talking about it in detail. I will just briefly say that we've got 2 types of semiconductors with 2 different lattice constants, and essentially we start depositing layer by layer of atoms one on top of each other. And then typically what they will do, they will, once the layer actually gets thicker, they will strain, they will form islands, which later on is capped with the same material as the substrate. That will result in formation of a quantum dot with a wetting layer, uniform wetting layer, or not uniform, underneath. So as Toshiba doesn't have any growth reactors, we outsource our material at 2 different places. So some of our quantum dots come from Cambridge University, and this is the reactor actually that we are using. And some of our quantum dots come from University of Sheffield. The difference is that in Cambridge we use MBE, in Sheffield we use MOVPE. The other difference is that in Cambridge we use gallium arsenide. In Sheffield we use indium phosphide. The reason why is that here we can reach probably O-band. We can definitely reach O-band with this material system. In Sheffield we can swiftly extend to the C-band of telecom window. So yes, what do we do? How do we make our devices, our quantum devices? We have this sort of sandwich approach. In order to determine the emission wavelength of our quantum dots, we have to first determine the material that we want to play with. And as I mentioned before, typically we use indium arsenide quantum dots, which are embedded either in gallium arsenide or in indium phosphide. And then we design different types of cavity. Most commonly, what we use at initial stage of the research, we use some so-called planar cavity where we put bottom Bragg stack and top Bragg stack to enhance emission in vertical dimension. Later on, actually, we may also end up adding some doping layers in order to get electrical access to the carriers inside the quantum dot. We also fabricate different types of devices around the dot, for easy manipulation. And then also another thing that we could do, we can engineer the quantum dots, which means actually we could, this is actually the latest progress that we've achieved. We can design to have either symmetrical dot with small structures, fine structure splitting, or we could move on. Well, we could keep on basically not caring about it and design a quantum dot to be slightly more elongated. So what does that mean? If I say that the dot is slightly more elongated, I mean that we grow quantum dots by Stransky-Krassanov growth mode, which is presented in this picture. So essentially, what does that mean? That once we've got substrate, we open indium and arsenic source at the same time. And essentially, we end up growing a wetting layer first, and then eventually we've got quantum dots which are strained driven. And such quantum dots will be typically elongated. The AFM looks like this. Slightly bigger magnification of a single quantum dot looks like this. And again, actually, it's quite clear that they tend to be quite significantly elongated along one direction. But if you need your dot to be round and symmetrical, you could actually apply a droplet epitaxy quantum dot. And this is something that ages ago people say that it will never ever work because, well, they had their reasons. But essentially the principle is that you deposit metallic droplets on the surface of semiconductor, and then later on you open up a source of element 5 and you crystallize your metal afterwards. That results in a formation of really lovely round circular quantum dots, which, as you can see, are not very elongated. The benefit of it is that the fine structure splitting of such dots is significantly smaller. So here you've got statistics over SK and droplet epitaxy quantum dots. So these are both grown, they are very similar, they are both indium arsenide in indium phosphide quantum dots, and they emit around C-band, telecom C-band. And you can see that droplet epitaxy quantum dots, they are very kind of well-defined actually within fine structure splitting, while SK quantum dots, you may have actually fine structure splitting varying from, let's say, 60 to over 300 micro eV. So yes, both techniques produce quantum dots in telecom C-band. However, droplet epitaxy are significantly improved. Let's move on. Another superiority of droplet epitaxy quantum dots is the fact that they have significantly extended coherence times. So these are a couple of results of 76 droplet epitaxy quantum dots measured together with 26 Stransky-Krassanov quantum dots. And on all of them, we chose negatively charged exciton just to be consistent and fair. And these are three typical kind of coherence time measurements. You can see that actually some of them could be very short, some of them could be very, very long. But then if you look at the statistics, you can see that the distribution for droplet epitaxy quantum dots is way, these are the SK quantum dots, is way more narrow, and the coherence times are way below 100 picoseconds, while droplet epitaxy quantum dots extend their coherence times to 350. And I have to say that actually I've seen myself a dot with coherence time as long as 800 picoseconds as well. So yes, so I don't think we should have any doubts that droplet epitaxy quantum dots are way superior compared to SK quantum dots, and I believe actually this is the way forward within the quantum emitter field. Okay, let's move on. So initially in our research, we started with 900 nanometers quantum dots. These were SK quantum dots. And I will show a couple of results there. The interesting thing is that in this type of quantum dots, the fine structure splitting tend to be small if we pick a dot which is emitting at 885 nanometers. Not sure why that happens, but it's a rule of thumb that, if the emission is close to this sort of value, then the fine structure splitting is going to be smaller. Then we kind of extended our emission wavelength to meet the O band in telecom within the same material system. But here, generally, exciton spin splittings actually they were quite large. But yeah, obviously the natural way was to work and extend the emission wavelength of the quantum dots towards C-band, mainly because of the fact that we could transmit the information on way larger distances. And therefore, in here, basically we had to figure out something else. We changed the material system. We started working with indium phosphide. We also changed the growth technique, moved on to MOVP, spoke with Sheffield, and basically ended up with telecom C-band quantum dots grown by droplet epitaxy. And this is a typical spectrum showing some sort of dot emission at around 1550. So these spectra are slightly more complicated. However, still, we are able to define our exciton and bi-exciton transitions together with positively and negatively charged excitons as well. So there are two ways of how to excite and manipulate our photons actually from a quantum dot. We could obtain our photons by optical excitation. So essentially what we do, we shine a laser with a wavelength which is lower than the expected emission energy from a dot. And this is the way how we generate two photons in our quantum dots. Or there is a more practical way. Basically what we could do, we could design our quantum dots within the PIN structure, and essentially by bending the conduction and valence band, we could manipulate how many carriers will go into the ground state of the dot and how many recombinations we're going to achieve. So obviously, this is way more practical because for real life applications, what we wouldn't like to kind of have another external laser kind of shining on our device to generate some photons. We would like to kind of have everything compact and nice and neat. So our entangled LEDs, first developed at 900 nanometers, looked like this, that we had our quantum dots embedded in gallium arsenide in between two Bragg stacks and doped layers P on top, and then on the bottom we etched a MESA, and then we added some contacts. And essentially we were able to obtain a typical emission just like that. So again, fairly simple process, well, not so simple in real life as always. But for this type of material, we were able to present sub-Bostonian statistics of the quantum dots. This is the second order correlation function measured for a quantum dot at 900 nanometers. And you can clearly see that the emission is anti-bunched with the G2 less than 1. We've got the fidelity, entanglement fidelity, way over 0.5, which is the critical value. And then we also have photon indistinguishability, well preserved above the threshold level. And actually, I wanted to point out here that this is a MESA which is biased, and you can see actually all the quantum dots glowing within our MESA. So what we do later on, we select actually what we want to work with, and we extract the photon only from individual quantum dots. So as I mentioned, we managed to get our quantum dots emitting at 900 nanometers, and we showed that we can achieve quantum teleportation over 1 kilometer in a fiber with the high fidelity. Then we did similar exercise. We moved everything to the O band of telecom bands. And then the next obvious step was to repeat the same stuff in telecom C band. So this is all what has been done. But obviously, there are always important steps and little improvements that we still need to make. So what I wanted to focus here a little bit longer is the first quantum LED operating at the C band. That was a pretty big breakthrough a few years ago. And this is a structure that we've used, our quantum dots, again, within the Bragg stacks at the bottom and top, biased, and this is the SEM image. So we had basically several MESAs surrounded by bottom contact. So these devices were fully compatible with telecom infrastructure. They had lowest loss in long distance transmission. The dots were symmetric because they had low fine structure splitting due to the growth mode chosen. And the important bit is that actually some people say that, yes, but these quantum dots, they only emit at very low temperatures. The truth is actually that for this type of quantum dots, we managed to get non-classical photons up to 93K, which is actually way above the nitrogen temperature. So this is a feature which we found actually only for this material system. The gallium arsenide doesn't emit actually at that low temperature. Well, it doesn't give us non-classical photons at that high temperature. Again, couple of examples at 45, 44K, electroluminescence. These are our quantum dots. This is the top contact. A spectrum coming from these quantum dots. We've got our exciton and autocorrelation function at 44K, and then comparing with 8K above band excitation. Again, the spectra look very similar. The G2 goes down to 0.18, so actually there's not that much difference. So this is all kind of nicely working. And again, another slide showing that they have amazing, very long coherence times under non-resonant excitation. We used Michelson interferometer to measure such coherence times, and essentially this is an example of a lifetime of a dot with 1.65 nanoseconds, and then this here, the coherence time for this particular dot is 1.6 nanoseconds, which in total gives us the ratio, the sweet ratio of T2 to T1 of 0.3, which is actually quite unique under that type of excitation. So what was the next step? The next step was to implement those devices and kind of see how they behave in real-time, real-life operation. So quickly here, just to show you that for this sort of experiment, we chose our O-band device with CW operation. We were sending some photons over the metropolitan loop-back fiber, which was 18 kilometers long. So this was coming from Toshiba, from our offices, down to Cambridge University and back. And essentially, we run such experiment for seven days continuously, and we managed to get the entanglement fidelity above 90% over 7 days, which again is a really great results. Yes. And then obviously the next step was, okay, fine, that was done with CW excitation, but we need them to be running in pulse mode. So this is our next generation of devices. This time, C-band in indium phosphide. We had to gain a little bit of knowledge about RF, and basically this is how the device looks like. We had to kind of become way smaller. So essentially that was, we wanted to be simple. We wanted it to be very simple. So essentially this is the MESA, the bond ball right on top, the P-type contact here, N-type contact, and then in all those little pillars around, you've got quantum dots which are emitting spectra just like this. And then based on that, basically we use those transitions to generate simple 1 gigahertz entangled photon source. I'll skip that. This is how our actually fiber looked like. So these were sent over 15 kilometers between physics department and Toshiba. Again, this time that was slightly different because the source was operated in the lab, and the qubits measured locally by SNSPDs, and the partner was sent to the deployed detector to APDs at Cavendish. And obviously we had to kind of synchronize everything to be compatible with 1 gigahertz clock. And again, I don't have much time, but I want to just flash a couple of pictures of our next steps. So I mentioned before that these devices, you know, they emit at different directions. So what we need, actually, we need to extract every single photon, ideally coming from a quantum dot. So there are a couple of things that we need to do. We need to kind of lower the density, and we need to access only one single dot without any kind of background emission from other surrounding dots. And also, a beneficial thing would be to kind of have some sort of Bragg reflector that would direct, you know, the dots emitting in different directions towards the top. So there are a couple of ideas how to proceed with this. So the basic thing that was planar cavity, but this is not good enough. We could actually use this planar cavity. We could etch a pillar around. Well, that also has some advantages and disadvantages. We also tried using micro lenses to enhance emission. And another method was to use open cavity for enhancement of the Purcell factor and optimal alignment and tunability. These are all fairly complex. What we ended up with eventually is so-called circular Bragg grating. This is a device which you can see in the picture. So this is a fairly complicated device because we've got a slab of 200 nanometers with quantum dots inside and a sacrificial layer. And then actually what we do, we take that wafer, we bond it to the host wafer, just as in this picture here. And then we remove the bottom of the wafer where the dots were grown. Once this bottom of the wafer is removed, the sacrificial layer is removed, we pattern our membrane with circular Bragg gratings, and essentially we end up with a dot right in the center pillar of the dot. And essentially, I also forgot to say that actually the bonding material is gold, which is also highly reflective. So we've got mirror from the bottom. The rings are also acting as a mirror at each side, and that gives us humongous increase in efficiency. So we did our simulations, but I think the most important are the real results. So a couple of spectra here of our quantum dots. So this is essentially to show you that you can see that
probably not very clear, but you've got actually quantum dots just emitting in a slab which is not bonded and without the circular Bragg grating. And then if you do the bonding and then you pattern the circular Bragg grating, you get 100 times improvement. We also have faster lifetime, which is beneficial for pulse operation. And quickly, maybe let's skip this. So we've got that done. And then the next step, extremely challenging, is because obviously those circular Bragg gratings, they were pumped optically. We would like to do a bit of craziness and apply some electrical contacts and have our quantum dots emitting on demand within such complicated structure. So fingers crossed, watch this space. I hope the simulations actually show that we can expect actually a really lovely results. However, I believe fabrication here is going to be extremely difficult. So fingers crossed for the coming months or years, we'll see. But just to summarize, I've introduced you to our view on quantum technologies, on photon-based quantum technologies, and shown you that we are working with semiconductors, particularly with quantum dots, which are emitting photons, and then we play with those photons. But from our perspective, what is important to us is the material, the emission wavelength of our quantum dots, how the device is made, how the device is operated, how applicable in real life is the device. Yes, everything just to build a quantum communication network for the future internet. Yes, and I just stress that ELEDs, entangled LEDs, are a highly promising technology with the compatibility, reliability, and simplicity as required per industry applications, and hopefully this is the future. Obviously, there are some challenges, but let's skip that. I hope, in the near future, actually, you'll be seeing that more and more of these challenges are going to be resolved. Yeah, and then a couple of papers just for the dessert. Thank you.
Thank you very much for the interesting talk. So now we open the session for discussion. So questions.
Thank you, very nice. Regarding your circular Bragg geometry, have you thought, or is it possible to consider other geometries which are not circular, for example? Would you expect them to be more efficient, or is this an optimum geometry that you can use?
I believe this is naturally the most optimal geometry. I mean, I can't believe, do you have any particular geometry in mind? I believe that, if a quantum dot emits uniformly in all directions, I think the most natural way is to use circular Bragg grating to reflect at the same time, uniformly from all the directions around the dot. I can't see actually how any other
If you have an array of quantum dots, would that be the same?
Well, that's the thing. For now, actually, we're working with the randomly nucleated quantum dots. Obviously, probably yes. In this situation, the approach might change. I'll tell you actually that what we are planning to do is essentially. Well, we're hoping that Sheffield is going to deliver us at some point, fingers crossed, some lovely position quantum dots. But in the meantime, actually, we're trying to pre-select a quantum dot and build a device around it. So that's another approach. And again, for this approach, probably the circular Bragg grating is the most optimum, I guess, for now. Obviously, with arrays of quantum dots, the situation might be completely different.
Great, thank you.
Thanks.
Thank you very much.
Excuse me, let me just check my understanding. I think you said you needed well-separated photon pulses, okay? So this would correspond to quantum dots in which the particle hole pairs that are injected recombine very quickly. Is that correct? So I would, if that is true, I would just like to say that for quantum computation, I would expect the opposite limit to be desirable, where a single qubit can be, so to say, long-lived inside a quantum dot. Would you agree with that?
You're talking about...
I'm talking about the half-life of an excited state inside a quantum dot, okay?
Mm-hmm.
So you said if I inject a particle hole pair, it relaxes and that gives me a photon.
Yes.
Now, my understanding is that if you have for your application, you need this recombination to be very quick, because then you will have very sharp, separated photon pulses.
Yes.
So the only comment I wanted to make that this seems to be somehow the opposite limit technologically from the quantum computation limit, which would want to have these qubits long-lived so that they decohere slowly. I mean, I don't know if I'm right. I'm just asking.
You're possibly right. You're possibly right. Maybe for the actual computations, the longer lifetimes are beneficial. For now, if we want to transmit the information, as you said, we need sharp pulses within a gigahertz regime, and 1 nanosecond is essentially. I think we reached the maximum with these quantum dots without parcel enhancement. We reached, I believe, 3 gigahertz, the maximum. For faster operation, we unfortunately need some sort of, shortening of the lifetime. But as you said, maybe for other applications that will be beneficial as well. Well, the long extended lifetimes. Yeah.
So more questions? Okay, may I ask,
sorry.
Yeah, please.
Excuse me, may I ask a question? From my understanding is that there is the 2 photons coming from the quantum dot, left-handed, right-handed, isn't it?
Yes.
And you are sending these 2 photons on the fiber in the same direction?
Yes.
And also, you are keeping only 1 photon per pulse? You said that single photon transmission?
Well, to be honest, no. In the real experiment, you've got a beam splitter. 1 photon is sent in one direction, and the other photon is sent in the other direction.
The other direction.
Yes. For the Bell state measurement.
Yeah.
So on 1 photon, we do Bell state measurement, and then on the other one, transmits the actual information.
Yeah, if you code the information into the 1 photon, what happens to the other photon?
Because of the entanglement, because they are entangled, it will be automatically transmitted to the other photon.
In the same direction again?
No, in the other direction.
In the other direction?
Yes.
Will interact with something else before the other photon interacts?
No, that's the beauty. This is the theory of the you can't really break into the quantum networks, right? Because the moment you do something with one of the photons, the other photons will know about it immediately. So you can do this. You can actually only kind of impose the information on one of the photon, and then the moment actually something else is going to happen with that photon, the other photon will know immediately.
That's the question I ask you. You are sending the photon information encoded to the kilometers away.
Yes.
How about the other photon? Where it does go? The kilometers away?
Well, it's kind of wasted, right?
It's kind of wasted.
Yes. Well, it's once the information is imposed, it's wasted. There's
wasted,
nothing. Yes.
Okay.
Okay.
It can't be recycled.
Excuse me.
You know, the question, what I wonder is that if the wasted photon is interacts with something else, the entanglement will be broken with the other one. That's the reason I asked. Isn't it? Am I wrong?
Yeah, I think your thinking is correct, but yeah, but remember that we work with train of pulses, and we encode information not only on one pulse but on the whole train. And again, if one photon from one single pulse basically does the job, it's done, and then another one comes, and then actually this is the one that does the job.
Excuse me, I have to interrupt the discussion because we are already over the time.
Thank you very much.
We can discuss this later.
Yeah, you can discuss it.
Let's thank Joanna once again.
Thank you.
Okay, let's start our session. So our first speaker is Tony Shiroka. The title is there, so please start.
Okay, thanks. So this is a talk which starts with a question and ends perhaps also with a question. We are looking for collaborations for people who can help us to understand some, let's say, non-usual results we found in a nematic topological superconductor. Now, this is work would not be possible without the collaboration of all these people here, in particular Professor Nakajima from University of Central Florida in US, and Gianrico Lamura, my long-term collaborator on CNR spin in Italy. Now, a very short overview of the talk. I go through a very quick introduction just to make sure we are on the same page. So what exactly we mean by topological nematic superconductors. Then we see a special case, which is this one, which really puzzled us a lot. And we go through two types of measurement, transport and magnetometry, and μSR. Now, most of you or some of you might not be even familiar what is this technique. This is very important because it's a bulk technique. So there are many techniques which are nice to study these kind of things like STM or ARPES, but they suffer from the problems of surface, like defects or pinning or other, or local scale too small, inhomogeneities and so on. This is a very good technique for these kind of studies I will show later. And then I spent quite some time in discussion because this is the most important part of the whole talk, basically. So we are going to address at least this question. Do we need another vortex lattice paradigm? And if so, with which we should replace it? This is the main point, okay? Now, first, very quick introduction. I start with this slide. It's not very nice, no pictures, but it's important. In almost more than 10 years ago, Fu and Berg started with a, let's say, came up with a criterion, what we should call topological superconductor. And they came up with two main things. One is odd parity pairing symmetry with a full superconducting gap. These are very important, both. And then the other is that the Fermi surface must enclose the odd number of time reversal and invariant momenta, so-called trim. This is something trivial. You do the mapping of summary surface to see where the momenta lie. So it is not difficult. This other instead is more difficult. By the way, when you see odd parity, most of you will think immediately p-type, but this is not so, because here we are talking material with spin-orbit coupling. Spin is not anymore a good quantum number. We have pseudo-spin instead. So this is something which is not the standard p-type you have in mind, let's put it like this. And then as a subclass of this, we might have sometimes so-called nematic topological superconductors, which is something we have seen here. Only in the superconducting phase, you have the lowering of the symmetry of the electron fluid below the symmetry of the underlying crystal lattice. And this spontaneously broken rotation symmetry is the fingerprint of nematicity in this case. One of the most well-known cases was that of this material here, which you see, sorry. This material here is the bismuth selenide topological insulator, which when doped with copper becomes a superconductor. Now here, I'm not going into much detail, but just to tell you, this is the, let's say, the equivalence between the standard liquid crystal nematic. We have a director and the, let's say, the couples, the Cooper pairs, which have polarized, so to say, Cooper pairs in the material. So this is the ordinary superconductor. This is the nematic one. What is very nice here is that this is some temperature. In this case, I don't know, 0.3 K or something like that. But you change the field. In one case, above the critical field, so high field, you have no modulation at all. But when you go below, you have a modulation, as you see here. And this is important. It's not only modulated, but it's modulated with lower symmetry than the hexagonal lattice. Therefore, this is a good candidate for topological superconductor. Here, I'm not going into much detail what I said, but what is important is this is seen in bulk properties, very important. So one is CP, which you show here, and the other is AC2. So both of these have the same type of symmetry. Now the question which comes after is, do we have similar materials and how they behave? Because with one material, you can say whatever you wish. But if you have more, you can talk about the class. So what they have behave as a class. This is our next slide. We spotted this, it's called calcium stannite. So tin calcium, basically. It's a very promising candidate, but to claim it as a topological nematic superconductor, we have to do the measurements. And then we did some characterization. I will show you more in detail. So it has nothing special, I mean, low TC, but it's important because it's topological non-trivial semi-metal. It comes from this, tin is semi-metal, basically. And then it prevents, I will show, it has a time reversal symmetry, which is preserved, but it has the broken rotation symmetry. I will show you later. What is important for now is this thing here. It fulfills the second condition, because from the Haas-Van Alphen oscillation, we see that this material encloses an odd number of trims, okay? But the question is, does it fulfill also the first condition, which is this, does it show odd parity pairing? And if so, is this also pneumatic or not? If it is pneumatic, how it behaves under applied magnetic field. So we are going now to address all these questions, okay? This is the stage for starting. So puzzling case of calcium stannite with transport and magnetometer results. I will not spend so much time on here, but just to show you the important thing is that it's extremely symmetric, very high symmetric point group, 48 symmetry. You see it from here, I mean, it's a cubic crystal. And then it shows almost linear resistance. When you go at very low temperatures, you see the superconducting transition. What is nice is very narrow. Narrow means this is a good quality crystal, single crystal. What is important also, this number here. It seems trivial, but this is below the TC of tin. Pure tin is 3.7. So this is not dirty tin, just to tell you, okay? And this is also seen in the magnetometry results. Now we go to something more interesting. We do, let's say, magnetotransport measurements. Now, here when you are in the normal state, you see nothing. So this is not pneumatic in normal state. But as soon as you cool down, you see you have a twofold symmetry. We have also, but you believe it's clear to see, you can see it also from the axial polar plot, let's say. What is important is that clearly you see for some directions you are superconducting, for others you are not. And this is indeed seen also here. So AC2 in one direction different from AC2 in the other direction. So we have broken the rotational symmetry of the electron fluid in the superconducting state. What is also important is that now here we don't have time to go in detail, but the curve here is not the usual multi-band stuff which has negative curvature. It is linear here. And more importantly, we can, at least these pseudospins behave. This is a p-type behavior. So it seems that it shows this exactly what we expect, this odd parity pairing. But we want more. So more means we go with a μSR result. Since most of you are not, or some of you might not be familiar, I have to tell you quickly what we mean with this. Muons are just heavy electrons or light protons. Basically, they are unstable and decay. Enter the sample, they are born polarized 100%, so they have all the same direction. In the sample, they persist under the internal field or under applied field. In one case, it's called zero field internal. It's sensitive to even tiny local fields because it has a huge magnetic moment, or gyromagnetic ratio, if you wish. Or in transverse applied field, it's very sensitive to field modulation, in this case, in the superconducting phase. What is very important, this is purely magnetic probe, no quadrupole moment, and this is very, very important. They are homogeneously sampling the whole field distribution in the bulk. This is crucial. And the other thing which is also important, we are talking about the nematicity of electron fluid, and they sit far from nuclei, so we are probing electronic environment. This is also crucial. Now, how it looks like when you do a transverse field μSR experiment in a superconductor. This is a picture familiar to most of you. This is the vortices, how they look like with a hexagonal symmetry. And if you project this, you have the probability density function of fields. So minimum here, you have maxima here, and you have saddle points which are here. Now, what is important is that when you apply, this is the, let's say, the real case. You apply the field in the normal state, you see nothing. All muons see the same field. They don't decay. There is no reason to decay. They are all in phase, same polarization, and they keep it in time. No decay. When you put, let's say, when you enter slightly the superconducting phase, you have large lambda. Lambda is infinite, but then it becomes a bit shorter, then you have some modulation. Therefore, this decays a bit. When you are deep inside the superconducting phase, this decays a lot. The shortest lambda, lambda 0, and this decays the most. Now, this is theory. This is instead the experiment. You see, it's one-to-one. There is no need to comment here. What is very important is that this sharp peak you see here, this is the background due to sample holder. This does not change any. You see, it's just very narrow and always at the same position. What is extremely important so is this one here. By doing the FFT of the signal, we get P of Ni, which is just P of B. So just compare this figure here with this figure here. They are the same, basically. Okay? So just by measuring this, we know that this material behaves as what we expect it to be, just a flux line lattice of vortices. Okay? Now, let's see what we get in our case. This is now more, to do our experiment, since we expect nematicity, we have to come with some clever setup. This clever setup consists in gluing cubes of sample, small pieces of sample, with this way. So this is the 110 direction, the diagonal face, and this instead is the edge of the cube. So by applying the field in this direction, we are in the so-called B parallel configuration. By applying the field in the plane, we are orthogonal with this direction. This is what we call B orthogonal direction, okay? I'm not going to more in detail, but this is just to distinguish the two cases we have measured. And now we go and see what we find in the first case. So now we are applying the field parallel to this direction. Here you see short time scales, nothing happens. But even if you go in long time scales, nothing happens. This is a very long experiment, a lot of statistics, 9 microseconds, if a lot for muons, and basically it's very hard to distinguish who is who. So it seems as we are in the superconducting phase, but nothing happens. Or basically, this is a material which has a huge lambda, because huge lambda means no decay of the signal of mu SR. They are all in phase and stay in phase. Now you go to the other direction. First thing you see immediately is that there is a difference. This is just to check, this is not the main point, but this is just to check the so-called shielding fraction. So it tells you this is a superconductor. We can give also some limit for the superconducting fraction. It's not 0 for sure, it's more than half. But what is important is to compare these two. Now, in the about superconducting phase, we are here, it does not decay, but here it decays. Very little, but still decays. So it's distinguishable from the other case, and therefore we can call this a signature of nematic behavior. Now, let's go further. This is a very important one for the theory. When we do zero field mu SR, we expect nothing to happen. And in fact, nothing happens. But if there were some development of ferromagnetic order, which is a signature of time reversal symmetry breaking, these two curves will differ. These are above and below TC. But as you see, nothing changes. Therefore, we conclude from this experiment, which is nil result experiment, but still very important, we conclude that the absence of differences seems to tell us that this material preserves time reversal symmetry. I will show you that this is very important later on. Now, let's try to summarize what we did until now. So by applying field different direction, we find in one case tiny depolarization, in another case no depolarization. These two allow us to tell there is a breaking of rotational symmetry. This is a confirmation of what we already know from the other measurements. This is local, let's say, local probe confirmation. The other thing is what I just told you, the preserved time reversal symmetry. If you go more into numerical, let's say, details, this is also very important. This is the standard vortex lattice model, and we can know this is the famous Ernst-Helmont-Brand formula, which connects what we measure sigma with what we want, lambda, decay, okay? And from this we can find lambda delta 0. What is important here is this number here. This is huge. I show it also here. And the other important thing is that we have a low T saturation, which is a signature of absence of low excitation. So this is fully gapped superconductor. This is also very important. And finally, we have also this other important result that this M star is measured from de Haas van Alphen, and if you put this together with this formula, we can extract what is NS. And this NS is extremely small. So this is very dilute, very suspicious, let's say, superconductor. Now, all what I told you refers to this sample. We should now try to go to a discussion, put this thing more in, let's say, in, how I'm doing with time. So how much minutes I have? 5, 10 minutes, I don't know. Roughly. Okay, I tried to finish earlier, so we have time to discuss. Anyway, what I wanted to tell here is that what we found here looks already a bit unusual, anomalous, but it's not the case, because if you put these together with the other materials, which also have been studied by MUSR, here we find these, let's say, huge numbers. So by the way, we know also from AC2 what is psi in this case, and we get a K kappa of 60 for this material. The other have also very high values. So what is unusual here are these numbers to compare with the standard ones like niobium. Here, these are 52. Here we have 1,600, or these very, very large numbers. And also what is important is the difference, huge difference between the normal state electron density and the superconducting electron density. These are, here they are different, but not so much different. Here is extremely different. So they are really a different class. You can really touch by hand. Now, the question is, what does it mean? So now we try to put together also with some theory. This is, let's say, a modeling of what we have until now. So by putting together all these experimental results, we can constrain our let's say, models. So not anything will fit. So already from knowing that we have broken the C4 fold, let's say, symmetry, we are left with much less states. So we are left only with 10 states. And we can, since there are not so many, we can even try to check them one by one. And this has been done. What is important is this column here. L means there are zeros in the gap line, you see here, line nodes, point nodes, or even F. F means full, but it's only one F. All the rest are different, which means this is one of the requirements I just have shown here. We need something which should be fully gapped, because this is what the experiment is telling us. And the other is the time reversal symmetry invariance, which I have shown you via zero field MUSR experiments, which tells that this superconducting gap has no complex components. So basically, these are also the pictorial, how it looks like. Basically, only this, let's say, candidate is the good one. okay? And then we come up with this possible gap function. Now you come to the real, let's say, purpose of this talk. The real purpose is why they are different and what can we say about the vortices. So now I'm not going to bother you with those details. Basically, here we are saying that in all these cases, we have some preferred direction which behave different from the other direction. And also in our case, these directions will be different, but the crucial thing is that these, let's say, directions are such that they tell us that these materials are nematic topological superconductors. And I have tried to demonstrate this in both cases. And what is more important, they are all characterized by these unusually large lambda values, which is clearly not corresponding to the normal state carrier density. Therefore, it comes natural to ask, but do these models, do these materials obey the standard Abrikoso model with this single peak and with broad distribution? Yes or no? We are almost sure no. And the question is, are there other possibilities? Probably yes, and what? This is what we are going to see next. Now, I would like to attract your attention to this paper. It's 30 years old, but still relevant. Very, very nice paper. It's called Phenomenological Theory of Unconventional Superconductors. Still has some very valid ideas. What is very valid ideas? OP here means order parameter. So in standard cases, in conventional superconductors, we have one component. Everything is well known. Mixed phase is described just in terms of Abrikoso state. Two-dimensional hexagonal, everyone is happy, and we find this. I have shown you the example. We find exactly what we expect to find. And in this case, we can use Helmut Brandt's formula, which links, as I told already, lambda to psi, to sigma. This we measure, this we find. Everything clear. But now comes the, let's say, the important and interesting part. What happens when you have some unconventional superconductivity? And then this paper tells us clearly we are allowed to have multi-component order parameter, which means different types of vortices can coexist. I'm not a theorist. If you wish to read it, it's very, very nice. It shows you all the possibilities. So symmetry is lowered, therefore everything is allowed, basically. In this case, we can have also, let's say, each order parameter component can produce its own independent topological stable vortice. This is interesting. And they bring an example. I don't know if this applies to our case, but one can be coreless non-axial vortices. Everything is explained here. And now we come to the real, let's say, the last but most important slide. We have been digging around asking if someone has tried something, and indeed someone has tried. And this is a very nice paper. It's not had been published yet, but has very, very nice idea. This is by Egor Babayev and Thomas Wynyard in England, Egor Babayev in Sweden. And they have come up with the same question as us. There are many people who are finding crazy results. Do we make a sense out of them? And the answer is yes. Now let me try to explain, spend some time on this. Now, if you go, here we are comparing conventional with nematic superconductors with more or less similar condition, let's say, same field. I'm not going to explain what, these are low fields, basically. It's complicated, but it's easy. You apply a field, let's say, 1.5 times AC1 or something in the low part. Now, what happens here, you see, there are two crucial results here. First is, this is, let's say, the red curve here corresponds to the red curve here. This is huge, very much broader than here. So we already see that if we have nematic superconductor, we should expect a narrow field distribution. This is exactly what we find, because narrow field distribution, remember, no decay. This is the crucial point. The other thing, this is also the fingerprint of this kind of material, is a double peak. Now we don't observe a double peak, because this requires single crystal highest quality, but we are working on it. Now, of course, you will ask, okay, that's nice, but I don't, I want more. More means why you have one single peak here and why you have two peaks. This is very easy to understand and very nice because it has to do with fundamental symmetries. Here we have only one number which describes the vortex lines. It's kappa. Okay, it's the ratio of lambda and psi, but it's a number. Therefore, we have only one peak. Here instead we have two because they describe there, let's say, we don't have any more vortices, but they say we have skirmin, or even better, skirmin stripes, especially at low fields. When you go to high field, this model then converges to the standard one, which means standard one is the standard vortices. There, it's hard to distinguish one case from the other, but at low fields, we can distinguish the two. And what is more important, where this double peak comes from? This is very easy to understand. Look here, we have let's say these are stripes. This is stripes of skirmins, but there is an inter-skirmin distance. This is one length scale, and there is a stripe periodicity. This is another length scale. And when you put these together, it comes naturally, it's come obvious that you should have also two peaks because you have two distributions, basically. So this is our, let's say, best knowledge or best effort to explain our crazy results. But of course, I'm open and I will be willing to have also your feedback on this, let's say, issue. And what is important is that what we have shown here is for one case, but this applies to the whole class. So I expect this to have further developments later on when people start to study more seriously topological nematic superconductors. So this brings me to the last slide. So just to summarize, we have seen with μSR magnetic transport measurements on this material, on calcium stannite, that we have a broken rotational symmetry. Second, we have a preserved, from zero field μSR, preserved time reversal symmetry. Then I have shown you from the numerical, let's say, result that this is fully gapped. And we even tried to figure out what it is, and we have come up with this one. Of course, all this is still work in progress, but it should not be considered as a last word, but as a starting point for addressing all these very interesting and unconventional properties of the mixed state of nematic superconductors. So thanks for your attention. So I leave these, perhaps it might be.
Yeah, thank you very much. Remarkable. Questions?
So thanks for this interesting talk. The multi-gap superconductivity was considered to be a mathematical trick of no interest for about 1958, the Bardeen, and even after magnesium diboride, many people started to say that it was just a electron-phonon coupling. On the contrary, Kresin and myself, and we showed really that it's completely different physics from single gap superconductivity. And Baba have shown since the early time, the fact that you have this kind of a complex superconductivity. I think that your results are really, really compelling, really make a point.
I hope we open a new, let's say, a new field of study.
Because
people are more
the people understood
willing
that
to study this.
When the BCS formula is wrong, so the correct formula is Bogoliubov form, and this was considered not interesting. So only in this meeting we had many other talks.
After some years, people realized that
it's completely different physics. That is important.
I thank you for your comments. Yes, it's very pertinent. More questions? Please. I expect some nasty questions from this guy.
So what sets the two length scales? So you have two kind of size.
You mean in this picture here? Sorry.
Yes.
Here?
Yes.
This case, this is a good question. They claim that this is very difficult, but they have done numerical simulation in, let's say, reasonable cases. And to answer your question, what sets is the applied field. So the higher the applied field, the more squeezed these become, until the two scales become just one, when you are very close.
But even if you do numerical simulations, you have to start with an Hamiltonian with two different numbers.
You can read this paper, it's very short. It's a PRL, basically, but they have also a long version. It's not yet published. It's still, where it is, here. So this paper, I can give you it's easy to, and they show exactly what they do. They take V1, V2, and then to cover the plane tessellation, and then start to put vortices and see these skirmings, let's say, and then start to see what you get. But this goes beyond my, let's say, field of expertise. But this is a short paper, easy to read, very clear. So it really addresses this problem. So the question in their paper, so the title of the paper is how muons, what is the muon stopping profile in a topological nematic superconductor? So exactly this question. But I don't know exactly. What I know after reading the paper is that basically the density of these skirmings and their periodicity depends essentially on the applied field. It might have to do also with some anisotropy of the material. But I don't know how exactly they try to model this. But as I said, this is still a very virgin ground, open field. We have more questions than answers. So I try to be honest, just showing what we get, and trying to attempt to answer questions. Our paper, by the way, stayed by referees for almost 1 year because they were always back and forth. When you try to publish something unknown or unusual, then you get this kind of reaction, let's say. It's not something, okay, everything known, next paper. No, we have to wait for a long time to repeat measurements, to grow another crystal to make sure this is exactly what we claim it to be. Anyway, thanks for the question.
Okay. Have a minute for comment? Short or not? Times the next talk, or maybe very quick. Okay, okay, thank you for a beautiful talk. Just one brief comment. You remember the talk of Christina? And this is exactly sort of like
we already had some discussion with the chair about this thing, but he now have seen exactly the results. So, okay, we can discuss even later. Thanks.
Sure. Well, thank you very much again. And don't go. Okay. Now we have our next talk online, and our next speaker. Where is our next speaker?
Our next speaker is Benoit Fouquet. He'll be talking to us about magnetic freeze-out and anomalous Hall effect in zircon telluride. Go ahead, Benoit.
Okay.
Thank you. Hi, Erika. Hi, everyone. I'm sorry not to be with you. I hope you have good time in Turkey. So the topic will change a bit. Here, the idea is to see what's going on when you apply a big magnetic field on a three-dimensional electron gas system, and to try to probe and maybe to induce a new state of the matter. So I will give you a bit of introduction because I guess this is maybe a topic that most of you are not so familiar with. So the idea is very simple. You start with an electron gas system, you apply magnetic field, so you know that the electrons will orbit. And as the magnetic field increases, the size of this orbit will decrease. And at some point, it will become comparable with the Fermi wavelengths. This is the so-called quantum limit, where you can expect that the dynamic of the electrons will be changed by the quantum nature of the electron, or you can even have a field-induced state, a new field-induced state which can emerge. A well-known case is, of course, the quantum Hall effect and fractional quantum Hall effect in 2D. So this is this limit that we want to explore, and this is a definition in the in the real space, but you can do the same definition in the K space. You start with your three-dimensional Fermi C, you apply magnetic field, you have Landau quantification, and as you increase magnetic field, you have less and less Landau level which are occupied, up to the moment where all the carriers, the charge carriers, are here in this lowest Landau level. And the question that we want to explore is does this change in the electronic spectrum change something to the ground state of the system? So if you take a piece of metal like a silver or gold, for example, where you have 1 electrons per unit cell, the field that you have to apply to reach this quantum limit is very large. It's about 10 to 5,000 Tesla. So there is, of course, no way that you can explore this physics in metals. But there is a way to overcome this difficulty, is to work with systems with a large Fermi wavelengths. That is to say, system with a very low carrier density. So what I mean is systems which are still metallic, but which have a density which is 5 orders of magnitude smaller than usual metals. So this is what we call dilute metals. And for this system, we can, using a field of few Tesla, explore the ground state of these 3D metals pushed in the quantum limits. So if you're interested by this question, you quickly realize that there is 2 types of systems. The first one are semi-metals, which is essentially a system where there is a hole and electron pocket which overlap. And there is actually many systems which can satisfy this low density condition. Especially with the emergence of new topological materials, there is many new materials which are good candidates. But the system that we know for sure that something happened in high field is graphite, which is a semi-metal with a hole and electron pocket which are elongated along the C-axis. And when you go beyond 10 Tesla, beyond the quantum limit, we have found that there is a field-induced transition. So this is here a color map of the C-axis resistance. So we put the field and the current parallel to the C-axis, and you see that at very high field, there is an insulating state which emerges and which is generally attributed to the formation of a density wave along the magnetic field. And the basic reason is that when you start with your three-dimensional electron gas system, you apply a big magnetic field, essentially your electrons becomes 1D, the spectrum becomes analog to a 1D, and there is 2kF instabilities. And this is where in graphite we find this electronic phase transition. I should mention that this is transport measurement, but we have now did several studies of ultrasound, but also specific heat measurement, which confirm the thermodynamic nature of this transition. So these semi-metals are very interesting to look at. Another class of systems which are, of course, very interesting to study is dope semiconductors. There is here, of course, a big difference with semi-metals. Is because the metallicity is here the result of a doping process. So you add some impurities, they ionize and they give an electrons. And what we are particularly interesting is dope semiconductors where the metallicity is actually protected down to a very low carrier density. And to have this condition, you essentially need to have a very large Bohr radius, and there is two ways to have a large Bohr radius, either by working with systems which have a light mass. So this is the case of zirconium tellure 5. I will show you. It's a Dirac material where the mass is super light, or to work with systems with a large dielectrical constant, such as lead telluride or STO. And so if you take a system like that, where the metallicity is protected down to low carrier density and you apply magnetic field, generally this is what's happened. So this is here the case of indium arsenide. You have here the resistivity as a function of the magnetic field. You see here quantum oscillations. Above this field, all the carriers are in the 0 minus Nodal level. And you see that you have a huge increase of the resistance, which is accompanied by a drop of the carrier density. And this is generally understood as the so-called magnetic freeze-out, where as you increase the magnetic field, the wave function, the in-plane wave function is shrinking with the magnetic field. And essentially, you go on the insulating side of your Mott criteria. So today, now I will essentially discuss the case of zirconium tellure 5. And one reason that zirconium tellure 5 is interesting is because the mass is light, but also because there is recent measurement which suggest interesting result. The first one is probably in this Nature paper, where people found that when you reach n equal 1, which is this peak here, you see that the Hall effect has a plateau. And above this plateau, there is a metal insulator transition observed here, which is marked by the existence of these crossing points. And this paper raises the question of, can we observe in three-dimensional system a quantized Hall effect? So this was the first motivation to us to look this result, and especially we were interested to try to understand the nature of this metal insulator transition here. And the second observation did by the Princeton group is the observation of anomalous Hall response. So now you're looking the Hall effect, and you see that the Hall effect displays a typical behavior that you observe in ferromagnetic metals. And of course, here what is striking is that zirconium tellure 5 is not a magnetic material; it's a diamagnetic compound, and there is no localized spin. So the question is, how can we have anomalous Hall effect or a Hall effect which saturates in absence of magnetism? And there is some idea that if you apply magnetic field, you can split the band. And if each bands have a non-trivial Berry curvature, you can have the emergence of anomalous Hall response. So then the question that we want to answer, and that I will discuss in this presentation, is first the nature of this metal insulator transition. Is it due to a spin density wave along the field, as it has been proposed in this paper, a bit like in graphite, or is it due to a magnetic freeze-out scenario? What is the origin of this anomalous Hall effect? And then try to connect the two observations. Okay, so this is, before to show you my result, I just want to quickly thank my colleagues. This is an effort where we combine transport measurement that we have done in Paris, but also in Toulouse for the high field measurement. But also we did optical measurement to extract the dielectrical constants. And samples have been grown. We have sampled from 2 different places, one from Brookhaven and one from the EPFL Lausanne. Okay, so first, let's discuss the resistivity versus temperature. This is here the result for the 4 batch. We cover a pretty large range of doping, which go from 8, 10, 15 to about 7, 10, 17. And the resistivity display always the same behavior. It has a peak. And the peak is actually separate a regime where at high temperature, the system is Hall-like. The Hall effect is negative, and here the Hall effect is positive at low temperature. So there is a change in the type of carriers, which has been actually beautifully observed by laser photo emission as a function of temperature, where you see that the Fermi energy shift from the valence band to the conduction band. So at low temperature, what you see is that the Fermi energy is in the conduction bands, and you see that this system has an extremely small gap of about 10 millieV. And so this is interesting because it tells us that actually the Fermi surface is pretty simple. It's essentially one pocket at the gamma point. And combining the Hall effect measurement and the resistivity, what you find is that actually the mobility of the carriers is extremely high. It's about 1 million. So the message here is that you have just one pocket at the gamma point of high mobile electrons. So then what we did is we apply magnetic field. The first thing that you observe is quantum oscillations. This is here the trace of the quantum oscillations for the three batches that we studied. What is remarkable in this sample is that the last quantum oscillation occur at 0.3 Tesla. So that means that the quantum limit in this system is reached at 0.3 Tesla. And then we did angular dependence to track the anisotropy of the Fermi surface. And you see that the anisotropy is pretty large. Actually, the mass anisotropy is about 250. So that is to say that the Fermi surface of zirconium telluride is one ellipsoid, one extremely elongated Fermi surface along the b-axis. And when you apply the field along the b-axis, the cyclotonic mass is pretty low, is about 0.01 m0. So now let's go to high field and let's see what's first happening in the resistivity. So this is resistivity as a function of magnetic field for the 3 batches. This is measurement down to pretty low temperature, the dilution temperature. And what you see is that you see here the quantum limit, which is at 0.3. And then you see a crossing point above which you have this insulating behavior. We can find the crossing point at 3.2 Tesla, which is about 10 times larger than the quantum limit. For S1 samples, then it moved to about 7 Tesla for S2, and then 30 Tesla for the sample S3. So if you combine this data, you can extract the 2 field scales, the quantum limit field scale and the onset of this metal insulator transition. And this is what I report here. The cycle are the position of the quantum limit as a function of the carrier density. I also include the data in the literature, and the square correspond to the onset of the metal insulator transition. So regarding the quantum limit, this can be well understood once you plug the anisotropy deduced from the quantum oscillations. And for the metal insulator transition, what we did is we used the standard magnetic freeze-out theory, which essentially tell you that when you're at high field, the in-plane Bohr radius has to be changed by the magnetic length. And if you know the mass coming from the cyclotonic studies from quantum oscillation and the dielectrical constant, which is that we measure through optical measurement, we can actually compute the threshold for this metal insulator transition, and this is the black line. And what you see is that this actually gives us a pretty good description of the onset of the metal insulator transition. So this is the first conclusion, that the high field transition in zirconium telluride is probably related to the magnetic freeze-out effect that we observed in other doped semiconductors. But there is two differences. The differences is that the value is remarkably high because the dialectrical constant is remarkably high in this system. So now we also studied the Hall effect, and here we had a surprise because, as I told you before, generally the magnetic freeze-out is associated with a drop of the Hall carrier density. But here what you see is that when you go to a low temperature, you have a sign change of the Hall effect. And this, for us at the beginning, it was really puzzling. Everything happened as if there was a Lipschitz transition induced by the magnetic field as you go from electrons to Hall. And then we decide to also measure the thermopower, and we actually find the sign change of the thermopower. So it's really something which is a strong result, reproducible both for the electrical but also for the thermoelectrical measurements. And then we dig a bit actually in the literature, and we actually find that in indium antimony at very low dose, there was a report of a similar sign change of the Hall effect. This is here the absolute value of the Hall number as function of the magnetic field for a carrier density of 21014, and you see that at low temperature there is a sign change. And the way that this sign change is understood
Benoit, something happened. We can't hear you. Are you muted?
Oh, sorry. Excuse me. Sorry. So I don't know. So I was saying that we dig in the literature and then we find early reports in indium antimony which also show a sign change of the Hall effect. This is a measurement here of the absolute value of the Hall effect as a function of magnetic field. And as you can see, at low temperature, there is a sign change. And the way that this is generally understood is due to a skew scattering, which is due to the asymmetrical scattering of the spin polarized electrons by ionized impurity. So again, here, when you are in the quantum limit, you are in n equals 0, but you have also the Zeeman energy. So you're at high field. When you are in the 0 minus Nodal level, your charge carrier are spin polarized, and they can be scattered in an asymmetrical way by ionized impurity. And there is actually an expression which quantifies this skew scattering Hall conductivity, which is set by the number of scattering centers, the G factor, and the value of the gap. And here it's interesting to look at numbers. In our case, in zirconium Taylor 5, we got a value of 1 ohm centimeter minus 1, which is actually pretty large. But in indium antimony, this is 4 order of magnitude smaller. And the reason that it is 4 order of magnitude smaller is because first, the carrier density is much larger in zirconium Taylor 5. And second, that the gap in zirconium Taylor 5 is much smaller.
In 3 minutes, we need to take questions. You have 3 minutes till questions.
Oh, okay, but I'm done. So essentially, what I show you is that zirconium Taylor 5 is an extremely interesting material because it's the Fermi surface is extremely simple. The Fermi surface is at the gamma point. The gap is extremely small, and the consequence is that the mass is extremely light. On top of that, there is a large dialectrical constant, which means that in this material, even at 0 magnetic field, the metallicity is protected down to extremely low density, which is quite unique. And then we apply a big magnetic field. We reach this quantum limit. I show you that there is a metal insulator transition, which is most likely associated with the magnetic freeze-out effect, which is in good agreement with with the absence of thermodynamic measurement signatures at the critical field from this paper where they find no evidence of ultrasound, and from this paper from NMR measurement. And then I show you that actually the Hall effect has, however, a distinct behavior than the usual doped semiconductors, because there is a strong contribution from the anomalous Hall contribution, which can be either due to intrinsic property as proposed earlier, but it can also have an extrinsic property associated with the skew scattering. So with that, I will stop and I will thank you for your attention.
Do we have questions from the audience?
So thank you for your talk. So I'm not sure this is a proper question to ask to you, but I'm working on thermoelectrics, and this can be like a thermoelectric project, right? And do you see any chance to be the performance can be improved further by just tuning some properties?
So yeah, it is true that this material has a pretty large thermoelectrical response, and also Nernst signal is pretty large. And it is true that the thermal conductivity also is a bit small. So I'm not sure. The thing is here we're working at a very low carrier density. Yeah. So generally for thermoelectrics, people try to work at 1019 or 1020. So the thing is, I don't know how doable it is to dope the system toward this regime of higher doping, where the conductivity will be a bit better. So I don't know if you have some application in mind, but so I would say at the moment the problem is that the resistivity is still too high. Even though the mobility is high, the problem is that the carrier density is too small to have a higher conductivity.
Yeah, I see.
So probably the best will be to try to go to higher doping.
Okay, thank you very much.
We have time for a couple more questions. Are there more questions?
Maybe I have a question.
But Benoit, I have a question. Because you're at very low carrier density, disorder should matter. And so, you know, where does that come into your system? How clean is it? What's the mean free path? That sort of thing.
Yeah. So this is a good question. So here is what I say, that the mobility is extremely high. It's about 1 million. Of course, the carrier density is small. So about the mean free path, I think it's about like 10 micrometer. But still, you're right that disorder play a role because there is a potential fluctuation. Okay, we shouldn't imagine that there is the electrostatic potential, the electrostatic landscape vary a lot. And this potential fluctuation, I think, affects the fact that this transition here is not a strong insulator. Okay, so the way that it works is that you know, if the system was perfectly 1D, you know, it should be a sharp. It would be 1 over square root for the density of state of the Landau level. In fact, there is a broadening of this density of state, and there is also a broadening of the impurity band. And this is, I think, the reason why this system is not a super strong insulator. Okay, this is why actually the resistivity saturates. So actually, I have maybe a sketch here. I remove it for sake of simplicity, but this is here a sketch of the density of state. This is the conduction valence band, conduction band. And essentially, when you have this metal insulator transition, what's happening is that you have an impurity band which go below. But the thing is due to disorder, to this potential fluctuation, there is an overlap between these two bands. And this is why actually the resistivity doesn't saturate. Okay. So there is disorder, and this impacts the nature of the insulating state.
Thanks. We have a question from the audience.
Yeah, I have one question and one comment. So this system is, strictly speaking, off-stoichiometric, meaning that you can completely suppress the transition if it's 1.0, 5.0. So how does that impact the observations? That's one question. The other question is,
can you give a comment on electron-phonon coupling?
Yeah, so for the first question, I think you're totally right that we are talking about a doped semiconductor. So there is a bit of tellurium or extra tellurium or vacancy of tellurium which give you these electrons. Okay. But this is the same question that asked Erika, that this extra tellurium will give you a disorder and will change the landscape, the electrostatic landscape. But we have to live with that, you know. But this potential landscape affect the nature of this transition. But still, there is a transition. Okay. So now about the electron-phonon coupling, I don't have much information about about this system. Actually, I don't know much. I can just say that I'm working at very low temperature, so I don't really think that phonon play any role in the for this. You know, I'm working at sub-Kelvin temperature, but I don't have any information. Except if you have a specific question about, you know, what do you want to know? You want to know the amplitude of the electron-phonon coupling, for example? Or I don't have this information. I'm sorry.
Yeah, that's fine. Thanks.
Okay. More question? Okay. Did you come, Susan? Not?
Let's thank our speaker again. Thanks, Benoit.
Merci. Thank you. Thanks a lot, Erika.
Thank you.
And we have to ask the tech people if our next speaker arrived. Okay, so unfortunately our next speaker did not arrive, and you have something to say.
Yeah, okay. Okay.
Okay, so we have a break until 4 o'clock.
Yeah, I thought she was coming.
No, she's an organizer.
Huh?
She's an organizer. I thought she would be here. Yeah.
And she's not.
Yeah. I thought Yvonne would be here too. Your microphone is on.
Alexander is using our next speaker. And okay, Alexander, it's great to have you here with us. It's a pity, not personally, but welcome, and please go ahead.
Thank you so much, Valery. And I would like first apologize for not being in time and for yes, I'm sorry for that. I would like to talk about our recent work that was done together with my brother, who is the researcher at Landau Institute for theoretical physics at the moment. I'll talk about transport and superconductivity in ferroelectric metal. Oh, all right. And mostly I will be talking about the particular example of strontium titanate. And here is the phase diagram of that material. It has the undoped strontium titanate is an insulator with about 3 electron volts of the gap. So it's here on this phase diagram. This is temperature, concentration, and some other parameter that might be kind of the substitution of this. I would say that might be a percentage of the substitution of some of the strontium or titanate here. I would not specify in particular. And this is the complicated phase diagram of this material under certain conditions. Right, so it is insulator. Then if it's doped, it might become a metal. If it's doped even further, it might become superconducting. There's a superconducting dome with kind of some shape in it. The shape is associated with the fact that strontium titanate might have actually has several bands, and by increasing concentration, one fills the bands. And then actually filling one and then filling another affects the shape of the superconducting dome over here. Now, changing the material properties in other way, let's say applying strain and so on and so forth, one can reach a ferroelectric state in this insulating state of this material. Right. However, one can reach a situation when the ferroelectric state and superconducting and metallic state might coexist. This is the region of material parameters. And further, I'll be talking about the metallic superconducting states, as well as very quickly, and as well as our interest is in this region. So I'll be focusing then later on this region where we have the overlap of the ferroelectric state and superconducting state in this material. So first of all, how can it happen, right? So one might think of the situation that there is no enough of free electrons in the metallic state to kind of screen the ferroelectric polarization in material. So increasing concentration further, we go from the insulating state where you have ferroelectric polarization towards the metallic state, but the concentration of electrons is not enough to screen ferroelectric polarization, and you still have unscreened dipoles there. And there's a window of parameters where you can have coexisting kind of Fermi C that coexist with the ferroelectric order as a background. Somewhat very well, you might think of a situation where you have a magnetic system with conducting electrons that kind of, due to exchange interaction, fill the cloud of the localized spins on the background. So what is strontium titanate is known for, that it's superconducting, as I said. It's known just from the discovery of superconductivity, and it was the first example of unconventional superconductivity, because you see that the superconducting order parameter or superconductivity start to exist at very low doping, at very low Fermi energy. You see it's like about 1 milli-electron volt. So this was very unusual at the time, and there's actually no explanation well established or for the superconductivity in this material. And then what is also important, as this material is very close to the ferroelectric transition, the dielectric constant is huge. So we might expect Coulomb interaction to be suppressed, not screened, but suppressed here. And as we are closer, as the material is close to the ferroelectric transition, and there are associated transverse optical phonons. So this transition is structural transition. Of course, there are transverse optical phonons with the corresponding soft gap away from the transition and the speed of sound. Now this is the Debye energy, which is much, much larger than the typical Fermi energy and typical energy scale of the phonon. So we are in the superconducting state. We're in the situation when the Fermi energy is much larger than the Debye energy of phonons. So that is the kind of prehistory. So what is also puzzling here is that this material in metallic state, the resistivity follows the T-square dependence. T is the temperature. So you see, if we substitute, let's say, titanate with niobium, this material becomes metallic. So that is actually one of the. So we are like on this scale, and this follows the T-square dependence over the actually large interval of temperatures. This is not yet understood as well. One of the possible explanation for that is related to electron interaction with transverse optical phonons. Since they are transverse optical and the material in metallic state is centrosymmetric, then there is no possibility for the electrons to interact with the first power of the polarization that corresponds to this transverse optical phonons. So the interaction, the electron-hole interaction, electron-phonon interaction is proportional then to the second power of the displacement vector of the transverse optical phonons. And this is the corresponding electron-phonon interaction Hamiltonian. So these are the electron creation annihilation operators. This is the operator of the displacement vector of transverse optical phonons, right? And I've just written it explicitly through the bosonic operators here. This is the dispersion relation of transverse optical phonons. This is the soft gap that softens at the vicinity of the ferroelectric paraelectric phase transition. This is the typical material-dependent parameter here. And just to compare with the Froelich type, where we used to work with, this is so the divergence of the polarization of the displacement vector is obviously 0 for the transverse optical phonons, which is not for longitudinal acoustic phonons, for example. And this Hamiltonian, or this particular interaction of electrons with transverse optical phonons, with a pair of transverse optical phonons, was proposed a long time ago to explain superconductivity in strontium titanate, then later by Epifanov, Levanyuk, and Levanyuk to describe T2 square dependence of the resistivity. However, it was forgotten for a long time, and only recently, actually stimulated by recent experiments, this was reinvestigated, and the model of the electron interaction with a pair of transverse optical phonons was kind of started to be studied again by these groups, by Maslov, Hegelman as well. And now, if we just look into the electron interaction with the two phonons, right, with two transverse optical phonons, and look into the self-energy correction to the electron green function, though this is the first order approximation correction to the electron green function, which would give us just the transport scattering rate. And obviously, since it's a two-phonon interaction, then it's obviously proportional to the T square. What is more important or more interesting is that the prefactor here is 1/tau is kind of a material-dependent parameter, and this 1/tau does not depend on the statistics So it can be applied for temperatures below and above the Fermi energy. So quite universal for quite large interval of temperatures. And this is the corresponding resistivity, which is scales obviously T2 squared. These are just known results. I'm just repeating what is known. And this model was applied to explain superconductivity in strontitanate. So if one looks into the Cooper channel for the superconducting instability and consider the two-phonon contribution to the Cooper channel instead of just the usual one we used to due to acoustic phonons, right? Then in the situation when the dBi frequency is much larger than the chemical potential, in the limit when the interaction parameter is small, then we can apply the theory of Garkov and Melik-Barkhudarov, assuming that the energy corrections to this integral can be thrown away. Right, high energy corrections can be thrown away in the renormalization of the interaction constant, and then obtain the critical temperature for the superconducting instability where there is an interaction parameter that depends that has kind of logarithmic term, which depends on the gap, soft transverse optical phonon gap, right? In addition to Bloch-Grunizing temperature. And why it might explain the superconductivity in this material is that that it can first of all explain the unusual isotope effect in this material, right? So we know what is the isotope effect and in usual superconductors, and here it is. It becomes the opposite to the conventional superconductors, right? So we have the enhancement of the TC as the frequency of transverse optical phonons goes to 0. Now that is all what was known before us. Now we are looking into the situation where we have overlapping ferroelectric state and superconducting state over here. So the previous theory was trying to explain this region in the phase diagram. Now we are going into that one. And we were motivated by the recent experiments by Rishao et al. We're here. This is the resistivity versus temperature in strontitanate, which is tuned into the region where ferroelectric and superconducting state might overlap. And by lowering the temperature, they first see the signatures where the ferroelectric transition appears. And then lowering the temperature further, they see the superconducting transition. Now, this jump in the resistivity can be associated with the jump in the dielectric susceptibility, which is measured in the insulating state of this material, right? So we can make this material insulating. We can reach the ferroelectric state there and see at which temperatures the ferroelectric state appears. And this temperature coexists with this unusual resistivity contributions in the metallic state of the doped material. And that is why they think that this is the onset of the ferroelectric transition at the background, which affects the conducting electrons. And then lowering the temperature further, these conducting electrons become superconducting. And all of this happens kind of in the with the ferroelectric state at the background. And below the ferroelectric transition, you see that the resistivity follows kind of the linear dependence in some region of material parameters. Right. So what we propose that in the ferroelectric state, obviously there is spontaneous ferroelectric polarization, and there are fluctuations around it. right? And we are also looking into the two-phonon interaction here. So polarization, ferroelectric polarization, assume follows the square root dependence on temperature, which increases as we go below the temperatures of ferroelectric transition. And it is known that the phonon gap in the ferroelectric state follows the ferroelectric polarization. It also increases as we go away from the ferroelectric transition. So this is our model over here. If we now write down the the electron phonon interaction potential, that is what we have here. So just to compare with the acoustic phonons over here, right? So first of all, what we need to know that these phonons are soft. Their dispersion relation is has a gap which softens the ferroelectric transition and then hardens as we go away from it in both sides. Second, the interaction potential is anisotropic, which means it is being suppressed at wave vectors of electrons which are parallel to the ferroelectric polarization. So that means we have to go further and take into account two phonon interactions. They are always there. So once again, two phonon interactions are always there. We always have p squared term. But in addition to p squared, in the ferroelectric state, we have a linear product, the spontaneous ferroelectric polarization and this term. Right. So that is just to compare with the acoustic phonons, what we have. And we can immediately calculate the electron lifetime due to interactions with transverse optical phonons in the channel where electron interacts with the one transverse optical phonon. We can obtain somewhat simple expression, but for the clarity, let's just look at this plot. So it's temperature, and this is the electron phonon interaction rate, right? So it's zero for temperatures larger than the ferroelectric transition temperature. It's only two phonon interaction processes that appear here. But when we go low with temperatures lower than the ferroelectric temperature, this contribution increases simply because the ferroelectric polarization increases with temperature. So it increases. However, since this is this rate is proportional to the kind of the strength of the electron phonon interaction, then we go to the linear term. So it's kind of proportional to the phase volume of the available phonons for electrons to interact with. And then we just this available volume is suppressed, and we get the T log T contribution. And at very low temperatures, this contribution vanishes simply because of the vanishing electron phonon interaction at low temperatures. So that is the additional contribution to the electron interactions with a pair of phonons. So what we have, eventually, we also can have the anisotropy of electric current, and it just goes because of the electrons interaction with the transverse optical phonons is anisotropic. So we can calculate the current versus electric field. This is just a standard contribution, which may contain all possible disorder with interaction with one phonon, two phonon, and actually Coulomb interactions here as well. And what is important is that one phonon interaction induces this anisotropic term, right? So that the current actually the direction of the current is proportional to the direction of the ferroelectric polarization. So that will be, for example, if you have this electric field, let's say, along one direction and polarization in another one, then you might have a transverse voltage drop here. This was not measured yet, but this is kind of our proposal for that situation. And what we get, we can think that we explain this resistivity anomaly simply because of the onset of the one-phonon interaction, so that the resistivity first follows, at large temperatures, first follows the T2 square dependence, T2 dependence, and then we have an increase because of the onset of the ferroelectric polarization, and then again decrease just following the suppression of the electron phonon contribution with temperatures. Now we can also look into the contribution of this one phonon interaction to the Cooper channel and calculate correction to the two phonon contribution. And this is our result in the ferroelectric state of in the superconducting state of the ferroelectric metal. And we see that one phonon contribution adds up with the two phonon contribution and increases TC as we go in to the deep into the ferroelectric state, simply because this contribution decreases, simply because the omega TO increases away from the ferroelectric transition. However, this contribution increases as we go away from the transition deep into the ferroelectric state. Right, and this needs to be seen actually in experiments and needs to be confirmed. So that is our main results. We looked into the transport and superconductivity in the ferroelectric metal, taking into account the strontium titanate as a particular example. And we argue that in the ferroelectric state, there is an additional one phonon contribution due to electron interaction with transverse optical phonons, which adds up with the electron contributions with two transverse optical phonons. And the channel we are talking about might lead to the anisotropy in resistivity, to the unusual behavior in the anomalous behavior in the resistivity versus temperature, and also might affect the superconducting transition temperature. It might increase the superconducting transition temperature deep in the ferroelectric state. What I was not able to tell you, but I think it's important that tell you here, is that this interaction is anisotropic, right? And when we will look into this Cooper channel, it will mean that the correction to the order parameter due to this contribution will be anisotropic as well. So we expect the state in the ferroelectric, in the superconducting state in the ferroelectric metal to be a kind of superposition of S and D wave superconducting order parameters. So we believe that we may have a transition between S and S plus D superconducting as we go deep away from the as we go deep into the ferroelectric state, when this contribution becomes more pronounced. Yes, that is I was not able to tell you in more detail, but that is what we are working at the moment. Thank you. I don't know.
Thank you very much. Questions?
Actually, I have a question on Zoom. Can you hear me?
Yes, I can hear you.
So I have two questions. One is, what you just described doesn't really depend on the Kaya density. I mean, there is no change of the electron phonon scattering in function of the Kaya density, because at some point we can expect that as you say, the electrons will screen the polarizability. So naively, I was wondering if there is a critical density above which what you say is true or not.
You're right. This contribution depends on density. This is hidden in the, actually, I'm sorry, I was just very fast with that. I didn't go into details. although they're somehow hidden on the slide. So this is hidden in the log-ionizing temperature through the K-Fermi contribution.
Okay, thank you.
Right, and if we carefully compare the two like rates due to one phonon and two phonon contributions, definitely it will give you kind of some critical density where one will overcome the other. And yeah.
And actually, I have a second question, actually, but it was in the introduction where you show the t-square term for the 1/2. Yeah, so this E0, actually, this is the same question, right? Because when you dope STO at high doping, the omega 0 start to going up, you know, I mean, at low temperature. So that means that the t-square term that you deduce here actually will be absent in system which is not a ferroelectric, not a quantum quantum paraelectric. Let's put it in this way. So imagine I take a system like, I mean, because I have in mind like low doped semiconductors, and we also find this t-square term, and then we here there is no polar mode.
Yes, this is what puzzles me as well. So I would say that I have no clear, well, I would say it this way. So that is one of the possible explanations, in addition to electron Coulomb interaction, for example. Yeah, and this particular channel, of course, has drawbacks, as, for example, if we lower the temperature, this contribution should vanish, right? At lower temperatures, because omega TO, well, because temperature goes much lower than omega TO, but yet people see the T-squared contribution in the resistivity. So there are some issues in applying this explanation to even paraelectric states, I would say.
I see. Okay.
So yeah.
Okay. And then the last question is, you know, in this calcium doped, there is also upturn of the resistivity. I mean, I think you show the slide. Yep. If you look, for example, on the right, the yellow curve for certain range of doping, there is this upturn. So again, for you, this is a consequence of this mode, additional mode. Because this lasts down to low temperature. My point is this upturn goes down to low temperature.
This upturn goes down to like 1 Kelvin, yes, right? Yes, so that is the temperature's scale. And then it does
saturate,
saturates and goes down as we go into superconducting state. Well, we speculate, let's say that if we speculate that this might be on state of ferroelectric order. Because under certain conditions, one phonon channel might dominate over the two phonon, in another one is not, and then the interplay between the two might give you like the region of parameters where when you would see the increasement, but in other region of parameters or under other parameters, then you won't see this one phonon contribution as kind of relevant here. So one needs to kind of subtract the two phonon or divide by two phonon contribution to see some one phonon additions, maybe on the very large background of two phonon. Yeah.
Thank you very much. It was very nice.
Yeah, thank you.
Thank you.
Okay, let's thank the speaker again.
Thank
you very much. And now we switch to the next talk. We have Leonardo Di Giorgi, and the title is, where is the title? Optical signature of anomalous Hall effect in a correlated magnetic wild super semi-metal. Semi-metal indeed.
So, dear colleagues, good evening. And first of all, I would like to thank. Okay, that's it. I would like to thank the organizers of this nice conference in such a beautiful spot for the invitation, and for giving me the opportunity to convey you some of our most recent investigations, which were devoted to shed light, so to say, on the charge dynamics of an interesting family of correlated non-centrosymmetric and magnetic whale semimetals. Let me try, first of all, to briefly introduce the topic of my presentation, yet from a broad perspective, but mainly with the goal to set the stage for the motivation of our recent investigations. The last decades vividly witnessed the fundamental discoveries of relativistic phenomena in solid-state topological materials. This is because of the presence of a direct state in the electronic structure of this system, which is characterized by this cone-like, I don't see it. Yeah, okay, it's very small. By this cone-like shape, because of the linear dispersion relation in the reciprocal space, and the two cones merge actually in one single massless point. Now, by breaking space inversion and or time reversal symmetry, you can lift the degeneracy of the direct cones. So basically, you can shift in energy at the same momentum, or to make a shift in momentum space at the same energy of the direct cones, so that you have or you create a pairs of direct cones, and this is known as the whale state. Now, most recently, the research focus actually moved to the understanding of the link and interplay of magnetism with respect to this topological state. This is not only of fundamental importance, but also for possible technological application, particularly when designing novel electronic devices. I'm thinking here to the broad field of spintronics. Now, this particular topic has been boosted by the discovery of non-collinear antiferromagnet, as well as Kagome ferromagnetic semimetals, but most recently, another family of materials attracted some interest in the community, and upon which I would like to focus my attention today. These are the so-called non-centrosymmetric rare earth aluminum germanium compound, and this system indeed breaks by their own the space inversion symmetry, and from first principle calculation of the electronic structure, you can predict, for instance, the density of state for the majority and the minority spin bands. So you can see that there's a perfect balance between the two density of states for the lanthanum compound, which is an empty F orbital materials, and this support the non-magnetic nature of this system. But there's an imbalance for the cerium and the praseodymium compound, which indeed are predicted to be ferromagnet. The magnetism in the cerium compound is somehow debated in the literature, but there are robust evidence that the praseodymium compound is indeed a ferromagnet. Now, this system provides an interesting arena, because upon rare earth substitution, therefore by circumventing doping, as predicted by first principle calculation, you can study the formation of topological, mainly well state, sitting very close or even at the Fermi energy, and therefore this state should contribute also remarkably to the DC transport properties. You have mainly well state, eventually of both type 1 and type 2, depending from the effective tilting of the direct cone from where the well state originates. Now, these materials are of interest also because in the ferromagnetic ground state, particularly for the praseodymium compound, on the top of the broken space inversion symmetry, you also break the time reversal symmetry, which will have important consequences as far as the DC transport properties are concerned. Now, our motivation was to address this family of materials from the perspective of the charge dynamics. So by looking basically to the optical properties, revealing some signature and fingerprints for the presence of this topological state in the electronic structure, but also to have access to quantities which allows us to establish a link or to look into that interplay between magnetism and this topological state. So our experiment consists in measuring, first of all, the optical reflectivity over a very broad spectral range from the far infrared to the ultraviolet, so on a continuum of frequency and as a function of temperature. And this is indeed a prerequisite in order to perform reliable Kramers-Kronig transformation, from where you have access to all optical functions. And for today's presentation, I'm going to focus on the real part of the optical conductivity, which is notably well-known quantities to describe the absorption spectrum in condensed matter. Now, the focus will be mainly on the praseodymium compound, which, as I said, is a ferromagnet below a Curie temperature of 15 degrees Kelvin. From the magnetic susceptibility, there are evidence for a Curie Weiss temperature, which is double as large, about 30 Kelvin, and the magnetic ordering is due to a magnetic coupling acting as a Zeeman field between the local moment of the F orbitals along the EZC axis, which is the C axis, indeed perpendicular to the layer AB plane. Now, the praseodymium compound can be really considered as the magnetic isochemical substitution of the non-magnetic, non-cytosymmetric lanthanum compound, which I'm going to consider as a reference materials. As I said, is an empty F orbitals materials, and therefore is going to provide values or quantities which correspond to the bare band values. So this I would like to focus now on the real part of the optical conductivity, particularly spanning the energy interval from the far infrared up to the mid-infrared, and look into the temperature dependence, which in that spectral range will have some direct link with the ferromagnetic phase transition, as I'm going to argue later on. So what we have here, there are basically two features. There's a zero resonance, so a zero energy mode, which correspond to the effective metallic contribution to the optical spectra. This is going to be later on a global Drude resonance, which actually narrow with decreasing temperature. And then as interband excitation, there's this very strong far infrared feature, which is actually quite broad at higher temperature. Upon lowering the temperature in the paramagnetic state, we observe, first of all, a narrowing of this feature, and then upon crossing TC, going into the ferromagnetic state, as I'm going to show you later on, there will be a suppression, depletion of the high frequency shoulder of the feature, which then leads to a redistribution of spectral weight, accumulating in these cusp-like far infrared absorptions at low temperature. Now, we also observe some spectral weight reshuffling, however very smooth and moderate from the mid-infrared up to the near-infrared, without any specific anomalies with respect to the ferromagnetic phase transition. And then at higher frequency, all the spectra merge together in a series of interband transitions, which are all temperature independent, and which correspond to excitation from state far away from the Fermi level, so deep into the electronic structure across the Fermi level itself. I would like to focus the attention particularly on this far infrared feature, and it could be instructive to completely decouple or disentangle that feature from the total optical conductivity. In order to do so, you first need to systematically subtract the intra-band contribution to the excitation spectrum, so the effective metallic part of the optical conductivity. This can be done, for instance, by describing, first of all, the measured spectra within the phenomenological Lorentz-Drude approach, which is a very common tool in optics in order to identify the various contributions which affect the optical conductivity itself, which indeed is an additive quantity. So what we did consider here, two Drude terms, a narrow and a broad one, accounting for the multi-band nature of this system, but later on these two Drude terms will define the global Drude resonance for the optical spectra, and then a series of Lorentz harmonic oscillators for the final frequency excitations. The higher frequency oscillators are temperature independent, and I will particularly focus the attention here on these two first harmonic oscillators, which fully shape the far infrared feature, namely this strong interband contribution in the far infrared. I don't have time to go into technicalities about this fitting procedure. but I would like to point out that this is really a minimal approach in order to describe the measured spectra. And also we did apply the very same fitting philosophy for all members of this family of rare earths, aluminum, germanium compound. So whenever performing a comparison between different compounds, particularly with respect to quantities which eventually profit from this type of phenomenological analysis, we believe that that comparison is reliable because based on equal footing. Now, first of all, as I said, you can define out of this procedure the global Drude resonance, which is shown here, for instance, for the low temperature. Then you can systematically subtract that intraband contribution from the optical spectra, and you are left with the clean interband contribution in the optical conductivity, which is shown here as an example at the lowest temperature. And here we immediately recognized a first important feature in the optical spectra, namely that the low frequency tail of these far infrared absorptions is characterized by linear frequency dependence. And this is a pretty well recognized feature in a large variety of topological materials. It is directly related to the linear dispersion relation in the reciprocal space related to the direct cone from which indeed the well state originates. Now, what is eventually peculiar here is that we have just one single linear frequency dependence without any kink in between. This is also an indication that the well state, as predicted by band structure calculation, are of type 1, so the direct cone are not tilted. And then you may also observe that this linear frequency dependence cut the frequency axis at a finite frequency. This is an indication for the presence of tiny massless gaps at the direct cone themselves. And this could be due to the reinforced virtue by spin-orbit coupling, particularly at low temperature, or a consequence of correlation effect in the spirit of the whale mode scenario as predicted theoretically. But beyond that, let me mention that evidence for gapped whale nodes was also provided at selected location in the Brillouin zone in the reciprocal space by the ARPES investigation, which indeed directly imaged the electronic structure. That linear frequency dependence has some importance in another from another point of view, namely it can be shown that the slope of that linear frequency dependence is inversely proportional to the Fermi velocity. So we can extract the Fermi velocity as a function of temperature, which is shown here from the charge dynamics, from this interband contribution, identifying that absorption feature as a feature of topological nature. And here is the results for the praseodymium compound. There's a very weak depletion from higher temperature. Otherwise, the Fermi velocity is very low and flat and temperature independent in the paramagnetic state. Then we observe a sudden enhancement here, however, very moderate upon crossing the Curie temperature going into the ferromagnetic state itself. It could be now, it is instructive now to compare these results with what we got as far as the temperature dependence of the Fermi velocity in the lanthanum compound. This quantity was obtained after the very same procedure, and the behavior is very distinct. In fact, the blue dashed line here is not just a guide to the ions, but correspond to a temperature, to a logarithmic temperature dependence of the Fermi velocity, which is indeed the expected, from a theoretical point of view, this can be predicted for weakly interacting topological materials. And from a theoretical point of view, that logarithmic divergence is supposed to vanish as soon as correlation effect play an important role. Indeed, we believe that that strong suppression of the Fermi velocity between the lanthanum and the praseodymium compound at low temperature is an indication for the important role played by correlation effect in these materials. And in fact, this renormalization of the Fermi velocity between these two compounds actually goes hand in hand with the very equivalent renormalization of the kinetic energy, which is directly related to the Drude weight, namely the spectral weight encountering the effective metallic contribution of the optical spectra, and which imply also a very important enhancement of the effective mass of the itinerant charge carriers in the praseodymium compound with respect to the lanthanum one. Obviously, it remains to be seen whether a Kondo-like scenario, because of the hybridization of the localized F states with the whale state sitting or being very close to the Fermi level, may be promoted in order to account for that role of correlation effect or for the onset of correlation in these materials. However, that strong suppression of the Fermi velocity has been found also in many other correlated heavy whale or nodal line direct semimetals. Let me now insist a little bit more or from another perspective on this far infrared absorption. And let me point out, as I'm trying to show you here by this inset, that in fact the spectral weight of this resonance increases upon crossing or upon going into the ferromagnetic state. The spectral weight in optics is the integral of the optical conductivity in a finite frequency interval, and in fact what you see here, that going from the paramagnetic, the red curve, into the ferromagnetic state, there's an obvious enhancement in spectral weight, which we can systematically extract also with the support of our phenomenological fitting procedure. And it turns out that the spectral weight of, as you see here, we can in fact focus the attention on the low frequency first harmonic oscillator describing the edge, the low frequency edge of that far infrared absorption. And within this approach, the spectral weight just corresponds to the square strength of the harmonic oscillator itself, which, as you see here, increases going into the ferromagnetic state. So you can extract in this way the temperature dependence of the spectral weight, which turns out to be basically constant temperature independent in the paramagnetic state. But at the Curie-Weiss temperature, there's clearly the onset for a progressive enhancement of the spectral weight of this far infrared resonance, which I tried to convey you before, is topological in nature. The most astonishing result is that this goes hand in hand with the equivalent enhancement, so to say, of the anomalous Hall conductivity, which has been measured independently. These are just data from the literature with this DC transport technique. And the two dashed line here, by the way, are just guide to the eyes. So this means that, or may allude to a possible association between a resonance, which is topological in nature in the charge dynamics, with state characterized by a very large effective Perry curvature, which indeed is the prerequisite in order to get anomalous Hall conductivity. And I would like to further argue on that, and very instrumental in that respect are first principle band structure calculation, which were performed after the density functional theory, following a procedure which is indeed well established in the literature also for this very same family of materials. First of all, you can identify the position of the well state in the paramagnetic and ferromagnetic state in the reciprocal space, and then we just selected a few of those well states representative of region in the reciprocal space where these well states gathered together and for which a Fermi surface was also predicted. Then we consider direction running nearby those well states, and we calculated the band structure of these well nodes or around those well nodes. And here I don't have time to go into too many technicalities or details, but I would like to emphasize something that you may observe by yourself looking to this data or to this calculation, namely that in the ferromagnetic state, the band structure developed some kind of asymmetry between the negative and the positive direction in reciprocal space with respect to the fully symmetric situation in the paramagnetic state itself. And this is going to have important consequence in the temperature dependence of the occupation function, which then determines the interband transition in the charge dynamics. You can also look at which are the most probable interband transition from a band structure point of view, and it turns out that in the paramagnetic state, the interband transition are grouped around two characteristic resonant frequencies, the red and the green bars here. For the ferromagnetic state, they distribute in a far infrared interval of energies represented here by the blue bars. Now, from this calculation, you can then extract the real part of the optical conductivity, for instance, via the Kubo-Greenwood formula, which is shown here in comparison to the experimental quantity. Now, let me immediately warn you that this comparison is probably more reliable in the energy interval of about 100 millielectron volt around the Fermi level, because in that spectral range or energy interval, the impact of the F electron is not that pronounced and invasive in the electronic band structure, and this might explain some deviation at higher frequencies. But from the calculation point of view, so in that low spectral range, you see that in the paramagnetic state there are actually two single resonance or absorptions, then going into the corresponding to those characteristic resonant frequency, the green and the red that I was pointing out before. Then in the ferromagnetic state, we observe a depletion basically of the R frequency 1, favoring a spectral weight redistribution, so that basically you have a distribution of interband transition in the far infrared and an accumulation of spectral weight into this cusp-like feature in the absorption spectrum. And this copies rather well with what we observed in our experiment, at least as far as the redistribution of the spectral weight is concerned. Let me mention that the calculation was done at t equals 0 without thermal broadening, so we believe that indeed thermal broadening prevents us from an experimental point of view to resolve in the paramagnetic state that absorption into two single excitation. But more important than that is that from this calculation you can then extract also the effective Berry curvature shown here for the ferromagnetic state within the y-x plane. The quantity is already integrated along the z-axis, and you see that that Berry curvature is very much enhanced, and interestingly enough, at location in the reciprocal space coinciding with the position of the whale nodes. Here the green dots correspond to the projection of those whale nodes within the y-x plane, and the black star are the selected one for our band structure calculation itself. And this brings me back to the previous result that I was emphasizing by the previous view graph, and I would like to reproduce here for the temperature interval below the Curie-Weiss temperature, where I did point it out the relationship, or let's say the similar behavior of the spectral weight of this topological resonance in the charge dynamics with the anomalous Hall conductivity, which eventually is no longer a surprise because the anomalous Hall conductivity is supposed to be directly proportional to the integral over the Brillouin zone of the convolution of the effective Berry curvature with the temperature-dependent occupation function. So basically we may say that this progressive enhancement of the spectral weight for that resonance in the charge dynamic, which is indeed topological in nature, indicate the empowered matrix element for the dipole active excitations in the charge dynamics, for which in fact very large Berry curvature may be predicted. And this brings me to the conclusion of my presentation. I try to convey you that from the charge dynamics we can reveal the characteristic features as far as the optical response is concerned associated to the presence of topological state in the electronic structure. Particularly the linear frequency dependence here is a typical indicator for the linear dispersion relation in reciprocal space due to the Dirac cone from which the wave state originates. And the linear frequency dependence allows us to extract then the Fermi velocity, which is very much depleted indeed in the with respect to what you get in the lanthanum compound, which is probably a sign of or an indicator for the important role played by correlation effect. Obviously, there's here an enhancement here, which is, however, very moderate. This could be due to the fact that in the ferromagnetic state, the suppression of scattering due to spin fluctuation facilitate again the movement of electron, but nonetheless, that values are very much suppressed with respect to what you get in the lanthanum compound. But more important is probably the discovery of that spectroscopic link, so to say, between the spectral weight of that resonance in the charge dynamics and the anomalous Hall conductivity, which, as I said, was determined totally independently. And this indeed has an important implication in the sense that a very large effective Berry curvature associated to the non-trivial topological state and concomitant with the broken time reversal symmetry indeed may deem necessary in order to provide the environment, so to say, for a very large anomalous Hall conductivity in these materials as observed by a transport type of measurement. More details about this work can be found at this recent publication. And let me then conclude by acknowledging the great work of my team. I would like particularly to mention my postdoc, or my former postdoc, Run Yang, now at Stuttgart, my PhD student, Matteo Corasaniti, who is about to finish and defend his thesis on this topic in a month from now. And then we got very beautiful spacemen from Sidomir Petrovic at Brookhaven National Lab, and we enjoyed the collaboration with teams based in 3 different places, in Dresden, at Beijing, and even at the University of Fribourg in Switzerland for the DFT band structure calculation. Last but not least, I would like also to acknowledge the partial support of our funding agencies in Switzerland. And with that, thank you very much for your kind attention.
Thank you very much. And now questions, please.
Yes, Leo, thanks a lot for this very interesting talk. I have a question, right? I mean, you somehow said now, oh yeah, this change of the Fermi velocity is minor, but it's basically a factor of 3, and within at the phase transition, this factor of 2, which seems to me it's a lot. Is this really some kind of trivial thing? So there,
you
extracted Fermi velocity, right? I mean, it changes at the Curie temperature at 30 Kelvin, right? By a factor of 2.
Yeah.
That seems like a lot.
Well, as I said, one possible explanation for that is that when you suppress scattering by spin fluctuation because of the ferromagnetic state, and particularly also because at the ferromagnetic state, as I was trying to convey you, we have certainly a reconstruction of the electronic band structure. So this may obviously explain also this change. Nonetheless, the values by itself in absolute value remain pretty much depleted and very low with respect to what you get in the lanthanum compound, which for sure. So that was somehow my point. But I mean, maybe this is a speculation, what I just said, that by suppressing scattering by spin fluctuation, you facilitate the movement of electron. But on the top of that, there's also a reconstruction of the electronic band structure, which is even more important in view to the very large Berry curvature, which then facilitate the anomalous Hall conductivity.
And then if I may, I have a second question. So now when you're fitting this, you're subtracting the both Drudes, and then you have this mid-infrared peaks, which basically you had like 2 of them, right? Well, if you had like 2 oscillators in the mid-infrared, so like L1 and L2, but you're basically just fitting both of them and you have this linear. So is this L2 so far away that you can neglect it, or does it play a role?
I mean, maybe I have maybe I have an additional view graph just to convince you that this is, probably is coming, yeah. Here it is. Okay, so here I'm comparing that with the lanthanum compound. And then you see that in the lanthanum compound, it barely changes in temperature. And by the way, if I just calculate the difference of spectral weight, for instance, at low temperature with respect to 100 Kelvin, which is large enough with respect to any magnetic phase transition, you see here, for the lanthanum compound, it remains flat. There's no change. But then there's a reshuffling of spectral weight between these 2 shoulders or these 2 oscillators, which is indeed an indication for the reconstruction of the electronic band structure because of the ferromagnetic phase transition. And in the lanthanum compound, which doesn't have any magnetic phase transition at all, I mean, there's absolutely nothing. And the 2 oscillators here are so distinct from the tail due to the intra-band contribution, Drude-like contributions, that basically, I mean, this is very trustable. I mean, you cannot just say that this change here is due to some kind of high frequency tail of the intraband. I mean, they are very well separated, the two ranges.
Okay, thanks.
Yes, could you show us your last slide again, please, the one with the conclusions?
Yeah. Now I have to go up. Yeah. 1 second, should come. Okay.
Okay. So now here I notice in the blue curve there is a peak at 0 frequency, okay?
Oh,
and,
yeah.
Okay. Now the question is, can you bring that into correspondence somehow with DC transport?
No. I mean, I think that this is probably somehow, you know, when you subtract. Okay, I could just claim it's a kind of spikes of noise because it's a very low frequency at 0. I mean, we cannot really measure down to 0. When you subtract the Drude resonance from the measured quantity, you might have some kind of. I would not pay attention to that.
So you have already subtracted the DC component to get this curve.
Yeah, I mean, this is the delta one, you see? This is already the, let's say, what I called clean interband contribution.
Okay, thank you.
I mean, yeah, probably you saw before, if I can go back quickly to the, here I'm coming. So you see, the Drude resonance in that one is definitely much larger. And then I subtracted that part here, the dashed line.
Okay. More questions? Well, if not, let's thank the speaker for a wonderful talk one more time. Let's thank all the speakers of the session, and thank you very much. One advertisement.
Okay, we have an announcement for the proceedings. So the journal where the proceeding will be published is open source, and there are some open source charge, but they are completely paid by the conference and the journal. So for all invited speakers, there is no fee for open source, and so this is the information. And in any case, if you are interested, you write to me, so I can help you. The editorial staff is very nice, and they help you very much. Thank you for your attention.
Thank you.
And small contribution. Okay. Okay, we don't have many people in the audience, but you will have one copy of this in your room tonight after the gala dinner. So please do consider it. And second thing is, from my experience, high-level scientists like Laura, Erika, and Valerie don't write papers, and ask one of your PhD students. And it will be good for him or her. And let's have a very good, prestigious special issue published for the first conference on quantum materials and technologies. I think this is our common understanding. Yes. Laura, we need your support. Erika and all. So we may also announce the same thing when most people, we have the gala dinner here, so this place will be prepared for the gala dinner in 2 hours. Yes. You will see the service sector in Turkey. So. So we will again announce this during the gala dinner, and enjoy your gala dinner tonight. I think starting at 8 o'clock. And this is what I will say. Yes, okay. Anything you want to say something? Okay, you are also co-editor.
Sorry?
So you can say anything if you want.
Well, okay. So the idea was that we will have these small topical reviews on a, let's say, okay, selected topics, and okay.
Yeah, we are opening for this journal the possibility to write topical review. Topical review is a perspective where you have a single paper, but with a number of order of 5 or 6 people that write only 2 pages, 2, 3 pages, or 4, from 2 to 4. And it will be a topical, it will be a single article with 4 sub-articles, like subsections, where each group is responsible for what they write. However, there is the 4 short paper are in a common topical review. And this is very important for the new perspective for young people and so on. And it's an intermediate between a review and a short paper. So it's been very successful in many different communities. In theory, very different theory group, mathematics, so all chemistry. So it's a new kind of review paper. And this is very nice because it's not a paper with 10, 20 authors for speaking on topics, but each small group present its point of view. And they are together. So and for us, it's less work to be done because we write a paper of like a longer abstract in some way. I think Laura can write something on heavy fermions. So try to put together a group of 5. You can ask a group of 5 or 4 by 4, so 16 pages or 20 pages. And you ask a group to write a topical review. And it will be very nice for the young people. I think young people they read less papers. So I think it will be very important for them to this kind of divulgation.
So I didn't know you were doing this, but I was editor-in-chief and editor of Reports on Progress in Physics for a very long time. And we would run into people who would agree to write a review article, but it was too much work. And then we started topical reviews. But your idea is something I haven't heard of before, that I could be like an editor or write an introduction and get 3 or 4 people to write it. Yeah, that's a new idea. Okay. Okay.
And then the other can write 4 pages. And for example, for heavy fermions.
Do they have to be in different institutions?
It's not important. It's important is that, the idea came from my passion for history of science. So Dirac had the one idea. Schrödinger has another idea. Pauli is writing another thing. Fermi is writing another thing. Bohr said to them, write what you find and put together. At the end, you see that a different point of view converge.
That's neat.
You understand? Because if you write a review with 10 people, then you don't. There is something like homogeneous part. On the contrary, also differences between different groups is good in the same topic. It's been very successful in different, in complexity, journal complexity, they did another. So I've seen different plays, a little bit different from each one. But so the journal decided to accept this kind of new contribution. For this kind of conference on quantum material, I think it's a very good, for example, you can select what is the George, optical property that has been this. So if we coordinate, it would be very nice results.
Well, so it's the end of our one more working day. Thank you very much. And okay.
It's been a long day.
It was a long day.